Hi, I'm Tim Dr. T. Shamillard, and I'll be your instructor for this course. I'm an associate professor in the computer science department at the University of Colorado at Colorado Springs, where I predominantly teach game programming courses, but I also teach some general computer science courses as well. I'm the program director for our Bachelor of Innovation in Game Design and Development, and I have 5.5 years indie game development experience running a company that I started with my two sons. My two sons have sort of moved on to other things now, so I do my game development in my one-man shop, Burning Teddy. So why Dr. T? Well, I am a doctor, even though I'm not the kind that helps people. And my name is Tim, so the T makes sense. But really the reason is I teach a lot of freshman students. And at least here in the US, students in high school are taught to call their high school teachers Mr. Smith or Ms. Jones and so on. So the very first time one of my students raises their hand and says, Mr. T, Mr. T, everyone knows how wrong that is. In case you need a visual reminder, I'm Dr. T, I'm not Mr. T. Okay, this is a 4-week course, and for 3 of those weeks, the first 3 weeks, the graded work is automatically graded programming assignments, and that's worth 75% of your grade, those 3 programming assignments. There's also a final exam worth 25% in the final week, and don't be alarmed by that. It's really just a big quiz with a few questions to make sure you've internalized the stuff from the course. There are also 13 exercises that aren't worth any points, but they're really important if you need some additional practice with C++ or Unreal Engine or both. And there are also some practice quizzes sprinkled throughout the course as well. So the lessons that you'll have in this 4-week course include getting started and your first C++ code in the first week. In the second week, you'll learn about data types, variables, and constants. In the third week, you'll learn about classes and objects. And in the fourth week, you'll explore Unreal Engine basics, and you'll have a finishing up video. I assume you have previous programming experience. Pretty much nobody does C++ as the first programming language, so I'm assuming you're coming into this course with some programming experience. I don't assume you have any Unreal Engine experience. We'll start with Unreal Engine from the very beginning, and in fact, I'll cover lots of foundational topics in C++ as well. It's just that C++ is more complex than many other programming languages, so it's important for you to have programmed in something else before. The only way to learn how to program in C++, and the only way to learn how to make Unreal Engine work, is to do it, right? Practice, practice, practice. And that's one of the main reasons I've given you lots of exercises as supplemental material for you to get your hands dirty and try to build that muscle memory of how things work in both C++ and in Unreal Engine. Frustration is normal. Even if this is your second or third or fifth programming language, it's common to get frustrated with either C++ or Unreal Engine, and that's just a natural part of the learning process. So try not to get too frustrated, even though, it is going to happen to probably every single one of you. When you get stuck, remember that there are lots of discussion forums, or remember for the very first time, I'm telling you now, there are lots of discussion forums that you can join in on this course. And of course, you can always search the internet as well to try to get solutions to your problems. So I hope you have a great time in this course. I hope you learn a lot, and it's time for us to get to work. This is the totally optional, don't watch it if you don't want to, meet the instructor lecture. I'm Tim Dr. T. Shamillard, and I grew up in a small town in southeastern Massachusetts named Norton. And after high school, I went off to Georgia Tech to pursue a bachelor's in electrical engineering degree but I was only at Georgia Tech for a year. So if you'd like, pause the video and guess for why I only stayed for a year, and then continue. As one of my past students said, I left for the love of a good woman. So my girlfriend was in Massachusetts, Georgia Tech is in Atlanta, Georgia, and that was too far for me. So I spent about a year and a half putting stuff into boxes and handing it to the UPS guy. And then I enlisted in the U.S. Air Force, went off to basic training, went to technical training school, and after about 4 months in the Air Force, I got married. So pause the lecture again if you'd like to decide whether that was the same girl I left Georgia Tech for or somebody else. The answer is it is in fact the same woman, and we are still married. So here we are in the Air Force. We went off to Omaha, Nebraska for our first tour, and then after 16 months, the Air Force decided to send me to school full-time to pursue a bachelor's degree in electrical engineering at Georgia Tech. So I did get to finish that degree at Georgia Tech in electrical engineering, and then I went off to officer training school and got my commission as an Air Force officer. Our first assignment in the Air Force was at Los Angeles Air Force Base, where I spent 4 years managing contractors writing software to help us fly satellites. Particularly orbital software was my general area of expertise. We had our first 2 children, both boys, while we were in Los Angeles. And I also pursued my master's degree in computer engineering at the University of Southern California, going to school nights. Finished that tour after 4 years and went off to the U.S. Air Force Academy, where I taught undergraduate computer science courses for 2 years. Now, the Air Force Academy is usually a 4-year tour, but I only spent 2 years there. So if you'd like to pause the lecture video again and try to guess why I only spent 2 years, go ahead and do so. The answer is the Air Force decided to send me off to UMass Amherst to pursue a doctorate. So I am in fact a doctor of computer science, so I don't actually help people. And my entire family loved the part in Treasure Planet, the movie, where there's a non-medical doctor and he is trying to help somebody who's injured, and he says, I just sit here and I'm useless. And I saw that movie with my entire family at the movie theater, and at that line, every single person leaned over and looked at me. So everyone knows I'm a doctor, just not a real doctor. Okay, so I finished off that degree and went back to the Air Force Academy for that full 4-year tour that I should have had in the first place. And then my final assignment was to Washington, D.C., where I spent a couple of years managing contractors, developing web applications, and the databases that support those web applications. And then I retired from the Air Force. So I've been at the University of Colorado at Colorado Springs since 2003, and I've taught a variety of courses, including graduate-level software engineering courses, undergraduate computer science courses, and undergraduate game design and development courses, all of which I created from scratch. And in fact, we now have a Bachelor of Innovation in Game Design and Development, and I teach many of the beginning and the final course in that particular program, and I'm the program director for that program. So at this point, I exclusively teach game development courses. I also spent a year and a half as an indie game developer in a company that I formed with my 2 sons, and that's Peak Game Studios. And we did a number of games both on speculation and on contract. So here are the games we built on speculation. The 2 images on the left are a game called Ket that's based on an actual board game. So we got the license from the board game manufacturer. And you can think of this as chess with lasers. And you can actually download a free version of this game at this point from the Burning Teddy website. I'll talk about Burning Teddy soon. The other screenshot from the upper right is for a game that we didn't quite finish as we shut down the company once my sons sort of grew up and moved on to do other things. And that game is called Battle Paddles. And you should think of this as Pong with weapons, because that's sort of the big idea behind that game. We didn't quite finish it, but we'll get back to that game as well. So on this slide are the games that we built under contract. So as a company, we went and we got a contract to build some games, and we actually got paid to build them, and that was awesome. So the two on the left are for educational games for 8th graders. The one all the way to the left was a set of 4 mini games to teach about physics. And the title of that group of mini games was Physics with Neat Details. And if you think of the acronym for that, it's PWND. And so, of course, a little tongue-in-cheek game development, of course. And the lower one was to teach 8th graders about robotics. So they would configure a robot with various attachments to go complete a number of missions. Again, there were a few mini games to do. The upper right one is something called Colorado History Arcade. We got a contract to teach 4th graders about Colorado history, and that game was deployed on the Pikes Peak Library District website. So all of the games we built as a company, except for the Colorado History Arcade game, were using C#. We happened to use XNA Game Studio to do that. But now, of course, we've moved on to Unity. The company hasn't, but I have. And so that brings us to this next slide, where I tell you I now have a small company, and by small I mean just me, called Burning Teddy. And I use that company to publish textbooks and online courses, and of course, also to do game development. So that Battle Paddles game that I showed you the screenshot from, I am in the process of porting that over from XNA Game Studio to Unity. That is about 60,000 lines of code, so it's going to take a little while to port, but at some point that will be on the Burning Teddy website, burningteddy.com. And I'm also working on another smaller casual game that is called Balloons Extreme, and I'll actually post my progress on burningteddy.com as I build that game in Unity. So Burning Teddy, all the game development I'm doing is actually in Unity. So when I'm not teaching and I'm not doing game development, what am I doing? Well, a number of different things. But one of those things is cycling. So riding a bike is one of my joys in life, I guess. So these are my 3 bikes. The blue one is the oldest one, and that's really an old bike at this point. But I used it to really get into cycling, not racing so much, but doing long rides like a number of centuries, which are 100-mile bike rides, including, at the time, one of the 10 toughest centuries in the United States. And so that century had over 10,000 feet of climbing. That's what makes 100-mile bike ride harder than another is, elevation gain. And so I did a number of bike rides. The mountain bike, the one on the bottom, is a result of going mountain biking with some friends one day, and I loved it so much that I went out and bought the mountain bike the next day. The bike all the way on the right is my triathlon bike. So, being a cyclist, I did a lot of long rides. I also did a bunch of running, including a number of marathons and a running race that goes from the bottom to the top of Pikes Peak here in Colorado Springs. I did that running race multiple times. And once you've biked a long time and run a long time, you say, well, you might as well do some triathlons as well. Just add a swim and you'll be fine. And so I've done a variety of triathlons, all the way from sprint distance, which are really short, all the way up to an Ironman distance race. I also play guitar. I started doing that way back in high school and then gave it up for decades while I was raising my family and doing other things. And now I've started up again to try to learn how to do it even better than I used to. So moving from left to right, the acoustic is a Yamaha acoustic that I bought way back when while I was just out of high school. The next guitar is a Joe Strummer replica. Fender came out with a Joe Strummer tribute guitar some years ago, and that was my starting point. But I replaced the 3-saddle bridge with a 6-saddle bridge because that's what Joe Strummer used. I got that relic pick guard from a place called Extreme Creations, and I even took the stickers that were on Joe Strummer's guitar and cut them into the shapes that they were worn into by the time Joe stopped playing the guitar, and affixed them to the guitar in the appropriate places. The next guitar is a Gibson Les Paul Gold Top from a couple of years ago, and the one all the way on the right is my most recent guitar. That is a Fender Stratocaster American Professional 2, and I didn't have a Strat, so I wanted a Strat, but I also couldn't resist getting it in the gorgeous Miami blue color. Really, the other thing, other than, interesting, like, reading books and stuff like that, the other leisure thing I do is I play video games. That should come as no surprise to you. And so the question is, what kind of video games do I play? And you should pause the video, guess in your mind what those might be, and then you can move on to see a screenshot of what I use to play my video games. You can see racing games are my passion, so really racing simulations, so, realistic racing games rather than arcadey racing games. And if you're interested in all the details of that racing rig, you can go to the PDF that I've provided as a resource for this lecture. So there you have it. None of this has anything to do with course content, but it gives you a little more insight into who's teaching you in the course. In this lesson, we'll set up our development environment and we'll write our first C++ code. The C++ code you'll write throughout this course will be of two different forms. One form will be something called console applications or console apps. And these are applications that we run and the output shows up in a command prompt window in Windows, or it shows up in an output pane in Xcode, but it's text-based output. So unless you're writing text-based games, this isn't really game development, but it is learning to program in C++. The other kind of C++ code we write will be Unreal scripts. So we'll write C++ code that drives our Unreal games. Early on, we'll have output in an output log window, textual output that we're displaying in our Unreal games. But as we learn more and more about how to develop games in Unreal, our output will actually be the gameplay that we implement in our games. So what specifically will you learn to do in this lesson? You'll learn how to install Visual Studio on Windows, or you'll learn how to install Xcode on a Mac. And you only need to do one of those two things. If you're using Windows, you install Visual Studio. If you're using a Mac, you install Xcode. Then we'll learn how to write a C++ console app in Visual Studio. We'll learn how to write a C++ console app in Xcode. And then we'll install the Unreal Editor. Once we've done that, we'll implement C++ Unreal scripts in Unreal, both using Visual Studio and using Xcode. In this lecture, you'll learn how to install Visual Studio on a Windows machine. C++ isn't available in Visual Studio on a Mac, so if you're on a Mac, you'll be installing Xcode, not Visual Studio. The big idea, though, is that throughout this course and other courses in the specialization, you're learning some of the C++ programming language, both in console apps and in Unreal. You're not trying to learn about a particular integrated development environment like Visual Studio. Okay, let's go install Visual Studio. The best way to make sure that you get this installation correct is to follow the step-by-step instructions that I gave you in the Setting Up Your Development Environment reading. So this video is just an extra resource for you, but really you ought to just go read the steps there and follow them. Okay, so here we are on visualstudio.com. And if you're on a Mac, leave now. You should go install Xcode. If you're on Windows, we want to install Visual Studio Community 2019. We do not want to install Visual Studio Code. Some people seem to want to do that, but don't. That's not what we want. Over here on the left, we have Visual Studio, and if I hover over this drop-down, I can pick Community 2019. Don't pick Professional or Enterprise, just pick Community 2019 and download the installer. Once you've downloaded the executable for the installer, go to that location and double-click that executable. It'll do some stuff, and then it will bring you to something like this. Although yours won't say modify or launch, yours will say install. But I'll click modify just so we can look at the workloads that you should make sure you have installed. So you should make sure you have checked desktop development with C++, and that you have checked game development with C++. I know you see some Unity and C# stuff over here. Just ignore that. We're doing C++ and the Unreal Engine in the courses in this specialization, so you need to check those C++ boxes. Also, in individual components, you should scroll down to Code Tools, and you should make sure you check Help Viewer so that you can install local help in Visual Studio if you want to. And then you go over here and you click, it probably says install for you, and you go here and you just click install, and then you wait for what feels like a very long time to get it installed. Once you have it installed, you'll have Visual Studio installed, and you can search in your search box on Windows, type Visual Studio, and it will bring up a result you can click. I've added a shortcut to my desktop, so I just double click that to start Visual Studio, but you can access Visual Studio however you want. The instructions for setting up your development environment tell you how to set up local help as well, and I strongly suggest you do that, but that's your choice. To recap, I'll remind you that throughout the courses in the specialization, you're trying to learn about programming in C++, both inside and outside of the Unreal Engine. You're not trying to learn a specific integrated development environment. With that said, if you're going to use Windows, you should now go install Visual Studio. In this lecture, I'll show you how to install Xcode on a Mac. I'm using Visual Studio to record almost all the video lectures, and I'm a Windows guy, so I use Visual Studio as my integrated development environment. But C++ is not available in Visual Studio on a Mac. So if you're going to use a Mac to learn how to program in C++ in this course, then you need to install Xcode. I want to make sure you understand that what we're really trying to learn in the courses throughout this specialization is how to program in C++, both in and out of Unreal Engine. So we're really learning C++. And C++ is 99.9% the same whether we're using Visual Studio or Xcode. So if you're using a Mac, you should keep watching to learn how to install Xcode on your Mac. We'll start by opening up Safari, searching on Xcode, and picking the first hit. Select Download over on the right. You may need to sign in. And click Download on the right. I'll say Continue. I'll cancel out of this. This is the tool I want. So I'm going to download, which will take a while, so wait patiently while that happens. And now that that's finished, we can actually just close all this stuff out. And if you go to the Finder and you pick Applications, and you can see that Xcode is here in our Applications folder. So if we double-click Xcode, we may need to install some additional required components, so go ahead and click Install, fill in your password to authorize this, and wait while the rest of the required components are installed. And when that's all done, you'll have Xcode opened up. To recap, I want to remind you that we're learning C++, both in console apps and in Unreal Engine games, so we're not trying to learn an integrated development environment. That means it doesn't matter that the videos are mostly recorded in Visual Studio because C++ is mostly, almost totally, the same across those two environments. With that said, if you're on a Mac, you should go install Xcode now. In this lecture, you'll learn how to create your first console app in Visual Studio. And even if you're planning to use Xcode, you should watch this video because I cover some of the basic programming ideas in C++ that you need no matter what development environment you're using. Speaking of development environments, when we develop software, we usually use something called an integrated development environment. And it's integrated because it lets us both type in our code, and build our code and debug our code if we need to and run our code and so on. When you're on Windows, at least in this course, you should be using Visual Studio. And if you're on a Mac in this course, you should be using Xcode. So despite the fact that almost all the videos will be recorded using Visual Studio, that doesn't even really matter because we're learning C++ in console apps and in Unreal games. So we're not learning an IDE, so it doesn't matter that Visual Studio is the one I do it all in, even if you're on Xcode. With that said, let's go build a console app in Visual Studio. Okay, I've started up Visual Studio, and you won't have a big list of recent projects you've been working on, so you can ignore that part. We're going to create our first console app. So over here on the right, the bottom option is to create a new project, and I'll click that. And we come to recent project templates. And you won't have the C# stuff here either, or even this DLL for C++. You'll probably only have the Windows Desktop Wizard, but that's what we want to pick. So I've selected it by left-clicking it, and then we say Next. And now we give it a name, and I'll call this First Console App. And I'm just going to save it in the default repos folder, but you can click here to browse around your computer to store it wherever you want. It's important for you to remember where you store your projects because for the graded work in the course, you'll have to upload particular files and you have to know where to go find them. So this will store this project in a folder called First Console App in my repos folder, as you can see in the location. But when you pick a place to store it, remember where you stored it. Okay, I'll say Create. We're going to leave all of this just the way it is, and I'll say OK. And here's what we get for our template console app code. There's lots of descriptive stuff in here that we'll delete, but the first thing I'm going to do is up here at the very top, I'm going to replace this with the standard copyright notice that we'll see when we do Unreal Engine projects as well. So That's the standard copyright notice that I include in my Unreal code. And this stuff down below says, here's how we run the program. Here's how we debug the program. And we won't worry about debugging yet. We will run it soon. It says use the Solution Explorer window to add or manage files, and that's over here. Over here on the right is the Solution Explorer, and you'll typically expand source files so that you can see your C++ file. So C++ source code files come with two extensions. In general, CPP is C++, and that's what we'll use for a while. And later, we'll also discover that C++ often has header files as well, but we don't have any header files in this project, and that's fine. We aren't going to be using source control. The output window is down here. This tab, let me magnify for you. This tab right here is the output window. I'll keep it magnified for a while. The error list window to view errors. Here's the error list window. We don't have any errors yet. And then there's some other descriptive stuff that we don't actually need to use. So I'm going to stop magnifying again, and I'll delete this stuff, but I'll zoom in on the code. So what is the structure of this code we got? We have this comment at the top that is that copyright notice. We have something called pound include, and we use pound include to include essentially libraries that other people have written that will help us write our C++ code. So we are including the IO stream or input-output stream library so that we can use the functions that are in that library. This right here is called the entry point to our application. This is what's called a function in C++. This function has two components. The one on the right is the name of the function. So this function is called main. And the one on the left is called the return type for the function. So we will learn as we interact with C++ functions that some functions, many functions, return something when they're done executing. And this tells us what the main function returns. I'm going to add a javadoc comment at the top of this code. And javadoc comments are used to automatically generate documentation for the code that we write. So it's a really good idea to comment every function we write and to comment every class we build, which we'll get to soon, with a javadoc comment. I'm going to remove that @brief at the beginning. The Visual Studio environment adds that for me, but I don't actually want it because I'm going to use the commenting style that is standard for Unreal Engine projects. I know this is a console app, but we want to just be consistent with the style that we use for commenting and capitalization and everything across our console apps and our Unreal Engine games in the courses and the specialization. So we'll just follow the Unreal Engine naming guidelines and commenting guidelines, coding standards, if you will, and we'll do that even here in our console apps. So I will just say print something, and this @return says here's where we should provide a description of what gets returned from this function. So I'm going to put here that this returns the exit status. It's basically an integer that says, did the main function run to completion fine, or did it crash along the way? We can actually run this code right now because we got this line of code in our template. Before we do, let's actually compile the code first. So up here on the top menu bar, we can select Build Solution. The hotkey on my computer is F6. I have seen it be a Control-Shift-B combination. I've seen it to be F7. So the first time you do this, you'll need to do it this way to figure out what the hotkey is. And if you always want to use F6 like I do, then you can Google how you can change these shortcut keys. Okay, so I'm just going to click Build Solution. And I'll zoom in again. And down here in Output, you can see I got a build 1 succeeded. So that's great. This built just fine. That's nice. There were no compilation errors. And now I want to run it. And up here on the top menu bar, we have a debug option. And we can either start debugging or we can start without debugging. There will be times that we want to debug a console app, but usually we just want to run it. So I will Control F5, and as you can see, it prints out Hello World, and now I can just press an A key to close the command prompt window. So how did that work? We said here that we want to send something to the output stream. And this first part is called a namespace. This is the standard namespace. And we don't have to pound include it or anything. If we use other namespaces, we'll have to pound include the library that includes the namespace. But here, we're just saying this stream is a part of the standard namespace. Then we put 2 less than signs because you can think of this as sending the stuff here into the stream. That's a good way to think about this. So we're taking this, which is called a string literal. Stuff between double quotes is a string literal. We're saying send that string literal to the output stream. And the default output stream is the command prompt window. So we can just do it this way and it will print this to the command prompt window. Couple of things. We could, up here, we could say using namespace standard, and then we could just do this and it will also work fine. I'll show you. Like so. The reason people use namespaces is in case 2 different namespaces have something that has the same name, and we use the namespace to disambiguate which one we're talking about. I'm going to always just use this notation. But know that there is a shortcut for doing it a different way. There's one more thing I want to show you. This /n here is called an escape sequence, and it prints a new line. If we didn't have this, and I ran, you can see that this message that says we exited with code 0 appears smashed up against what we output, and I don't like that. So I like the new line instead. You may have noticed, or you may not have noticed, I'm just Control F5ing without building, because if I've made changes to my code, Visual Studio will automatically rebuild when I run. And there's that space I want. Another way that you will regularly see C++ programmers moving to the next line in the output is doing something like this. So this is the end line that we're also sending into the output stream after this. And I'll run it again to show you that. And it works exactly the same way. Now I said it works exactly the same way. That's not strictly true under the covers. So I am going to use this instead, which is in fact a little more efficient than using standard end line. And that's it. That's our first C++ console app using Visual Studio. To recap, You saw in this lecture how to build a console app in Visual Studio, and I'll remind you that you can use either Visual Studio on Windows or Xcode on a Mac to do all your C++ development in this course. I'll provide all the course materials, lecture code, exercises, programming assignments, everything, both for Visual Studio and for Xcode, so it doesn't matter which one you end up using in the course. Last time, we saw how to create a C++ console app in Visual Studio. In this lecture, you'll see how to create a C++ console app in Xcode. I've opened up Xcode, and I'm going to create a new Xcode project. And we're going to build a command line tool. And the product name will be First Console App. And now I pick where I want to put it, and I'll pick that, and then we'll come back. And if I select main.cpp on the left, I get my main C++ file. I'm going to modify this top part with the standard copyright notice that I'm going to use on the code throughout the course. And I like to have my open curly brace on the following line, not at the end of the line. And I want to include those documentation comments that I put in JavaDoc format so I can use Doxygen to generate documentation. There's a reading about doing Doxygen comments in Xcode, and I'll type doxy and then hit enter. And that's because I created a code snippet in Xcode as that reading describes, so that it will fill this in when I type doxy and hit enter. I'll just say that I'm going to print something. And I actually have two parameters here. I have argc, command line arguments, count. And I have another parameter that is argv, and that's the command line arguments. And then finally, I return the exit status for the main function. The code I'm inserting is the code that it gave me by default. Just says hello world. And it returns 0 as the exit status, so if it gets to that line of code, the main function executed successfully. We need to do two things. We need to build our code and we need to run our code. And we can do both at once. If we just say go ahead and run, it will build it first and then run it. But I'll show you both steps here. So to build, you can either use Command B, or you can say product build, and then you wait patiently while it builds, and you get a build succeeded, hopefully. And to run it, you can either use Command R or product run. And as you can see, it builds it again, and now it's running it, or it's getting ready to run it, because we need to allow access. I put this in my documents folder, so I'm going to allow that access. And as you can see down here on the bottom right, it says hello world, and the program exited with exit code 0. And that's how you go about creating a new Xcode project and writing a simple console app in Xcode. To recap, in this lecture you learned how to create a C++ console app in Xcode, and as a reminder, even though almost all the videos are recorded in Visual Studio, the C++ ideas are the same. In this lecture, we'll go through the installation process for Unreal Engine. And even though there are minor differences between a Windows installation and a Mac installation, you should be able to follow the process that I'm showing you here to get Unreal installed on a Mac. Just as for installing Visual Studio or Xcode, the best way to do this is just to follow the instructions in the setting up your development environment reading, but I'll show you some of the steps anyway here. So you go to unrealengine.com, you can click Get Started Now. You want the publishing license, which is free for you to use until you start making $1 million. And then you need to start paying a royalty. But that's a long way away for those of us who are working through this specialization. So you just go down here to download now, and you click it, and you'll end up downloading an Epic Games Launcher installer. You should go to that installer and double click it to get it installed. And as the reading says, when I did the first installation, I got this error message, and it's great if you don't, but if you do, you should follow the instructions in this paragraph to resolve that problem. Now that you have the Epic Games Launcher installed, go ahead and launch the Epic Games Launcher, start up that program, and you'll get something like this. You probably won't have any Launch an Unreal Engine over here yet because you don't have any installed. What you'll do is you'll click Unreal Engine on the left, and up here on the top it will say Install Unreal Engine. And you should do that, and that will get Unreal Engine installed for you. Later on, if you ever decide to add additional versions of the engine, as you can see, I have the most recent at the time of this recording engine and an older version, you'll just click this plus and it will give you options, but it won't include the ones you already have installed. So that's how you get Unreal Engine installed. To recap, in this lecture you saw how to install Unreal Engine, so now you should go install Unreal Engine. In this lecture, you'll learn how to write a C++ script in Unreal. So let's get to it. As you can see, I've launched the Unreal editor, and I don't want to open any of these existing projects. I want to do a new one. So I'm going to select Games here and then click the green Next button. I'm going to do a blank template, and be sure to change over here in the upper left hand option, change from Blueprint to C++. We want to build a project that we use C++ code in, not blueprints. Blueprints is the visual scripting language that you can build lots of really cool Unreal Engine games with, but the courses in this specialization are also teaching you C++, so we want our projects to be C++ projects. Sometimes when you first start using Unreal Engine, you get some starter content over here, and you should click the icon like this and make sure you're starting with no starter content. Down at the bottom, you can pick where you're going to put the project you're about to create, and you can name it. So I'll call it First Unreal Script, and I'll create the project. And now you just have to wait until the editor actually opens. And here we are in the editor. The first thing we're going to do is we're going to save our map. This is the map right here that we're looking at in the viewport. You can think of it as a level in your game. I'm going to click the Content Browser tab down here on the lower left, and here in the Content Browser panel, I'm going to right click and I'm going to create a new folder. Now we're using good folder naming conventions for Unreal, and that means that this top level folder in content should have the same name as my project, which is First Unreal Script. Then within this folder, which I'll double click to open, I'll right click and I'll create another folder called Maps. And then finally, I'll either Control S or I'll save current, and I'll navigate to my Maps folder, and then I'll save my map. I'll call mine Map 0 and I'll save it. The next thing that's really useful to do to help people who might be opening this project, like when I save it and you open it up, it would be nice if Map 0 actually automatically opened up in the editor when you opened up the project. So I'm going to say Edit, Project Settings, and on the left, I'll click Maps and Modes, and over here in the Default Maps area, I'm going to change both of these to Map 0. And then I can just close the Project Settings panel. And that way, when somebody actually opens up this project, it will open up to this map. The next thing I want to do is I want to add a C++ script that's going to print a message. So I can go up here on the top menu and say File, New C++ Class. And we're going to talk about classes and objects soon, but not quite yet. So just know that we need to pick New C++ Class, and I need to pick Actor as the parent class, and click Next. I'm going to call it Print Message. I'm going to make it save in the default folder, and I'll say Create the class. Now we'll add a template C++ class to the project for me, just like we got a template C++ class when we told Visual Studio to create a console app for us. Once that's done, we want to actually open up that code that was just generated for us. If Visual Studio is already open for you, you can Alt-Tab over to it and say Reload All. And as you can see, I forgot to fill out my copyright notice on the description page of project settings, so I'll add that and we'll come back. So, how do we make this script that Unreal generated for us print a message in the output log? I'll show you the output log soon, but we want to print a message to the output log. There are a few things that we do. First, here in this function, which is actually called the constructor for this class, this is setting a particular value to true, which basically says for objects of this class, you should call this tick function every frame of the game. But we don't need that. We're just going to print a message once, so we're going to set this to false. We won't call the tick function on this object every frame because we're just going to print the message once. The place that we're going to print the message is down here in the begin play function, which is called when the game starts or when this object is spawned in the game. So here's where we'll do it, and here's what we do. We'll use something called UE log, Unreal Engine log, which is actually something called a macro, but we can just treat it like a function. We can act like we're calling a function here. We do, however, need to provide 3 arguments to this macro. We need to provide the name of a log that we want to log to, and we'll just use log temp, which is just one of the built-in logs that Unreal Engine gives us. We'll give it a verbosity level, which we'll say is warning. So that will just really affect what color it shows up as in the log. And finally, we'll say, what do we want you to print in the log? We'll use another macro called text because we're going to say we want you to print this text in that log. And then we provide a string literal just like we provided when we did our hello world message. Here we'll be a little less supportive and we'll say hello noob instead, but that's what we'll provide as our log message. Now it's super important to know that if we don't compile over here, then when we get back over in the editor, this code will not have any effect. It will pretend we didn't type anything. So the pattern of behavior you should have every time is compile the code as soon as you've typed it. And when you see that the build has succeeded, we're good to go back to the editor. You don't actually have to compile the code as soon as you've typed it, but you always want to make sure you compile before you return to the editor. Okay, back here in the editor, we still haven't added our script to the map. So because it's not living in the map, when we run the game, the behavior we included in that script won't get executed as the game runs. So we need to add the script to the map. The way we do that is we click on this folder icon just to the left of content here in the content browser panel, and you can pick C++ classes and you can expand this, and it has a built-in folder called First Unreal Script. So we'll select that and we see here's our print message script that we just wrote. We'll drag it into the map and drop it there. And over here in the world outliner, we can see that we now have a print message script in our map. If I click the output log tab here, I'm going to be able to see the logged output when I run my game. If you're not seeing the output log, you can just say Window, Developer Tools, Output Log, and if you select that, you can drag it and drop it over here and it'll be there until you decide to remove it. So I could right click this tab and close the tab, but I'm not going to do that because I want it. So now I want to run my game. I can click the play button, or I can Alt P and it will play the game, and you can see down here in the output log, you can see that we got our hello noob message. And to stop running the game, we just hit escape or click the stop button up here. And now we're back to our map. We have some changes to save, right? We added our script into the map. And by the way, once we did that, that script is called an actor. It's in the map as an actor. So we'll save current. You can Control S or click that button. And now we're all done saving this first Unreal Script project. To recap, you can write your C++ scripts in Unreal using either Visual Studio or Xcode. And an important thing to remember is you need to have your script in the map for your script to actually run. Last time, you learned how to write an Unreal script in Visual Studio. And even if you're using Xcode in the course, you should go watch that video anyway because it talks about how scripts work in Unreal. Now, let's go write a C++ script in Unreal using Xcode. As you can see, I've created a new first Unreal script project, and I did all the map folder stuff and so on, and I created a new C++ class called printMessage. And if I double click a script, it gives us the .h header file and the .cpp C++ file. And I don't actually want either of these, so instead I'm going to say File, Open Xcode, because I'd prefer having the full Xcode environment. I can now navigate over here on the left into Games, First Unreal Script, so this is my project. Code gets saved in the source folder, in the First Unreal Script folder, and here's my print message C++ file. As usual, I'll change this to false, And down here, I'll print a message. And I'll do that in the usual way. And I'll even print the same message I used in the previous lecture. Now I can build using Command B, and you don't have to worry about those error messages that are showing up. You just need to wait patiently until you get the build succeeded message. Now we can come back to the Unreal editor, and we'll add our script into the map. And finally, we'll Alt-P to run the game. And if we look at the output log, we see it says "Hello Noob," just as we expected. So obviously, doing your first Unreal script with Xcode is remarkably similar to doing your first Unreal script with Visual Studio, except that we need to explicitly open Xcode to get the full environment, rather than just double-clicking the script. To recap, in this lecture you learned how to write an Unreal script using Xcode. What will you learn about in this lesson? You'll learn how bits are used to represent information. You'll learn what data types are. You'll learn about some of the C++ data types, and you'll learn the difference between a variable and a constant. In this lecture, we'll talk about how we can encode things in a computer using bits, and we'll also talk about how many bits do we need to encode a particular number of unique things. So everything in the computer is in binary. And what's binary? Binary is base 2. Why do we care about that? Because we can use ones and zeros to represent anything in a computer. We can represent numbers, we can represent characters, we can represent pictures, we can represent sound, we can represent anything with zeros and ones. That raises the question though, first, how do we do it? And second, how many bits do we need to represent a particular number of things? And that requires me to tell you a Christmas story. So my family, several years ago, were trying to figure out who gets to open the first present. That's part of our tradition of Christmas. And we wanted to do it with coin flips. So we were thinking about how many coin flips did we have to do to pick out of 4 people. One of my children was not there yet. Out of 4 people, how many coin flips did we have to do to figure out who opened the first present? Now, me and my son, a computer scientist, came up with one answer, and my wife and daughter came up with a different answer. So you should pause the video for a minute and think about how many coin flips you would need to do to actually pick from 4 people the person who gets to open the first present. Once you've figured that out, go ahead and unpause the video and I'll talk through the 2 different solutions that we came up with that Christmas morning. Okay, one of the common solutions that we might use would be to have a tournament. This is sort of a standard structure that you see in, playoffs in hockey or some other inferior sport to hockey. So you have these ladders, if you will, and you have A plays B and somebody wins, and that would be 1 coin flip. C plays D and somebody wins, and that would be another coin flip. And finally, the winner of those first 2 games, if you will, play with 1 more coin flip. So you can do that with 3 coin flips. And that's a very natural, normal way to come up with a solution to this problem. However, I'm going to be very dramatic here. We can use the power of binary, and we can actually encode A, B, C, and D, each of those 4 different things, by using 2 bits. And so if we encode A as 0, 0 and B as 0, 1 and so on, we can actually determine who wins with only 2 coin flips. And I will freely admit that we spent far more time talking about this than it would have taken to do a third coin flip, but that's kind of how my family works. But the next question is, how many bits do we need to represent a certain number of unique things? This was a really interesting conversation because it was how we go about encoding stuff in the computer. But if we're going to encode stuff, how many bits do we need to encode stuff? So let's say we have 1 bit. We can encode 2 unique values. We can have 0 or we can have 1. So 2 unique values. What if we have 2 bits? Well, that was the example we just did. We can encode 4 different things. And if we have 3 bits, we have 8 different possible encodings. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. And let me fix my glasses. I was counting up in binary, but those are the 8 different combinations we can get with 3 bits. Now, some of you may have already realized that if we have 1 bit, we can represent 2 things, and 2 to the power of 1 is 2. If we have 2 bits, we can represent 4 things, and 2 to the power of 2 is 4. And if we have 3 bits, we can represent 8 things, and 2 to the power of 3 is 8. So now I'll show you a slide with the biggest font you'll see throughout the course. The relationship is 2 to the b equal n. So if we know how many bits we have, we just raise 2 to the power of b, and that tells us how many unique combinations of those bits we get, which tells us how many unique things we can represent. If you know how many things you want to represent, you can use the inverse relationship, right? We can take the log base 2 of n to calculate b, but I'll tell you, I personally never do that, right? I sort of go through the process, well, I'm trying to represent 12 things. How do I figure that out? Is 3 bits enough? No, 2 to the 3rd is 8. Is 4 bits enough? Sure, 2 to the 4th is 16. We can never use partial bits. You can't say, oh, I need 3.7 bits. It's not how it works. You only get whole bits. But I don't usually use the log base 2n equation. I usually use 2 to the b equal n and work my way into however many bits I need. So that's it for this lecture. The 2 powerful ideas are we can encode anything with 0s and 1s in a computer, and we have to because computers use binary, and we have this relationship, this 2 to the b equal n, that will tell us how many bits do we need to encode n unique things. Recall that last time we discussed the fact that everything that's represented in a computer is represented in binary. That gives us a problem though. So what does 01, 0000001 mean? Well, it can mean a lot of different things. It could mean the number 65 if we're talking about the binary number system. It could mean capital A if we're talking about ASCII representations of characters. It could mean the red component of a pixel if we have 8 bits for the red component of a pixel. So a sequence of 1s and 0s can represent a whole bunch of different things. How do we know which thing this sequence of 1s and 0s actually represents? A data type tells us how to interpret the bits at a particular location. A data type also will tell us the valid operations that we can perform on those bits in that memory location. For example, it doesn't make any sense at all to take a character and add true or false to it. Those are not compatible data types for addition. Okay, so here is a conceptual representation of memory. The numbers on the left are the addresses of locations in memory, and the contents of the boxes on the right are the strings of ones and zeros that are in those locations. When we program, we're actually interacting with memory. We're putting stuff into memory and we're taking stuff out of memory, and it would be nice if we could get a memory location that we could refer to by name instead of by memory address, because memory addresses in our programs are really horrible to look at. So we want to refer to this memory location by a particular name, and we also want to be able to tell how should we interpret the ones and zeros at that memory location. There are multiple ways that we can actually get a named location in memory that is interpreted properly. And those two ways are variables and constants. When we declare a variable, we provide the data type, so that tells us how to interpret those ones and zeros, and we provide a variable name, and that is the name that we'll use to refer to that memory location instead of using the actual memory address. Optionally, for variables, when we declare one, we can also provide an initial value for that variable. We can set the zeros and ones in that memory location to a particular value. That's called initializing the variable. We can also declare a constant. And a constant, we provide the data type, we provide the keyword const, we provide the data type, we provide the constant name, and we provide the value. And the value is not optional for a constant. The value has to be provided when we declare the constant. The difference between variables and constants is variables can be changed by our program as our program executes, and constants can't. They have to be, wait for it, constant as our code runs. To recap, in this lecture, we learned that a data type tells us how to interpret the bits at a particular memory location and tells us the valid operations for the bits contained in that memory location. And we learned that we can use variables and constants to get named locations in memory with data types that control how their contents are interpreted and the operations we can do with them. In this lecture, you'll learn about some of the data types we use in C++ to represent integers. So what's an integer? An integer is a whole number. It's a number with no decimal point, no fractional part, like 0 or 42 or -11. Some of the common data types we use in C++ to represent integers are short, int, and long. Each of those data types has a different number of bits used to represent that data type. And what does that tell us? Well, we know 2 to the b equal n. So it tells us if we have more bits, we have more whole numbers that we can represent. We are typically going to be using int through the courses in this specialization, but it's important that you know that there are other options. The operations, because remember that's the other thing that data type tells us, the operations on these data types are mostly as you'd expect, except for division. And I think it's a good time for us to go take a look at some code to see how all that works. I've started Visual Studio and I'll create a new project. And again, I'll use the Windows Desktop Wizard, which we'll always use as we're building C++ console apps. I will call this integer data types. And I'll say OK here. And here's my template code again. I'll just type in my copyright notice and then we'll come back. Okay, this time I'm not printing out this message. What I'm going to do is I'm going to have a total seconds played as an integer. And so the first thing I do when I'm declaring a variable is I put its data type. And since this is an integer, I'm going to use int. The next thing I put is the name of the variable. And there are a number of different naming conventions people use when they name variables. I'm going to show you several of those, ending with the one that we'll use throughout the courses in the specialization. So I'm going to have a total seconds played here. One thing people use is something called snake case, like that. So it's called snake case because the characters are higher than the underscores, so it looks like the curves of a snake. We're not going to use that. Another style people use is this, which is called camel case, because it has capital letters that you can envision as humps on a camel's back. We're going to use this style, which is called Pascal case, because in ancient times there was a programming language called Pascal, and this was the standard way we would name variables in Pascal. Even more importantly for us, the Unreal Engine coding standards say that people who are programming in the actual engine code base name variables using this capitalization scheme. So we are going to use Pascal case for our variables. You will look at C++ code on the web and elsewhere, and you'll see all kinds of different naming conventions for variables. And the bottom line is, if you're doing personal projects, you use whatever coding standard you want. If you're working at a company, you use whatever coding standard the company uses. And so we're going to use the Unreal Engine coding standards. The other thing I want to do, though, is I want to initialize total seconds played to be 100. I want to use 100. One of the common ways you'll see this done is with something called an assignment statement. So we can say equal 100 like this, and it will give the total seconds played variable a value of 100. And this is the syntax that's used across many, many languages. We're going to use a different syntax here that is only available, to the best of my knowledge, in C++. We're going to use something called a braced initializer. And that spacing happened. Visual Studio fixed that for us. This is another way to actually initialize a variable. The reason that I want to use a braced initializer here, I decided personally I wanted to use a braced initializer here, is because if I make a mistake here, I know this is an integer, but if I make a mistake and I type 100.3 and I try to compile, when I do that, I actually get an error message that I cannot convert from double to int, because it's what's called a narrowing conversion. I am converting a bigger data type into a smaller data type, and because 2 to the b equal n, we know that we will or could lose precision by doing that. So this is an error. It's not allowed. I'm going to keep the zooming in turned on for now. If I do this, if I use the assignment statement and I F6, it builds fine. It doesn't complain at all to me that there was a problem. If I come over to the error list, I can click this warning box that tells me that you could lose data doing this, but this is a warning, not an error. And this is a bad enough issue that we actually would prefer our code doesn't compile at all. So I'll turn off the magnifier, And I'll change this back to a braced initializer. And I'll get rid of the 0.3 as well. So sometimes this helps us and sometimes we don't care, but when it helps us by giving us a compilation error, we can then fix our code rather than just potentially ignoring warnings that we say, well, whatever, it compiled, let's move forward. Okay, what we're going to actually do is we're going to calculate minutes and seconds played. And then we're going to print the results. So, calculating minutes played, we will use another int. All of our results will be ints here. So we'll say minutes played. And we can use the fact that division on integers does that quotient and remainder division to say this is total seconds played. And you can see, by the way, that this IntelliSense is popping up, and I can just hit tab and it will fill that all in for me. So it's total seconds played divided by 60. And let's print those results to see them. So remember standard, cout. We'll print a label to say what number we're actually outputting. And I will say, we typically will label our output in console apps. When you're writing code to submit to the automated grader, you won't be labeling your outputs. You'll just be printing out numbers. And that way the automated grader can just compare numbers. People who decide to have different labels for their output make it really difficult for the auto grader to say, oh, that's correct, it's just a different label. So when we write code for the auto grader, we won't label our output, but in our typical console app, we will. Okay, so I've sent that minutes played : space string literal to the output stream. Now I want to send minutes played, the value of the variable, to the output stream. And then I want my new line character. So I'll compile to show that this compiles fine. And I'll show you over in the error list that we are warning free. We have 0 warnings. And I'll run the code. And you can see that minutes played is 1, just as we would expect. So now we can calculate seconds played. And that's total seconds played. And I'm getting ready to type 60 again, but I'm uncomfortable doing that because 60 is what's called a magic number. And although it's easy to tell here what we mean by 60, it would be much better for readability of our code and for maintainability of our code to declare a constant for the number of seconds per minute, because that's what this 60 means. So let's come back up here. And this constant can go anywhere. It could go right here after this comment. It could go after the variable. It's just personal preference. I declare a constant by putting the keyword const. This one's also going to be an int minutes per second. And I can use braced initializers for constants as well. But now I can use the constant in both these places, and it makes it more readable. It makes it clear what we're doing. I will say that that may not feel super compelling to you at this point, but if you thought of this constant as something like damage per hit, if we use damage per hit throughout our code and say it's 10, if we decide to change damage per hit to 5 instead, all we have to do is change the value of the constant, and it works everywhere throughout our code. If we don't do that, we have to look at every 10 that we can find in our code and think about whether that 10 means damage per hit or seconds for cooldown or score per destroyed teddy bear or whatever, and only change the 10s that mean damage per hit to 5. And so using constants is a great way to sort of consolidate that number in one place and make our code readable and make it so that if we decide to change that number, we can easily do so. I know we're not going to change the minutes per second, but that's the big idea behind using constants, so you might as well start doing that now. Of course, we're going to print out seconds played as well. And when I control F5, you see I made a mistake. It is certainly true that minutes played is 1, but seconds played is not 1. Part of the moral of this story is you should know the answer before you run your code to make sure it runs properly. Of course, what I wanted to use here instead of divide was percent to get the remainder. So when I control F5, I get 1 minute played, 40 seconds played, which is the correct answer. And that's our example for using integer data types. You can see that Visual Studio is somehow getting confused up here with these red squigglies around our comment. It's okay, don't worry about that. Typically, red squigglies mean you have a mistake somewhere, but this compiles fine. It's really strange because I can make those red squigglies go away by doing this, using the assignment statement rather than a braced initializer for my constant. And it runs perfectly fine. And it will even work fine with no squigglies if I do a braced initializer here. It's just that it sometimes gets confused and puts those red squigglies. So let's not worry about those. As you can see, they're not there right now. The big important thing is that when we compile, we get output that says build succeeded or up to date, which means it didn't really change anything. Of course, you would have realized when I was declaring my constant as minutes per second that what I actually meant was seconds per minute. And I put a banner in the video there, but we can easily fix this. And this is something you should do as a programmer. We shouldn't just leave it this way because it's horribly misleading to have a constant called minutes per second that actually means seconds per minute. Here's how we can do it. We can right click minutes per second, and the second option is rename, and I can just type seconds per minute, and I can preview it if I want and say apply, and it changes all the occurrences of minutes per second to seconds per minute instead. So when I run my code now, it works exactly the same as it did before, but we have a constant that is declared to be an appropriate name, and that's what we should do as good programmers. We have a few more things to talk about before we're done with this lecture. So let's say you have an int variable and it has a value of 1, and you add 1 to it. What do you get? Pause the video, think about it, and then come back. The answer is 2. Isn't this great? You're taking a college level class and 1 plus 1 is 2. That's not the big idea. Here's the big idea. Say you have an int variable that has a value of 2,147,483,647, and you add 1 to it. What do you get? You actually get negative 2,147,483,648. And why does that happen? Well, I've added a reading you can read that really explains in agonizing detail why these integer variables wrap around. But this is because 2 to the b equal n. And for ints, where we have both negative numbers and positive numbers, if we're at the maximum positive number and we add 1 to it, we wrap around. And it's because 2 to the b equal n. So, if we only want to store positive numbers, this does not solve that 2 to the b equal n problem, but if we want to only have positive numbers, we can use unsigned integer data types in C++ instead. So we only get positive numbers. What does that buy us? It gives us twice as many positive numbers as we have if we have both positive and negative. We don't have to save any bits for negative numbers. We still have the wrapping problem. If we have the max positive number and we add 1 to it, we'll come back to 0. But it gives us more positive numbers. And if we're using numbers that we know will never be negative, it's reasonable to use the unsigned data types. And those are unsigned short, unsigned int, and unsigned long. And there are some other C++ integer data types that we haven't talked about and we won't really worry about. So to recap, in this lecture, you learned about a number of data types we can use in C++ to represent integers. And I said we were recapping, but I have to say that you might think that that wrapping thing that I talked about is just like a geeky academic thing and doesn't matter in practice. But I will say that in Grand Theft Auto 5, Rockstar used an int to represent how much money people had earned. And somebody, because you will learn that players do things you never expect them to do, somebody got really, really rich, right? And he had approximately $2,147,483,647, and then he earned more. And suddenly he was wildly bankrupt. And it's because ints wrap. So this isn't just of academic interest. That 2 to the b equal n thing really matters when we're deciding the data types for our variables. Okay, now I'll call this the end of this lecture. In this lecture, we'll talk about a number of the data types we can use in C++ to represent floating point numbers. And floating point numbers are numbers with a decimal point, right? They have a fractional part. Before we talk about specific C++ data types, we should talk about a big problem that we have, because numbers in the real world, particularly numbers that we call real numbers, those numbers that have a decimal point, have an infinite number of values. So we know that 2 to the b equal n. So when we try to translate or represent those infinite numbers in what's called the discrete domain using bits, we can't do it unless we have an infinite number of bits, because the only way to represent an infinite number of unique things is with an infinite number of bits. What we do is we decide that we are going to represent a range of real numbers with the same sequence of bits in the computer. And when we do that, we lose some precision, right? We've got sort of rounding. We're rounding every single one of these real numbers to a particular floating point number in the computer. In general, if we use enough bits for whatever application we're doing, that works out to be okay. But it's important for you to understand the difference between real numbers in the continuous domain and floating point numbers in the discrete domain inside our computer. Okay, so for floating point numbers, there are a number of data types that we regularly use. They're float, double, and long double. And floats are what we will typically use throughout the courses in this specialization. They each have a different number of bits allocated to them, and as we know, that means that the data types with more bits can represent a wider range of numbers. The operations on these floating point data types are pretty much as you'd expect. So let's actually go take a look at some code that uses floating point data types. I've already created my Visual Studio project and I called it floating point data types, and I've added my copyright notice and my Javadoc comment above the main function. So here's what we're going to do in this code. We're going to calculate and print points per second. And I know some of you may be like, well, no, it should be DPS, damage per second. But let's say I played an action game and I earned a score and I played for a certain number of seconds, and now I want to calculate and print the average. So I need a variable called score. That's whatever score I happened to score during that gameplay session. So let's say that score is 1360. And scores are typically integers, so I'm going to make this an integer. And let's say that I kept track of the total seconds played as an integer as well, just as we did in our integer example. So int total seconds played. And let's say that was 10,000 seconds. That's not too bad. And now I want to calculate and print my points per second. Let's start by doing it a naive but feels correct way to do that calculation. I know that I want to put this into a float because I'm going to divide score by total seconds played. And so I know that my numerator is going to be smaller than my denominator. So my points per second is going to be some decimal number less than 1. So I'll say here points per second. And I know I'm making a mistake here, but I'm going to do it anyway, is score divided by total seconds played. And then I'll print that out in the typical way with a label because I'm not submitting this to the auto grader. And I don't think I want to say pinte, I think I want to say points per second. And I'll send the value of the variable to the output stream as well, and my Boolean character. But then when I run it, I end up with 0 as my points per second. And I end up with my 0 because here I'm dividing an integer by an integer. So this division does integer division, which, as we know, gives us the quotient. And if the numerator is smaller than the denominator, the quotient is 0. Now you could say, well, I know how to solve this. I'll just make score a float. But that doesn't make sense. If you think about this, score is a whole number. We know that from our game. So changing the data type of score to be a float just to make it all work is not intuitive based on how the game actually would play. So we don't want to do that. Same argument for total seconds played. I said we stored that or kept track of that as a whole number. So when you declare variables, they should always be the correct data type, not an incorrect data type just to try to trick the compiler to do what you want it to do. There's a better way to solve this problem. And the better way to solve this problem is to make one of these, or both, but one will be sufficient, be treated as a float. And the way I'm going to do that is I'm going to do something called a typecast. So I'm going to say treat score as a float just for this calculation. This is a temporary thing. It doesn't change the underlying data type of score. Score is still an int. It just says for this calculation, treat score as a float. As soon as we do that, this division becomes floating point division. And that's just what we want because we have a fractional part in our division result. So if I control F5 now, you can see points per second is 0.136. And hopefully you can see that that is the correct answer based on score and total seconds played. So the important lessons from this short example are we always want to declare variables to be of the correct data type. We don't want to try to trick the compiler. We just use the right data type. And we want to typecast, if we need to force the math to work right. I will say before we leave the code that you might be tempted to do this. You might say, well, if typecasting score is good, then typecasting the whole result must be even better. But that's not true. If I control F5, you'll see points per second is back to 0. Because what happens is this part does integer division, so you get 0, and then you say treat that 0 as a float, but sort of who cares, right? So the other moral of the story here is that when you do typecasting, you should typecast as close to the place that you need to typecast as you can. Instead of saying, oh, I'll just typecast the whole result. That doesn't work in this case. We need to typecast one or both of these variables. And it's your choice. We could have typecast this to float instead. We could have typecast both of them to float. But doing just score makes the division be floating point division, which is just what we need in this particular example. To recap, in this lecture, you learned the difference between the continuous and the discrete domains, and you also learned about some of the floating point data types we can use in C++. In this lecture, we're going to explore a little more deeply how to read documentation. And I know no one ever says, I want to develop games so I can read documentation, but this is really a critical skill for programmers. Throughout your programming life, you'll spend time reading C++ documentation or Unreal Engine documentation, maybe not even through your programming life, through the courses in these specializations, but you have to be able to do it for code that other people have provided to you. Watching me do it is not going to help you learn how to do it. You're just going to have to practice and practice and practice. But you're going to have to do it to be able to become a good programmer in a particular domain. Let's go solve a small problem that requires us to get some practice reading documentation. Here is our template console app with the copyright notice added and the comment added above our main function, and the comment that says what we're going to do in this particular chunk of code. And what we're going to do is we're going to calculate and print the cosine of 45 degrees. So we'll start by declaring a variable that holds the angle. And I have a choice of data type here, right? I can do int if I want to do whole numbers for degrees. I can do float if I want to do floating point numbers for degrees. So I think I'll make this a float. And I'll call it angle. And I'll initialize it to 45. So now I have an angle in 45 degrees. And I need to figure out how to calculate and print the cosine. Of course, the first step in that is to calculate the cosine, and this is where reading documentation helps us. So if you're using Visual Studio and you've installed local help, then you can just say help, view help. And it's reasonable to guess that cosine, the standard abbreviation for cosine, will be something we can use. So if we search on cosine, we'll just click that first hit, and we discover that there are a number of versions of cosine. So here are those 3 versions of getting a cosine that we could use. We have a cosine function that takes a double as an argument. It's a parameter on this side, but it's an argument when we call it. and it returns a double. We have cosine f that takes a float and returns a float. And then we have cosine L, which takes a long double and returns a long double. In all of these, for the argument, we could pass in an int, for example, and it would get promoted to the appropriate parameter type when we call the function. So we don't have to worry that we can only explicitly pass a double to cosine here, for example. We could pass a float, we could pass an int, we could pass any of the smaller data types, and they get promoted to a double. Let's use this one because we're going to try to use float pretty consistently throughout our Unreal Engine games, so we'll try to use floats here in our console apps as well. So you've sort of read the documentation as fast as you can because you didn't go into game development to read documentation. So you read this parameter x and you say it's the angle and you say, great, I know what to pass in. You stop reading right there and you leap back into your code. If you don't have Visual Studio Local Help installed or you're working in Xcode, the C++ reference webpage is a good place to go to find out information about C++ code. Think of this as the C++ documentation that's authoritative and reasonable and so on. So if we go up here in the upper right hand corner and do that same search on cos and hit enter, we find this, which also gives us similar documentation, right? We have this one, we have the double one, we have the long double one, and there are some other versions listed as well, but essentially we're looking at, approximately anyway, the same documentation. And again, you'd say, okay, the parameter arg is a value representing an angle, and you're excited to get back to work, so you get back to work. I'm going to put the cosine into a variable before I print it out. That's of course not required. We could just print it out directly, but we're still practicing declaring variables and assigning values to them and so on. So let's do that here as well. So I'll call this one cosine, and I'll say equal to cos f of my angle. And I'll print it out. With a label because we're not submitting this to an automated grader. So when we run it, it says that's the cosine of 45 degrees, and we're all excited. We say, hey, that's great. We got a number. It must be right. It's not right. It's not the correct cosine of 45 degrees. And that reminds us again that when we run our code to test it, we have to know what the right answer is to be able to tell if we're getting the right answer. And we're not. So now our issue is, what's going wrong? And your first instinct, as you look at this code, is fairly straightforward. It seems like it should work. You say, I must be doing something wrong. I better go back and look at the documentation again. When you do, you read this entire sentence and it says angle in radians. Or you look at this documentation and you see it says angle in radians. So now we come back here and we realize that the problem is our angle is in degrees and we're calling the cos f function as though the angle was in radians. So let's convert angle to radians. So we can take angle. On the left-hand side of this assignment statement, we're giving angle a new value, and we can say angle times something. So you have to know how to convert degrees to radians, and it turns out that 360 degrees is equivalent to 2 pi radians. So 180 degrees is equivalent to pi radians. So if we take degrees and we multiply by pi over 180, we will have converted to radians instead of degrees. I'll start by doing it the way you shouldn't do it. 3.1415 float divided by 180. And I'll explain why we shouldn't do it that way in just a moment, but I'll run the code. And we get 0.707 and change. And it is the cosine of 45 degrees, at least to 3 decimal places. But we shouldn't do this piece. We should try to find out if there's a constant that's available to us that represents pi. Because you have to imagine that people using C++ for computation must use pi more than once. So somebody somewhere should have declared a constant for it. Let's go see if we can find it. In the Microsoft Help Viewer, we can just search for pi, and that doesn't help us much. Let's go to the C++ reference and search for pi, and none of those things are helpful. And at this point, you might say, well, I'm not getting anything that helps me. I should do something else. And the something else that you can do that people regularly do is to go Google or Bing or Yahoo or whatever your favorite search engine is. You might go looking for pi in C++. So let's do that. I'll go to Google and I'll say pi in C++ and see what I can find out. And you have to search around a little bit. Sometimes you can find it down here. And this will actually be helpful to us right here. So let's follow this link. And we can scroll around a little bit. And we can see that sometimes some compilers, including all the compilers we're going to be using, declare a constant called m_pi. So we can use m_pi with a little extra work in our code. I will say that searching the internet for help in discovering things like this is a really good technique to use. You have to have your internet filter so that you recognize what seems to make sense and what doesn't make any sense at all, but this in fact makes sense. So we'll go back to our code and we'll put mpi here, just like it was talking about, but we get red squiggles, and that's disconcerting to us. Unfortunately, one of the side effects of using C++ across multiple different platforms is different platforms deal with the C++ libraries in different ways. And in Visual Studio, not in Xcode, but in Visual Studio, we need to include a #define use math defines in our code. And we can compile again at this point, and we can run again at this point, and we see that that number is slightly different from what we had before. It's more correct than the number we got previously when we just used 3.1415, because the mpi constant is to more decimal points of precision for pi than just 4 decimal points of precision. So we did a couple of things here. We read the C++ documentation directly, finding the cosine function, and particularly the cosine f function that we used here to calculate our cosine. We learned the importance of carefully reading the documentation, especially for the arguments that we provide to functions when we call them. And finally, we learned that sometimes just guessing what we're going to need and going into the documentation doesn't help us. So we have to Google some reasonable search terms and then filter through the results trying to find what we need. And while that might feel frustrating, it is also a natural part of programming. So reading documentation and searching for answers that aren't immediately obvious in the documentation are both important skills for you to develop. In this lecture, you got some more practice reading documentation. In this lecture, you'll learn how to debug in Visual Studio. And even if you're using Xcode, you should watch this lecture so you can learn a little bit more about the debugging process. Speaking of the debugging process, here's one good way to think about the steps we take when we need to debug our code. The first thing that happens is we discover that there's a bug in our code. There's a problem with player input. There's a problem with the math that we're calculating. The projectiles in our game aren't inflicting the kind of damage they should. Something tells us that something's going wrong in our code. The next thing we do is we form a hypothesis about the source of that bug. What could be causing the problem that we're observing when we run our code or play our game? Then we fire up the debugger to see if in fact our hypothesis is correct, or we may discover, oh, that was a bad guess, that's not what's causing the problem, but let's use the debugger to try to find the actual bug. And then finally, we fix the bug, so that bug is no longer in our code. Let's go see how this works in Visual Studio. This is the code that we're going to debug, and what it's supposed to do is prompt for and get an angle in degrees, convert the angle to radians, and print out the sine and cosine of the angle. When we run the code, I'll enter 45 because I know the answer for that, and we are clearly getting incorrect results here. Now we could just examine our code and try to figure out what's going on, but let's practice using the debugger. My first hypothesis could be that I'm reading in the angle incorrectly. So as I look at this code, I've declared a variable for the angle, and I've prompted for it, and I've read it in. So let's put a breakpoint here on line 20 so that when we run our code, it will stop at line 20, and we can look at the value of the angle variable. We set a breakpoint by clicking over here in this gray vertical bar on the left. So left clicking in that bar will set a breakpoint. Left clicking on a breakpoint will remove the breakpoint. So I want a breakpoint, and this is one of those times where we don't want to use Control F5 to run our code because we're actually using the debugger this time. So we want to debug start debugging, which is just F5, not Control F5. When we start debugging, the command prompt window opens up. It executed the line of code that outputs the prompt. I'll enter 45 degrees and hit enter, and then we come here and we stop. We can tell what line we're on because here we have a yellow arrow on the left that points to this line, so we've stopped at this line. And I'll turn on the magnifier for us. So here on this line of code, we can look at the value of angle by doing a variety of different things. We can hover over angle, and if we do, we can see it's 45, so we know we're reading in the angle properly. And if we go down to the bottom in the locals panel, we can also see that angle has a value of 45. So we in fact read in the angle properly. Now we're going to convert the angle to radians. And you should know that 45 degrees is pi over 4 radians. So that should be about 3/4, right? Around 0.75 after we step over this line of code. There are a number of ways we can step over a line of code in the debugger. you can go up to Debug and say Step Over, which is F10, or of course you can press F10. But when we step over it, you can see that the yellow arrow moved down to the next executable line. It doesn't stop on blank lines, it doesn't stop on comments, it goes to the very next executable line of code. But it did execute line 20 when we stepped over that line. If we look at angle now, we can see that our angle is 2,578, and that is clearly not correct, right? It should be about 0.75. So using the debugger and testing our hypothesis, and then when we discovered our hypothesis was incorrect, we were able to step over the next line of code, and that actually turned out to be our bug. So it's not that we're reading in the wrong angle, it's that we're converting the angle to radians incorrectly. And by the way, down on the bottom, you can see that the value of angle changed, and Visual Studio shows us in red that that particular value changed when we executed that line of code. I'm going to turn off the magnifier. I'm going to stop debugging, and we can stop debugging by clicking this red box near the middle top of Visual Studio. And I'll remove this breakpoint, assuming I won't need it anymore. And if I look at how I'm trying to convert degrees to radians, I have this exactly backwards. I need to multiply by pi and then divide by 180, not multiply by 180 and divide by pi. So let me just fix this. And I'll compile again. And once you think you've solved the bug, there's no need to use the debugger to test that. We can just run our code again. And if our code gets the correct answer, we fixed our bug. And if it doesn't, then we form a new hypothesis and we use the debugger again and so on. So let's go ahead and run the code. 45 degrees. And I get the correct answer for sine and cosine. To recap, in this lecture you learned about the debugging process and you learned how to debug code in Visual Studio. In this lecture, you'll learn how to debug in Xcode. And even if you are using Xcode, you should go watch the video about debugging in Visual Studio to learn more about the process we follow when we debug our code. Let's go see how to debug in Xcode. This is the same code that we just debugged in Visual Studio, except for our javadoc comment up above. So I'm going to prompt for and read in an angle, and then I'm going to convert the angle and print out the cosine and sine. I want to set a breakpoint because remember I have a hypothesis that I'm reading in angle incorrectly. So I'll just go to the left of the line where I want the breakpoint, and I will left click to place the breakpoint there. Now I can actually just run my code. I don't have to run it in a different way like in Visual Studio we start debugging versus not debugging. I can just Command R and allow access to my documents folder, and now down on the bottom right I can type 45, and then I end up here at this particular line of code. And if I hover over angle, I see it's 45. And if I look down here in the lower left, I can see it's 45. So again, I know I am reading in the angle correctly. So now I want to step over line 20. So I want to execute line 20 and move to line 23. And I can do that by either clicking Debug, Step Over, or using F6. And now if I look at angle again, we see that it's that horrible 2578, which is a huge number, not around 3/4. So I can stop debugging with this black square on the upper left. And so I'm not debugging anymore, and I don't want this breakpoint hanging around anymore. So if I right click it I can delete the breakpoint. I can't just click it to delete it. That disables it, but it doesn't delete it. So I want to totally delete it, and I'll do that. And now I'll fix my code like I did before. And I'll Command R again to rerun now that I've fixed the problem. And I'll enter 45, and I get the correct cosine and sine. So that's how we can use the debugger in Xcode for a console app. To recap, in this lecture you learned how to debug in Xcode. In this lesson, you'll learn the foundational concepts behind the object-oriented paradigm. The big idea is that we can build software as a set of interacting software entities or objects. This is a great paradigm to use for game development because our games are regularly composed of interacting entities in the game world. Think of players and NPCs, think of bullets and asteroids, you could even think of landmines and teddy bears. So what will you learn about in this lesson? You'll learn the difference between classes and objects. You'll learn that each object has state, behavior, and identity. You'll learn how to construct an object. You'll learn how to use getters and setters on an object. You'll learn to call the functions that an object exposes for us to use. And finally, you'll learn how classes and objects work in Unreal Engine. We'll start this lecture by talking about objects. And before we talk about the details, you should think of objects as software representations of tangible entities or things, ships, asteroids, projectiles, entities that we might want to include in our games. Every object has three things. Every object has state, and state is the characteristics of the object. If we're thinking of a ship, that ship has a certain amount of fuel, it has a certain velocity vector, it has a certain angle at which it's rotated. There are particular characteristics that that object has, and those characteristics are called state. Every object also has behavior. So behavior is something that we can tell an object to do. For example, we could tell our ship to rotate. And sometimes we think of it as something that we can tell an object to do to itself. So we can tell our ship to refuel itself or something like that. And when we talk about decks of cards later, we'll say the deck should shuffle itself. So those are behaviors. Those are things that the object can do. We can tell it to do, or we can tell it to do to itself. The final thing an object has is identity. And identity makes it so that we can distinguish this ship from this ship. It gives us a way to distinguish between objects. In practice, the software representation of an object lives at a memory address, so different objects are at different memory addresses. Okay, I know I've been talking about a ship, but let's talk about a playing card. What's the state of a playing card? Well, playing cards have rank, ace through king, suits, and whether or not they're flipped over or face up. So we can store the state in good object-oriented design in something like C++. We store the state in fields. And fields are really just variables that are available throughout the class, not just in a particular function like we've been using so far, or that we've generally been using so far. We don't, however, want people external to the class to be able to just access those fields directly. Instead, we provide them with things that are called getters and setters, or accessors and mutators. People use those two different pieces of terminology, and I will use those two pieces of terminology interchangeably, but they allow consumers of the class, somebody outside the object, to either access state by saying, hey, what's the rank of this card? Or by being able to set pieces of the state, which we actually won't do in our card example. The next thing is behaviors. What behaviors does a card have? Well, the most obvious one is that we can flip a card over, right? If it's face down, we can flip it over and now it's face up. And behaviors are implemented through functions. Now I will say that getters and setters are also functions, but we tend to think of them as distinct from behavior functions because they're really just designed for accessing the state of the object. It's also the case, as we can see with this example, that calling a flip over function will in fact change the state of our playing card, right? If it's currently face up and flipping it over will make it face down. So functions, sort of general behavior functions, also are likely to change the state of our object, but they're distinct from getters and setters in the way people think about it. Finally, identity. So each object that we create from the class, and I'll talk about the distinction between classes and objects before we're done, but each time we create one of these objects, which is called instantiation, that object gets a place in memory to live, and that gives it its identity. Here's a conceptual picture of our card class, our card object, the way we've been thinking about it. So at the core, that inside part, the donut hole, although it has stuff in it, is the fields that we're going to declare for this particular object. So we have a Boolean that will tell us whether or not the card is face up, and we have its rank and suit. And then we have the getters and setters spread around. We can get the rank, we can get the suit, and we can ask is face up. So for getters, and that's all we have in this particular discussion, right? If the getter returns a piece of state that's Boolean, it is general convention to say is instead of get. And that actually makes it so that when we build Boolean expressions, which we'll learn about in the next course in the specialization, as we build Boolean expressions, they'll be more readable. And finally, we have the one function that is a behavior function, the flip over function. So this is sort of a picture of a card object. There are two important ideas that go along with the object-oriented paradigm. The first is called encapsulation. So as you can see, I now have a magenta boundary around my object. Encapsulation simply means that we've put the data and the operations, those getters, setters, and functions that affect the data all in one software entity. So we've encapsulated them inside this shell to make them all together. So that's one important object-oriented idea, is encapsulation. Another really important object-oriented idea is information hiding. So now, as you can see, I have shaded all the internals of this particular object, and that's because somebody outside the object can only interface with the object through the getters, setters, and functions, and they don't know anything about how the implementation is implemented on the inside, right? They don't know if we have 3 fields or 20 fields. They don't know the code that is contained in getRank. they don't know how the flip over function is actually implemented. And this is great. This is a huge idea, because if we do good object-oriented design and we use information hiding, then say we have tons of other pieces of code that use my object. If I change the guts, but I don't change the interface, all of those things still work. And that's fantastic. For maintainability, it makes it so we don't have to worry about changing the internals, because everyone interfaces with this object through the interface, through that boundary of the object. So I told you I would tell you about the difference between classes and objects before the end of this lecture, and I've sort of been using those terms interchangeably, but there is a precise difference between them. So a class defines all the fields and the getters and setters and the functions for any object we create from the class. So you can think of this as a cookie cutter. We want to make cookies, and the class defines sort of the shape, conceptually, of the cookies. Now, cookies with behaviors might give you nightmares, but this is, just think of the metaphor as this is the cookie cutter we'll use to make cookies. So it defines the shape, the fields, getters, setters, and functions for any cookie we make. An object is actually the sort of real live instance of the class, and you can think of it as the cookies we make with the cookie cutter. So we make a number of cookies, and then the cookies can interact with the real world, and we can, well, the software world, and we can interact with them by, biting them or whatever we choose to do with our cookies. And they'll interact with each other. We throw them at each other and they'll break and all kinds of stuff. So the objects are the things that we actually put into the real world, the game world, by instantiating the class, that instantiation thing. And I will point out that each cookie holds its own state, right? We can have two ships that this one has a half a tank of fuel and this one is full, and they're going in different directions and they're rotated at different angles. Or we can have two playing cards and they have different ranks and suits. That's kind of the only way you can build a card game, right? Is if all the cards aren't the same. So when we create an object, we are giving it sort of embodiment in the game world, and it will now maintain its own state. This is actually a more common representation of a class, and this is in something called Unified Modeling Language, or UML. So at the very top we have the class name, and then we have a set of fields, and in UML we give the name of the field and then the data type. That is exactly opposite of the way we declare variables in C++, but we're going to use real UML notation when we use UML notation, and the name of the field comes first. So these are the three fields that we're including in our card class. And then at the bottom, this says methods, and I keep saying functions. I will say that people call these behavior implementations in C++ either functions or methods. Those two terms are interchangeable. I will consistently call them functions, but Visual Studio, which I use to generate this UML diagram, calls them methods. But those two words, functions and methods, mean the same thing. And then we list each of those functions that we have, the three getters, and the flip over behavior function. To recap, in this lecture, you learned some important object-oriented ideas. You learned that we have object-oriented classes that we use to create objects, and you learned that those objects are the things that we can actually have interact with each other to actually implement our game world. Last time, we learned some of the conceptual ideas behind classes and objects. In this lecture, we'll start using classes and objects in a C++ program. The first thing we need to know is, how do we construct an object? How do we use instantiation to get an instance of an object so that we can interact with that object? So that's what we'll learn how to do in this lecture. This is our starting point for this lecture. So what we're going to do in this lecture is we're going to create a deck object, which under the covers uses the deck constructor to create that object and to put it into a variable. I need to point out that all this stuff that we're using, the deck class, and there are actually other things included too, like cards and ranks and suits, those don't come automatically in C++. These are actually in a DLL, a dynamic link library, that I wrote to include this reusable code. So this is more like using a library that somebody else provided, but it's not a C++ standard library. It's code that I wrote and I integrated into this Visual Studio project as a DLL. So you can't just fire up a new console app and type deck and expect it to work, because I've done extra work in this Visual Studio project to include all the stuff we're using today from that DLL. Okay, so we want to create a deck object, and we need to understand more information about the constructor. We need to know, in particular, if the constructor requires us to provide any arguments to initialize the deck. And the way we find that out is by reading documentation. And here's the documentation for all the stuff that's in the DLL that I included in this particular project. How did I get this documentation? I did all the JavaDoc style commenting that I told you we would do in our code throughout the course, and then I used a tool called Doxygen to generate the documentation from those comments. So this is why we do documentation comments, so that we can generate documentation for users of the code or consumers of the code that we wrote. So over here on the left, I'm going to click on classes, and here's a class list, and I'll click on deck because we're trying to use the deck constructor, and I'll even zoom in so that you can see that the public member functions that we have available to us in the deck class are the constructor. The constructor is always the same name as the class. And then we have an isEmpty accessor that we'll look at next time. And then we have 4 different functions: cut, shuffle, take top card, and print, that we'll actually look at not next lesson, but the lesson afterwards. So what we care about at this point is the constructor. And I can click the constructor, and it takes me to the constructor, and it turns out that there are no arguments that I need to provide when I call the constructor. And we know that because there's nothing between these parentheses. Just looking forward, when we cut the deck, we're going to have to say where we want to cut it. So we're going to have to provide an argument when we call the cut function, and that's shown right here. And there's discussion about that particular parameter. But the constructor doesn't have any of those, so we know we can just use the constructor without providing any additional information. Back in our code, our inclination is to come here and say deck for the data type, the class name that we're trying to use, which is deck, and to name our variable, and we're going to name our variable deck. So this is okay. It's okay. The compiler can figure out that this is a variable name, but it doesn't know about deck the class yet. That's why we have red squigglies. So we regularly find that we need to pound include header files for classes we want to use. So first I'll type the pound include and then we'll talk about header files. And we'll explore this much more when we are creating our own classes about how we structure header files and CPP files. So all you need to know for now is when we're using a different class, if it's not already built into a predefined C++ library like this, we need to include the header file that in many ways defines the interface to the class. It doesn't have all the implementation details in there, but it does have information about the interface into the class. So putting the information about the class in two files, the header file and the CPP file, make it so we can distribute the header file with our DLL because people need to know how to use the class, but we keep all the implementation details inside the CPP file, which they don't get when they get the DLL. So that's information hiding. They don't get to see the implementation details. Okay, but we still have red squigglies here on line 14. And the reason is because just as if we type cout, which we've used before, we get red squigglies. But if we provide the namespace for cout, the red squigglies go away. I'm sorry, that's such technical terminology. So we know DAG from our documentation. Let's go back and take one more look. We know that DAG is actually in the console cards namespace. And I've scrolled up and you can see that up here as well. So it's in a namespace that I defined for all the classes that go in the DLL. We either need to do this which fully specifies the name of this class, or as I've shown you before, we can say using namespace console cards. And while I did say when I was talking about using the standard namespace that I didn't want to do it this way, my general rule will be that if I'm using built-in C++ namespaces, I'm going to fully specify them. If I'm using namespaces for code that I've written or sort of custom code that's not C++ standard code, I'm going to include using namespace for that particular namespace because that makes this code easier to read. I'm going to run the code even though there's nothing at all interesting to see, just to show you that we can in fact run the code. And even though it's not obvious, what happens here is we're actually calling the deck constructor, which I will tell you actually fills up the deck with 52 cards. It's not obvious from the syntax that that's what's happening, but that's what's happening. It's calling the constructor to create a deck object and put it into this deck variable. To recap, in this lecture you learned how to use a constructor to construct an object. Last time we learned how to use a constructor to get an object so that we could interact with that object. In this lecture, we'll actually interact with that object by accessing its state using a getter. And as I mentioned a couple of lectures ago, getters and setters are also called accessors and mutators, and I will use that terminology interchangeably. Okay, let's go see how to use a getter. This is the code that we ended with last time, and this time we're going to use the only accessor that the deck class exposes. So our first step is to go to the documentation, and the isEmpty function is our accessor. And I clicked it so that we could see that it gets whether or not the deck is empty. So we've got this description of what the function does. We can also see that because there's nothing between those parentheses, we don't have to provide any information. And that makes sense. We don't have to provide any information because we're just asking a question about the internal state of the deck. And the deck knows about its internal state, so we don't have to tell it anything else when we call this function. I'll show two different ways to do this. First, I'll declare a Boolean variable, and I'll call it empty status is equal to, and here's how we call any of the functions, whether they're accessors and mutators, or getters and setters, or other kinds of functions. We use the same syntax every time. We put the name of the variable, dot, and then, as you can see, IntelliSense says, well, here's what you can do once you've put the name of the variable in the dot, and isEmpty is the function we're calling, so we can just grab it like that and put the open and close parentheses, which we always need when we call a function. Even if we don't have to provide anything between them, we still need those parentheses for the compiler. And now I will print out that empty status. So when we run our code, the first thing that happens is it creates a deck object and puts it into the deck variable. Then we ask the deck, are you empty? And then we print out the results of asking the deck that question. And we get an answer that says 0, which means false. I will say that experienced C and C++ programmers can easily do the translation from 1 to true and 0 to false when we're looking at bools, but we can also make the output actually print true or false by saying standard cout standard bool alpha. So now if I run the code again, it actually says false. So you can decide to print out 1s and 0s for true and false, or you can send this bool alpha to the output stream, and then your Boolean output will be expressed as true and false. And that's certainly my preference, so I'm going to leave that in the code. The other way we can do this, though, is we can also just say, you know, I don't need a variable for empty status hanging around. I'm just trying to print that out to show that I can use the accessor correctly, so we can do this instead. We can grab that function call and put it here instead and get rid of our variable declaration completely. And now if I control F5, I get the same exact result. So I don't have to put the result of an accessor into a variable if I only need it briefly. I can just use it in my output or to do whatever else I need to do with it. But I wanted to show you both ways of doing this. In the code that I give to you, I'll add back in that other way we do it. I'll have it commented out so that you can see both ways and decide which way you want to do it. But this is probably the more common way to use an accessor for a very brief period of time and nowhere else in our program. To recap, in this lecture you learned how to access the state of an object by using a getter. In the previous two lectures, we learned how to use a constructor to create an object we could interact with, and then we interacted with that object to get access to the state of the object through a getter or an accessor. In this lecture, we'll access the behavior of the object by calling a variety of different functions. We're starting with the code that we had last time, and we're going to come down to the bottom of our code. And this says call methods, but we're really going to call functions. Some people call the functions in C++ methods. Other people call them functions. I think we'll stick with the functions terminology here. So looking at the documentation, we can see that the deck class exposes 4 different functions. And we'll go through them one by one so that we can call each of them. We'll start with the print function. And we can see we don't have to provide any information as arguments when we call the print function. And it prints the cards in the deck from top to bottom. Back in our code, all we have to do is say deck.print. Again, using this name of a variable dot name of a function, open parenthesis, close parenthesis. Let's go ahead and control F5, and we see that all the cards are face down in the deck, so it refuses to print them for us. And that makes sense, right? All the cards in the deck are face down and we can't see their values. So this is in fact printing the deck, and it's printing each of the cards in the deck. It's actually telling each of the cards in the deck to print itself, but it's not giving us really good information here, but it is giving us accurate information here. So you'll find that even though this print function has been provided as part of the deck, it's more useful if we walk through all the cards in the deck, flipping them over, and then print the deck. But I did want to show you how we can actually call the function. The next function we'll call so that we can actually take a look at how things are happening in the deck is we'll call the take top card function. And the take top card function also doesn't require any arguments, right? You can't say, give me the card that's 3 down from the top in the deck, because that is typically considered cheating. But we can take the top card. And when we take the top card, it hands something back to us. It gives us a card object from the top of the deck. It removes it from the deck, but it hands us a card. So I'll just comment out this print function because that's not useful to us at this point, but I'll leave it in the code so you can see how we did it. So we actually can go like this. We've got a card. I'll call it card 0. So there's a card class also in this DLL, and you can see over here in the headers that there's a card.h file. I'll call it card 0, and I'll say deck take top card. And now if we look at the documentation for the card class, by looking over here and seeing there's a card class as well, we can get the rank of the card, we can get the suit of the card, we can check to see if the card is face up, we can flip the card over, and we can print the card. So let's start by just saying card0.print and see what happens. When we control F5, it tells us the card is face down. So this is more evidence that when the deck was printing itself, it was just telling each card to print itself, but each card was face down, so each card was saying, hey, I'm face down. We can tell card 0 to flip itself over. And now when we run, we see that the king of spades was on the top of the deck, and we took it off the top of the deck, we flipped it over and we printed it, and we discovered that it was in fact the king of spades. Now what I'm going to do is I'm going to go back to the deck class, and I'm going to call shuffle before I take the top card. And again, we see we don't provide any information. Before I do that, let's go back to the code for a moment, because I want to show you that I can actually also do this. This will compile, this will run, and you should think about what's happening. What am I doing? I'm taking the top card off the deck and I'm just throwing it away. So if I then took the next top card off the deck and flipped it and printed it, I get the queen of spades because I took the first card off the deck and threw it away. So we actually can call functions that return objects to us, or ints or floats or anything that have a return type. We can call them without putting the result anywhere, and it's just like us saying, I don't care about the result. I'll just throw it away. And you could do this if you wanted to get rid of the top 5 cards of the deck. You could just call take top card 5 times and not put it anywhere, and then start using the deck from there. So that's valid syntax, and it's even valid in, I'm going to say, rare cases, but almost always. If a function returns a value, you should use that value somehow. Either print it out right away or store it in a variable to use later or something like that. Okay, let's go to shuffling the deck. Again, I'll comment this out. I'm trying to space this out so that if you look at the code later, it makes some sense to you about the structure of the code. So let's shuffle the deck. And while we won't have strong evidence that the deck actually got shuffled because we can't look at the ordering of the cards with all of the cards face down, we can at least make sure that we're not getting the king of spades off the top of the deck. So I've shuffled the deck, and now I'm taking the top card, and I got the queen of clubs. Okay, the last function we have in the deck class is cut. And cutting the deck, we do in fact need to provide an unsigned int for the location at which we want to cut the deck. This is not just an int, because ints have negative numbers. So saying we want to cut the deck at the -8th card, that makes no sense at all. So when I wrote this function, I said the parameter on the function side and the argument on the calling side needs to be an unsigned int. So it starts at 0 and is always positive. Let's go call this function. So let's go ahead and cut the deck. And first, I will show you that I can cut the deck after the 0th card. Programmers start counting at 0 for very good reasons that I'll talk about later in the specialization, but I'm going to cut the deck at the 0th card, which means I'm going to cut it just past the king of spades. We know the king of spades is on the top of the deck if we haven't shuffled it when it's created, so I'm going to cut the deck, taking the king of spades off the top of the deck and putting it on the bottom of the deck. So cutting the deck just past card 0 should give us the queen of spades. And it does, as expected. I could cut the deck just after the 13th card in the deck because we're doing 0-based counting, and I should get the king of some other suit, because I know when I built the deck, My first 13 cards were the king through the ace of spades. And I know that because I wrote the class. You don't know that as a consumer of the class. I know that because I wrote the class. And so I see the king of hearts. And I could even figure out what order they go. So spades, hearts, diamonds, and we could ask clubs, right? We should have known that even before we did it. So the last function here, it doesn't return anything because it's just changing the internal state of the deck, but we do provide information to tell it where we want it to cut the deck. To recap, in this lecture, we accessed the behavior of an object by calling a variety of functions, and we used the documentation to make sure that we were calling those functions properly. This will be an incredibly short lecture, but I wanted to keep the Unreal Engine discussion distinct from the pure C++ discussion of classes and objects. So in Unreal, the scripts that we create are, in general, classes. And when we drag one of those scripts to make it an actor in an Unreal map, that is an instance of the class or an object. It turns out that we won't use constructors to create objects in Unreal, but we'll explore the details of that in the next module. So to recap, our scripts in Unreal are almost always classes, and when we pull one of those scripts into the map as an actor, that's an instance of the class or an object. What will you learn about in this lesson? You'll learn how the Unreal Editor is arranged. You'll learn about meshes and actors. In other words, when we import a model into Unreal and then add it to our map. In the Lights Camera lecture, you'll learn how to set up an orthographic camera and a light to light our models properly. So throughout the courses in the specialization, we'll be importing 3D models, but all our games will keep everything in the YZ plane. So essentially, we're building 2D games using 3D models. You'll remind yourself, or I'll help remind you, that scripts are actors. And then we'll look at how we can debug a script in Unreal. We'll look at blueprints, which are reusable assets. We'll study basic physics. And we'll learn how collisions work in Unreal, both collision detection and collision resolution. In this lecture, we'll explore the different parts of the Unreal Editor. So let's go do that. This is the default layout for the Unreal Editor, and throughout the courses in the specialization, I will just use the default layout. So there are a number of different areas that we need to know about when we're using the Unreal Editor. First, at the very top here is a menu bar. So you can do sort of the standard things in the menu bar, and periodically I'll show you how we use the menu bar to do some of those standard things. Over here on the left is what's called the Modes panel, and we'll most commonly use the Modes panel to drag assets from there into the map. And the map, which you can also think of as a level, is displayed here in the Viewport panel, which you'll hear me and many others simply just call the viewport. So one of the ways that we add assets to our map is to take the mode panel and drag them over and drop them into our map. Another way that we add assets to our map is down here on the bottom using what's called the content browser. And this, not surprisingly, lets us browse our content, and you'll see as we develop our Unreal games throughout the courses in the specialization that we will populate this content browser with assets that we can then drag into the map. And by the way, when we drag an asset into the map, it's called an actor. So it's an asset when it's just sitting off somewhere in a folder, but once we drag it into our map, it's an actor. Over here on the upper right, you can see the world outliner. So this shows everything that's been placed in the world. And these are default assets that are placed in our level. This is with no starter content. This is just the basic stuff that Unreal adds to a no starter content project. So you can see if I select floor, for example, I've now got the floor selected in the map itself. And you may have noticed that a whole bunch of stuff showed up down here. So down here is called the details panel. And the details panel is where we modify characteristics of the actors that we have in our map. So for example, if I decided that I wanted the floor at 100Z instead of 20, I can just do that, and I've just moved the floor up. You'll also commonly see, as you move things around, this message that says the lighting needs to be rebuilt. And there are a number of different ways we can build the lighting. We can Control-Shift-Semicolon, and if you do that, it says it's starting up a swarm connection that's just the lighting builder in Unreal. You'll see some messages down on the lower right, and then lighting has been rebuilt. The other way you can rebuild lighting is by using this toolbar that you see along the top above the viewport. So you can also click this down arrow and you can say build lighting only. So that's another way to build lighting if you've forgotten the hotkeys for building lighting. And of course this toolbar also gives us other options like saving current, which you can also do with Control S. It lets us play the level, which isn't exciting with the default level, and a variety of other things that we'll explore as we build games. The only other thing that I'll talk about in this lecture, because we'll be interacting with all these different parts of the editor as we build games, this is just a quick tour of how that works, is down here on the bottom, you'll see I also have an output log tag. And that doesn't come by default, but we're going to use that a lot, especially early on in the first courses, to display messages. So if you don't see the output log tab in your configuration, you can always go to Window, Developer Tools, Output Log, and select Output Log, and that will give you the output log panel, and you can drag it down over here and dock it next to the content browser and so on. This is a pretty standard interface where you've got dockable panels and you can peel them off from where they currently are and move them somewhere else. But I'm going to just leave it as the default layout so that we don't have to worry about that changing the way it looks. If you keep the default layout as well, then your Unreal editor will look the same as mine, and that will make it a little easier to follow along as I'm doing things. And that's a quick tour of the Unreal editor. To recap, in this lecture we learned that the Unreal editor has lots of panels that are useful to us as we develop Unreal games. In this lecture, you'll learn how to import models into Unreal and how to add meshes to your Unreal map. A model is a graphical 3D asset, and when we import a model into Unreal, we get a mesh and one or more materials and one or more textures. An actor is an entity that we've actually placed in an Unreal map. Let's go see how all that works. I've created a new Unreal project called Meshes and Actors, and our goal here is to get a model imported into our project and drag it into the map. The first thing I'm going to do is I'm going to come over here in the content browser, and I'm going to add a folder here in the content browser So I right-clicked and I'm selecting New Folder. And I'm going to call this folder Meshes and Actors. The reason I'm doing that is because we're going to try to follow this Unreal Engine style guide as much as possible for the naming conventions in our Unreal Engine projects. And those naming conventions apply to folders and folder names and folder structure, as well as the asset names for the assets that we import or create in our Unreal Engine games. And there's the URL magnified so that you can read it and easily type it in and bookmark it in case you ever wonder how you should name assets as you're developing Unreal Engine games. This is really a great style guide, so we're going to try to follow this as much as possible. Now that I have my Meshes and Actors folder, I'll double click it and I'll create another folder called Maps, so I can store all the maps in my game in a single folder, and I'll save this map into my new maps folder, and I'm going to call it Map 0. As we build more complicated games, we'll certainly call our maps gameplay and perhaps main menu or controls menu or those kinds of things, but for now we can just call it Map 0. It would be convenient if this map opened up in the editor whenever we open the editor. It's not currently configured that way though, so let's fix that by going to Edit, Project Settings, and on the left I'm selecting Maps and Modes, and I'm going to change each of these to be Map 0. And that will make it when we start up the editor, it goes to this map, and when we start up the game, it goes to this map, and so on. I'll also go to the project description and say, if you want to avoid the annoying comment that says this at the top of each of the scripts that you create, you can change that here, and that will populate that top comment on your scripts with whatever you've put here instead. But since I'm not adding any scripts in this particular project, I'm not going to bother doing that. Once we're done here in the project settings, we can just click the X in the upper right hand corner and close that panel just as you'd expect. Okay, the art assets should go into a folder called Art, and when I double click Art, I'm only going to import one FBX model into this particular game just to show you how that process works. But generally you have multiple models in your game, and typically I will create a folder for each of those models that I'm importing. So I'm going to right click here and I'm going to select Import to Game Meshes and Actors Art ... And here's where I'm going to import my model. So I'm going to navigate to an FBX and select that using this browser panel. And once I've selected that, we'll come back and continue with the process. So I've selected a static mesh called SM Yellow Teddy Bear. That's the FBX file name right there. And I'm going to leave everything here as defaults. I will say that this is a static mesh. It's not something called a skeletal or skeletal mesh, which would mean that I'd want to check this checkbox here. But the skeletal mesh is actually, it's got bones and it's skinned and it's rigged to do animations. And we're not going to be using any of those kinds of models in this specialization. We're focusing on the basics of C++ and C++ in Unreal Engine, doing interesting things. We're not focusing on the more complicated 3D things we can do, like animating meshes. We'll leave that for your future exploration. So I'm importing a static mesh. I'm leaving all the defaults and I'm saying import all. I'm going to turn on the magnifier, and down here in my content browser, I end up with a number of different components of this static mesh. I have the mesh itself right here. I have a material for the mesh right here. I have a diffuse or specular texture for the mesh, so its color and so on. And I have a texture that specifies a normal map for the mesh. So I made a big deal about following the naming conventions at that website, but the name of this static mesh, for example, the base asset name shouldn't be in snake case here, it should be in Pascal case. That's an easy fix. For me, I'm going to right click and rename it. And now I can just make the name have the base asset name in Pascal case instead. You certainly can have your artist change this as well, but I wasn't very specific for my artist about how exactly I wanted everything named. So some of these are pretty close. It turns out that we want static meshes to start with SM. We want textures to start with T, we want materials to start with M, and so on. So I shared some of that with him, but I didn't actually say the exact name I wanted to use for these assets in the game. So I could certainly have had him go back and rename everything in Maya to export, so I didn't have to rename here, but it's certainly reasonable for me to just rename them here as well. So I'm just going to rename all of them. I will also point out, if you didn't actually have to rename them, you still want to save them. These two assets have stars, which means they haven't been saved as U assets yet, Unreal assets. So if you don't have to rename them, you can just select Save All and click Save Selected, and it will then save them in the Unreal Asset format. But I'm going to rename them. Renaming them automatically saves them as well when you're done renaming, but I'm going to rename these so that everything is the way I want it to be for my asset names in my game. Just one more to go. And I'm going to turn off the magnifier now. So as I said in the previous lecture, when we take an asset and we drag it into the map, we have turned that asset into an actor in our map. And for all the games in all the courses in the specialization, we're just going to set X to be 0, and we're going to play our games in the YZ plane. So Y goes to the right here, that's that green arrow, and Z goes up, that's the blue arrow. So now we've added our static mesh into the game. And as you can see in the World Outliner panel, it's got a name, and we can rename it here if we'd like to. We can change it to moving if we were going to move it around. And if I click on the actor here in the World Outliner panel, then it focuses me right in on my actor. I think I'd like to actually make Y be 0 and Z be 0. And by the way, you can navigate around the world with your mouse, and I'm going to let you just explore those different ways to do it. It's not worth me just saying, well, sometimes you alt left click and so on. Just experiment with that to navigate around the world. I am going to get rid of the floor. So I've just selected it in the World Outliner and hit the delete key. And if I play the game right now, sadly I can't actually see the teddy bear in the game. That's okay. In the next lecture, we'll see how we can add an orthographic camera and change our lighting source so that we can actually see the teddy bear in the game. So the focus on this particular lecture was how do we actually import the static mesh into our project. To recap, in this lecture you learned that a model is a graphical 3D asset. You've learned that when you import a model into Unreal, that you get a mesh, one or more materials, and one or more textures, and you also learned that an actor is something that we've placed in an Unreal map. In this lecture, you'll learn how to set up an orthographic camera and a light source so we can build 2D games. Our games are actually 3D actors in 3D worlds, but we're going to treat them as 2D games by keeping all our actors in the YZ plane. Let's go see how to add our camera and set up our light source. This is where we ended up in the previous lecture. I have a teddy bear mesh, static mesh, in my map, but we can't see it when we run the game. And because all the games that we're going to develop in the courses in the specialization are essentially going to be 2D games, we're going to keep all of our actors in the YZ plane, so at x equals 0, and that means that an orthographic camera is a better choice for the games we're going to develop. Let's add an orthographic camera to the map. I'm going to come over to the Modes panel, and it turns out that we can search for the things we want to add, and I'm going to add a camera to the map. And I'm actually going to add it at 500 in X and 0 in Y and 0 in Z. I'm also going to say that the camera is static. I'm not going to move it around as I play my game. I'm going to make it orthographic, and I'm going to leave these settings the way they are. So I'm going to make sure my camera actor is selected, and then I'm going to come up here and select Blueprints, Open Level Blueprint. And while we're in a C++ Unreal Engine project, we're going to use the Blueprint scripting language just to set up the camera in the level. We could actually do this by writing a separate C++ script and so on, but there's no need for us to do that. We can just use Blueprint just for this one thing. So don't worry about the details of how is this scripting language working and how are functions getting called and so on. These are just the few basic steps we need to set up our orthographic camera. I'm right-clicking here and I'm going to search on player, and I need to get the player controller. So I've clicked on that, and then I drag off the return value and I say set view target with blend, and then I connect those two together. I will point out that that begin play event is the same as the begin play function that we used in our script to send a message to the log. We're almost done here. All I have to do is right click and create a reference to the camera actor and make the camera actor the new view target. I'll move this out of the way. And that's really all we need to do to set up our orthographic camera. I'm going to compile because this is code. It's just in a visual scripting language. And then I'm going to save because it compiled fine, and I'll close that panel. The other thing that I want to do before I move the light source around is I want to get rid of the actors in the map that I don't need. I need the atmospheric fog to give us a background. I need the camera actor to render the map in an orthographic way. I'm going to need the light source to light my model. I don't need player start. We'll need it again later in the courses in the specialization. Not in this one, but in later courses. But we don't need it for now. We don't need the sky sphere. We don't need the skylight. Let's keep our teddy bear model, but we don't need this either. So at this point, I'm going to change the characteristics of my light. And remember, this is the default light source that was added to the map by Unreal. I'm going to change X to -500 because I want to light the model from the front. I'm going to set Y to 0 but I'm going to set Z to 100 so that it's above the camera. And then for rotation, I'm going to use 0 in X, -10 in Y, and 10 in Z. And when we run, we still can't see it because I made a mistake. So our camera actor should be at X equal -500. You can see the teddy bear there in the preview. And my light source is in fact already at -500. So now when I play, we got this weird sphere. Sometimes that happens. I'm going to play again, and there you can see my teddy bear in the middle of the screen. Now, that teddy bear is pretty brightly lit, so let's fix that. We'll take the light source and we can change the intensity here, and I'm actually going to change it to be really, really mild. So 0.2 lux. When I run my game again, as you can see, I now have my teddy bear in the background. It's got this nice blue background behind it, and it's an orthographic view. So we've set up both the light source and the camera actor to give us an orthographic view with a good location for the light and a good intensity for light for really all the models that we're going to use in the courses in the specialization. And of course, I should save my map. And that's it for our Unreal Engine work for this lecture. To recap, in this lecture you learned how to set up an orthographic camera so we can treat our games as 2D, and you also saw how we could set up a light source to render our meshes properly. As we've done in several previous lessons, we can create C++ scripts to implement custom behavior. We've always selected actor as the base class for those scripts when we create them, and when we drag those scripts into the map, we've been turning them into actors. This lecture is a reminder of how all that works. I've created a new project and set up folders and saved the map. I haven't bothered with the orthographic camera or the light because in this lecture we're just reminding ourselves that scripts are actually actors in our map. I'm going to come up to the top menu bar and say File, New C++ Class. I will select Actor. I'm going to change the name of my script to Say Hi, and I'll create the class. And then we wait patiently while the code is added to the project. And here we are over in the code. We'll do the usual stuff. I'll say I don't need the tick function to be called every frame, but in begin play, I want to say hi. And remember, we use UE log for that. We can use the log temp, warning, the text macro, don't forget the semicolon all the way at the end, and I'm going to say hi, so I'll say hi. I'll compile, and I need to make sure I do that so that my changes take effect when I go back to the editor and add this script as an actor to the map and run the game. So back here I need to navigate to my script so I can drag it into the map to make it an actor, and I'll click this folder and I'll expand C++ classes, and here I am. So I'll just drag it over into the map and I'll select the output log tab, and when I play we see that hi message. I know you've seen this before, and I just wanted to remind you that scripts are in fact actors if we drag them into the map. And that's important because we'll see in a few lectures how we can take that script actor and turn it into a reusable asset that we can place numerous times into the game or even spawn as the game plays, though we won't get to that until the next course in the specialization. So I'll save my map, and we're all done in the Unreal Editor for this lecture. To recap, in this lecture you were reminded that our Unreal scripts are specialized forms of actors that implement custom behavior. In this lecture, you'll learn how to debug an Unreal script using Visual Studio. Recall that in a previous lesson we talked about the debugging process. We'll use that same debugging process when we debug an Unreal script. I've created a project that has an actor called Buggy Trigonometry, so let's go take a look at that actor. I've added our Buggy Trigonometry code to the script, except that we're not prompting for and getting an angle because we haven't learned how to do that yet in Unreal. So I've declared an angle variable and set it to 45 degrees. I'm trying to convert the angle to radians here, but MPy gives us a compilation error. So let's find out in the Unreal Engine documentation what we should do instead. Here in the documentation, I'll search on pi. And I get a number of results. So let's click on this get pi thing because that seems like it might be useful. Unfortunately, this is the blueprint for get pi, but it says the target is the Kismet math library. So let's search the Kismet math library. And if we click on the top result, we see that there's a math library that has lots of functions available to us. So let's look for get pi. And luckily this is in alphabetical order, so we found get pi. We can click on it to see that it returns the value of pi as a float. So we can call this function in the UKismet math library to get pi. So we'll say, I'll steal some code from down below. So remember, when we fully specify a namespace, UKismet math library is a namespace. So we put the namespace, colon, and then we can call get pi to actually get pi. Now, one of the important things in that documentation was at the very top of the documentation, and it said we need to include the Kismet/Kismet math library.h header file. So I've already done that here in the script. I already knew I needed to do that, so I did it here. So we're using the UKismet math library namespace, which is specified in the Kismet math library.h header file. So we have to pound include that header file so that we can use stuff in that namespace. I made a mistake here. I wanted us to have a bug, so let's add our bug back in. And I meant this to be the buggy code from before. And as you can see, when I run it, we get incorrect cosine and sine values in our output log panel. So now it's time to actually debug our code. Now there's lots of information on the internet about how you can debug your C++ code with Unreal Engine and Visual Studio. Unfortunately, my personal experience has been that sometimes those things work and sometimes they don't, and I'll even do something and it'll work the first time and then it won't work the second time. So debugging in Visual Studio with Unreal Engine is a hit or miss proposition much of the time. I will say that you can always use the uelog macro to print out intermediate values of variables to see what they are as you run your game. But I'm a huge fan of using an actual debugger to do stuff, so I may have found something that consistently works, and I'll walk you through what that thing is. So I'm going to actually close down the Unreal Editor, and I went to the folder that holds the Unreal project and double-clicked the solution file, the Visual Studio solution file. The extension for that file is SLN, and it's the same solution file you would double-click if you were doing a console app, except of course this is in an Unreal Engine game. Once Visual Studio opens, you need to make sure that up here under the solution configurations you select Development Editor. And then you need to rebuild your solution. So you select Build and you say Rebuild Solution. I've already done that. That takes a long time, so I'm not going to do it again during the video. But now I can set a breakpoint and I can just press F5 to debug just like we did in a console app. And what's going to happen here is it's going to actually open up the Unreal Engine editor, and we'll be able to run our game with the Visual Studio solution attached to that Unreal Engine game so that we can debug. I'm going to turn off the magnifier again, and now when I run my game, I stop at that breakpoint, and I can look at the value of angle either here or down here, and I can see that the value of the angle is horribly incorrect. I will point out that I added a little extra to my code to make this work though. So compilers will optimize code, and optimizing code means that it makes it run more efficiently by sort of restructuring sometimes as it generates the machine code that's going to run on the machine. The problem is that in the debugger, sometimes that optimization makes it so we can't actually look at the values of variables. So for example, I might try to hover over angle, and if the compiler has optimized that variable away, just because it's used temporarily here in this function, then I won't get anything when I hover over it, and I won't be able to look down below to see it. And in fact, even the thing down here in locals that says this, that I can expand and look at characteristics of it, that also will say this has been optimized away. And that's not helpful to us while we debug. It's usually helpful to us as we run our game because we want our code to run as quickly as possible. But if we can't look at it with the debugger while we're trying to fix bugs, that's not helpful to us. So I've added what's called pragmas. And this pragma, I might as well stop debugging for now. And this pragma, optimize, I'm basically saying turn off optimization for everything. There are various levels of optimization, and by providing this empty string, I'm saying turn off all the optimization. So I turn off optimization before the function that I'm trying to debug, and then I turn it back on after the function I'm trying to debug. So this is a function level command, if you will, to the compiler, and this is a Visual Studio compiler command. Other compilers will have potentially different commands for turning optimization on and off. So I needed to do that so I could actually look at the value of the angle variable while I was debugging. We know that this is backwards, so I will multiply by pi and then divide by 180, and I'm going to debug again. And I'll just press F5 and I'll run the game again. I hit the breakpoint again, but this time angle is the correct angle, remember, about 3/4. So now that I believe that I've fixed the problem, I can get rid of the breakpoint and I can close the Visual Studio solution. And I've opened the project in the usual way, and now when I Alt-P to run the game, we see that the cosine and sine values are now correct. To recap, in this lecture you learned how to debug an Unreal script in Visual Studio, recognizing that it may be easier to just use UE-log to output the values of selected variables in your code. The process I showed here does not work in Xcode, so to debug an Xcode Unreal script, you're really going to just have to use UE-log to print out those variable values. In this lecture, you'll learn about how to create blueprints. And I'm not talking about the blueprints visual scripting language in Unreal, I'm talking about something else. So what are blueprints? They're prefabricated entities. In other words, they're entities that we've configured to behave the way we want them to, and then we've saved them as a blueprint. What are they good for? In the editor, they're useful for adding multiple instances of that blueprint to the map. And as we'll learn later in the specialization, they're also really useful because we can spawn blueprints from a script. I've already built my project. I've put the orthographic camera in and set up the light source. I've imported the yellow teddy bear static mesh and its material and textures. And I've created a script called teddy bear that logs a message saying, "Hi, I'm Ted." I added that script to the map, so if we run the game and go over to the output log, we see it says, "Hi, I'm Ted." Now what we want to do is we want to turn this script into a blueprint, a reusable asset that has both behavior, printing out a message, and a visual representation, the static mesh for the yellow teddy bear. I'm going to remove the script from the map. Before I actually create the blueprint, I want to put a folder in my content that holds blueprints. So I'll go to our blueprints folder. I know that's the name of the project as well. I already have an art folder that holds the mesh assets. I have a maps folder that holds our single map. And I'll create a new folder that holds all our blueprints, the one blueprint we're going to create. Now I'll go back to the script and I'll right-click the script and I'll say create blueprint class based on teddy bear. What that does is it brings up this dialog for me to name my blueprint, and I'm going to always put BP underscore for blueprint underscore for this blueprint asset. And I'm going to make sure I put it in that new blueprints folder that I just created. Once I click that green button, I get the blueprint editor panel here, and the blueprint already includes the script because we said we were creating the blueprint from the script, but it doesn't have the yellow teddy bear static mesh yet. So we can come over here. Notice that I have the blueprint editor not maximized and moved out of the way. So I can navigate over here in the content browser and I will drag my static mesh here onto this sphere, the default scene root. And as you can see at this point, I now have both the sphere and the teddy bear, but I can get rid of the sphere by dragging the teddy bear up one more time. And now I just have the teddy bear and the script built together into my blueprint. I'll compile it just like we needed to compile the level blueprint when we set up the orthographic camera. And I'll save it. And I'll close this. So if we go to that blueprints folder, we now have this blueprint. And if I place 1 in the scene and make sure he's at 0 and X, when I run my game, I can see in the output log that he printed that warning. I'll also say that I can drag multiple instances of this reusable object into my map, making sure that I have them visible and making sure that they're in the YZ plane. And if I run my game again, we can see all three of them, and we can see in the output log that they all printed the message. One of the things that's really nice about these blueprints is not just the convenience of being able to drag multiple instances of the blueprint into our map. I can go back to Visual Studio and I can change the message in the script and recompile it, both to make sure I didn't make any mistakes and to make sure it has an effect when I run the game. And then back in the game, if I run the game again, you can see that all three of those instances of the blueprint are outputting the new message. So if we've set up these blueprints as reusable assets and we decide to make a change to the behavior of the blueprint, then that change automatically takes effect in every instance of the blueprint that's in the map, and of course every new instance of the blueprint that we bring into the map later. To recap, in this lecture you learned about blueprints and you learned how to make one. You learned that they're useful for adding multiple instances of the same blueprint to a map. And I told you that later in the specialization we'll also discover that blueprints are great when we want to spawn those blueprints into our game. In this lecture, you'll start learning how to use the built-in physics in Unreal. And Unreal uses the physics PHSYX software development kit, or SDK, from NVIDIA to implement its physics. This is essentially what we ended up with at the end of our blueprints lecture. I have a blueprint, this time for a yellow teddy bear because I have teddy bears of multiple colors. And if I Alt-P, he just sits there. So in this lecture, we're going to implement basic physics. We'll come over here to Edit, Project Settings, and we will scroll down under the Engine section down to Physics and select Physics. I'm going to turn on the magnifier. So here, under Simulation, we have default degrees of freedom, and it defaults to full 3D. But remember, we're trying to keep our actors in the YZ plane. So instead of using full D, we'll say constrain all our actors to the YZ plane. So no matter what forces are applied to our actors, they won't come out of the YZ plane, and that's a good thing. Next, if we scroll down to constants, you can see the default gravity is in the Z direction, which is just what we want because Z is pointing up in our games, and it's -980, and that works just fine. You should know that the gravitational constant on Earth is pretty consistently -9.8 meters per second squared. No matter where you're located, it varies a little bit, but that's a reasonable constant to use. So we've only changed one setting here, but we looked at the gravitational constant. We'll close our project settings, but it doesn't matter that we constrained our actors to the YZ plane. Still, when we run the game, the teddy bear doesn't do anything. However, if we select the teddy bear blueprint, and it's sometimes the case that we actually need to expand this area a little bit under components, but we want to select the static mesh component on the yellow teddy bear blueprint, and if we scroll down a little bit, we can say simulate physics. The other thing that we'll do is we'll say we don't want any linear damping. So linear damping means as we move, we slow down a little bit over time. And we're not going to have any of that in our game, so we'll change that to 0. And now, when we run our game, watch closely, the teddy bear falls out of the screen. It's important to realize, though, If I come over here and I drag another instance of the blueprint over here, and so up here in the world outliner, you can see this is Yellow Teddy Bear 2, and I change the location of Yellow Teddy Bear 2 to be 0. I'm going to move him over a little, -100, like so. When we run our game, only one teddy bear falls. So this is an important thing to recognize. You might forget this once or twice or 100 times, but the changes we made to this instance of the blueprint were just to the instance of the blueprint. It doesn't change the blueprint itself. We can change the blueprint itself by clicking this blue button that says Edit Blueprint and saying Apply Instance Changes to Blueprint. So we're trying to make the blueprint match what we now have in the instance. And it did update it, but you can see on the blueprint that it now needs to be saved, so we'll save it. And now if I drag another instance over and make sure it's in a reasonable location, if I Alt-P, they both fall down. So that's an important step. When you're modifying a blueprint in the map, you need to make sure that you apply those changes to the blueprint and then save the blueprint to make sure those changes take effect. Okay, I'm going to get rid of this Yellow Teddy Bear 2. Now for this lecture, I've also imported a green teddy bear model and a purple teddy bear model, and I'd like to have all three of them as blueprints that I could place in the map. So I'm going to go to the Yellow Teddy Bear blueprint and I'll right click it and I'll say Duplicate, and I'm going to change its name to Green Teddy Bear. Now this green teddy bear blueprint still has the yellow teddy bear static mesh on it, so if I double click it to open up the blueprint editor, you'll notice it actually brings me to what's called the event graph panel, which is not what I really want here. The editor thinks I want to start using the blueprint scripting language to edit my blueprint, but I don't. But I can get back to the viewport that we saw the first time we edited blueprint by clicking the viewport pane. And as you can see, I have a yellow teddy bear there. I'm going to navigate in my content to my green teddy bear static mesh, and I'll drag it up and drop it on top of the yellow teddy bear mesh. Now that is a weird looking teddy bear, and I like it a lot, but I'm going to make the green teddy bear just be a green teddy bear, and I can do that by either dragging this up like we did when we were getting rid of the default scene root, or in this particular case, I can actually delete the yellow teddy bear and the green teddy bear becomes the new root for the mesh. I'll compile, I'll save, and I'll navigate to my blueprints folder, and I'll put one of these in the scene and run my game. And it's important to note that even though it brought the behavior over, I didn't show you that, there's two hi I'm Teds, one for yellow, one for green, but it did bring over the behavior of the mesh. So the physics characteristics that we used on this blueprint were associated with the mesh that's attached to that blueprint. When we replaced the mesh, we got rid of all those characteristics. I'll show you another way that we can edit the underlying blueprint. So remember, for the yellow teddy bear, I did this by changing the instance and then applying those changes to the blueprint. I can also open up the blueprint editor. I don't actually have to go to the viewport for this, but I like to have that view. If I select the mesh, I can just over here in the blueprint itself, I can say simulate physics and set linear damping to 0. We'll compile again, we'll save again. And now when I run my game, they both fall down. So there are two ways that I can put a change into a blueprint. I can edit an instance in the map and then push those changes into the blueprint, or I can open up the blueprint editor and make those changes directly there. I'm going to do this one more time because I want a purple teddy bear as well. I'll open it up in the blueprint editor. I'll navigate to my art. I'll drag the static model up here and then delete the yellow teddy bear mesh. We'll look in the viewport and see we do in fact have a purple teddy bear there. I'm going to remember to make this blueprint obey physics. More accurately, this static mesh that's a component of the blueprint obey physics. I'll compile, I'll save. We'll put one in the game. And I'm not sure how I managed to do this, but I lost my yellow teddy bear blueprint. So let's get him back in there as well. And now we've got a yellow, a green, and a purple teddy bear in the game. And when I run, they all fall out of the game. That's certainly basic physics, right? Gravity is basic physics. And I did want to show you how those physics settings can be handled or need to be handled as we modify the blueprint by changing the static mesh that's a component of the blueprint. To recap, in this lecture you learned that the Physics SDK in Unreal lets us implement physics behavior without having to actually code our own physics simulation. And I'll tell you that we can also take advantage of the physics engine functionality from within scripts. And if you want to explore that, you should do exercises 12 and 13 that let you do exactly that. In this lecture, we'll learn about collision detection and resolution, and we'll learn how collisions and physical materials help us with that in Unreal. So what's collision detection? You won't be surprised to hear it's detecting a collision between two actors in a map. If both of those actors have a collision, a collidable volume for that actor, then the physics engine can detect those collisions automatically. And I know that terminology is a little difficult because the collidable volume is called a collision and the collision between two actors is called a collision, but we'll just deal with that Unreal terminology. A collision is a collidable volume for an actor. What's collision resolution? It's doing something as a result of the collision. So physical materials help the physics engine determine how the collision should be resolved from a physical perspective. And we'll learn later in the specialization that we can also do our own custom collision resolution from within scripts. Let's go see how all that works. If we navigate to our static mesh for the yellow teddy bear and double click it to open up the mesh editor, we can actually look at the collision that was added when we imported the model. I'm coming up here to the toolbar on the top and expanding this and showing simple collision, and then I'm zooming in and you can see that we have a collision volume, or what in Unreal Engine is just called a collision, already associated with this mesh. If you don't like that particular collision, you can come up to collision on the top menu bar and you can remove the collision that was added when we imported the mesh, but I'm not going to do that. But if you want to, you can remove that and then you can add a different collision to this particular mesh. And you can add a sphere, which looks like a sphere. You can add a capsule, which looks like a capsule, and you can add a box. So sphere, capsule, and box are pretty efficient collisions. You can add other types of collisions as well, but I'm just going to use the default collision that we got when we imported the mesh. I need to add a floor for the teddy bears to bounce off. So I'm going to get rid of this from when I added the camera to the scene, and I'm going to drag a cube over into the game. I'm going to need to manipulate the cube to make it like a floor. And so I'll center it in 0 and in Y, and I'll put it at -149. Which through trial and error I have determined is a good place when we display it with the orthographic camera. I also need to scale it in Y to make it extend the full width of the scene, and I'll also make it thinner because I don't need that much there. You'll see I have a message that said lighting needs to be rebuilt, so I'll do that. And now when I run the game, the teddy bears fall down and land on the floor. Now, I'd like the teddy bears to bounce more than that. So I'm going to add something called a physics material to each of the blueprints that I'm using for these teddy bears. These are the blueprints that we had from the previous lecture when we did some basic physics. So I'm going to go to Content and go into my collisions folder, and I'm going to add another folder called Physics. I'll go into the Physics folder, I'll right click, and I'll say Physics, Physical Material. I'll select Physical Material as the class I want to use and click the green button, and I'm going to rename this Physics Material PM_teddy bear. If I double click it, I can edit the physics material, and the two things that we're going to care about are friction and restitution. So friction is just as you'd expect, sort of how sticky it is when you try to slide along it. We're just going to leave friction just as it is, but restitution is bounciness. And I would prefer a rubber teddy bear compared to a 0.3 bouncy teddy bear, I guess. So the scale of all these values are 0 to 1. So I'll make the teddy bear as bouncy as possible by setting this to 1. And I'll save it and close this. While I'm here, I know from past experience that I want the floor to be a little bouncy also. So I'll create another physical material for the floor, and I'm going to call this one PM Floor. And I'm going to leave the friction the same. I'm going to make it kind of bouncy, but not totally bouncy, because I know that I get too much bounciness, but this is the kind of thing that you sort of play around with and figure out what works best for your game. Okay, I'll save this. And now I need to attach the physical materials to each of the actors that I want them attached to. For the floor, which I have selected here, and in fact, why don't I just come up here and change its name from cube to floor. That's a little more descriptive. And I can scroll down in the floor, and under collision, I can override. This is hard to read because it's cut off a little. It's Phys Material Override, and I'm going to pick PM Floor as the physical material to use for the floor. For the teddy bears, it'll be easiest for me to modify each of the blueprints rather than modifying these actors that are already in the map. So I'll go to Content, my Blueprints folder, and I'll double click each one, select the static mesh, scroll down over here, and under collision, I'll select teddy bear. I'll compile because I changed the blueprint, and I'll save, and I'll do that for the other two as well. So select mesh, scroll down to collision, and pick teddy bear, compile, save. And now when we run the game, we've made our teddy bears really bouncy as possible, and we've made our floor pretty bouncy, not the maximum, and we can see what happens. And that's pretty good. You could just watch that and be hypnotized, but I'm going to stop it. The other thing that we want to have happen is we want teddy bears to actually bounce off each other as well. And I'm going to show that that's happening by adding another teddy bear to the scene pretty much right below the yellow teddy bear that's right there. I'll slide it over a little. And over here on the right, I need to make sure it's at 0. And then I'll slide it over. And now these two teddy bears will bounce off of each other, as you can see, and they bounce on top of each other and they fall over and all kinds of great stuff. That was a nice little flip. Now, something that you haven't seen is this game running with 18 teddy bears, 6 of each color. So I'm going to go add them, and then we'll come back so you can see that. Okay, so I've made it so I have 6 teddy bears of each color. When I run the game now, you'll see they bounce off each other, and we've lost some of them out of the game, which is sad for me. So let's make one more change. I'm going to add walls on the 2 sides, so I can drag in another cube. I can change its name to right wall. And I can place and scale it properly. So I've placed it on the right hand side, and I'll make it skinny, and I'll make it tall enough. And again, I messed around with those different settings to place the wall in the right place. And one more cube over here at 0, -261, 0. And again, scaling it as 0.1, 2.88. And I haven't added any physical material to these, but I do need to rebuild the lighting. So the teddy bears that bounce off the wall will bounce off them a little bit, not a lot, like the bounciness from the floor. So one more time, we'll play the game. And the teddy bears bounce around for a while and then stop, but we still have all 18. To recap, in this lecture you learned how collisions, those collidable volumes, help the physics engine perform collision detection. We saw how physical materials help the physics engine determine how to resolve those collisions from a physics perspective. And I also told you, though I didn't show you, that later in the specialization, we can also do custom collision resolution from within our scripts. Okay, you made it to the end of the course. Great job. I know for some of you it might have been a struggle with the programming in C++. That's why I require that you have learned some other programming language first, because pretty much nobody does C++ as a first language. Some of you may have also struggled with the Unreal Engine. Unreal Engine is a huge commercial quality industrial strength game engine, so that means there's a lot of complexity associated with doing even what feels like simple things. That's okay though, because we've been building up your foundational knowledge in Unreal Engine. There's still tons to learn about using C++ and Unreal Engine. So if you'd like to learn that stuff in a structured environment, you should move on to the next course in the specialization. But if what you've learned has been enough for you to say, well, I want to start messing around with it on my own to work on games, then you should do that too. And you should always do that, because building cool games is our end goal as we go through the courses in the specialization. I want to thank you for taking this course. I love doing courses on Coursera to share what I know about game development with all of you. So I appreciate you joining me on this journey of exploration in this first course. Cheers. Hi, I'm Tim Dr. T. Shamillard, and I'll be your instructor in this course. I'm an associate professor in the computer science department at the University of Colorado at Colorado Springs, where I predominantly teach game design and development courses, but I also teach some computer science courses. I'm also the program director of our Bachelor of Innovation in Game Design and Development. I have 5.5 years of indie game development experience in a company that I formed with my 2 sons, and now I have a one-man indie game dev company called Burning Teddy. This is a 4-week course, and you'll have 3 programming assignments to complete in weeks 1, 3, and 4, and each of those programming assignments is worth 25% of your course grade. You will also have a quiz to complete in week 2, and that quiz is worth 25% of your course grade. I've provided you with lots of exercises that aren't worth any points toward your course grade, but are really good practice for you to engage with the course material. So I strongly encourage you to do that. Speaking of the course material, in this course we'll cover selection, which is the way we make decisions in our code. We'll cover Unreal Input, so you can finally have the player interact with your Unreal games. We'll cover iteration, which lots of people call looping, because it lets us loop or repeat or iterate over blocks of code in our programs. And finally, we'll cover arrays and containers, which let us store multiple values in single variables. This course builds on the foundation of C++ and Unreal knowledge that we started developing in the previous course, so I expect you to have a firm grasp of that material. A couple of the lessons include chapters from a book that I may or may not ever publish about C++ and the Unreal Engine, but that provides you with an additional reference as well. And of course, if you run into trouble, you can also get help from the web or from the course forums. Let's go ahead and get to work. In this lecture, I'll show you how to navigate one of my courses on Coursera. And while this probably isn't the course you're currently enrolled in, that doesn't really matter. All the courses that I do on Coursera are structured pretty much the same. So let's go wander around one of my Coursera courses. Here's the home page for the course for you, and you can scan different information about the different weeks in the course. I typically would go to one of the weeks in the course, and this particular week has a module, and the module is starting to program. There are a variety of learning objectives for this particular week. There's a getting started lesson that will typically have some videos in here, a course introduction, this video I'm recording right now, and a meet the instructor video. And then there's another lesson here, your first C++ code in this particular course. And so there's a mix of videos and readings, oftentimes exercises or other kind of readings, and a discussion prompt typically at the end. And then most commonly, there's a programming assignment for you to complete. So let's look at this programming assignment. If I click it, you'll see I've passed. Wow, I could do the programming assignment. There are instructions that you should follow very carefully. Each of these steps or comments or sentences in the instructions matters, so you should read them all and do them. And then when you're ready to submit, you click the My Submission button, you click Create a Submission, and you upload a file, and you say you're going to abide by the honor code, and then you submit your assignment. So I'm going back, and I'm going to look at week 2, because if we look at this video integer data types, for example, I wanted to show you the resources that typically go along with each of the videos. So if you go over here on the left and select download, you can see there's a variety of things you can download. You can download the lecture video, you can download the slides. This one actually has an extra reading, and then I've got some zip files for, in this particular course, both Visual Studio Final Code and Xcode Final Code. So if you're in a course that you can use either Visual Studio on Windows or Xcode on a Mac, then I provide the code for both of those. If it's all Visual Studio, no matter which platform you're on, then of course I just provide Visual Studio code. But each of the videos that I generate code for, I include the code as a downloadable resource for you. So you should download that rather than trying to copy and paste from a video. If you're trying to use some of the ideas from the code I generated in the video, just go download the code and unzip this, and then you can use that code. Okay, also on the left in the navigation bar, you can take a look at your grades. And look at me, I've got 100 on all 3 programming assignments. This particular course has a final exam, a quiz at the end that I'm late doing, but that's okay. So this is where you can go to see all your grades. The notes section, you can add some notes if you choose to do so, and they can be created from the video pages, so you can capture notes for particular videos. Lots of people go to the discussion forums. So for example, if you went to the week 1 discussion forum, there's a generic week 1 discussion forum, there's a sub forum about the assignment that's due that week, and there are sub forums for each of the exercises as well. So there's lots of opportunity for you to interact with your fellow learners, posting questions about the course material or specific graded or ungraded activities, and people are generally reasonably active on the forums. So that's a good place for you to go to ask for help if you get stuck on stuff. The messages section, if I send you a message, it will appear here in the messages section. So my guess is you will probably be picking, in general, a particular week to interact with, and you'll work your way through the material for that week, all the way through submitting the programming assignment, and I expect that's in general how you'll interact with the page, although of course you may well be active on the discussion forums as well. And there you go. That's how you navigate one of my courses on Coursera. This is the totally optional, don't watch it if you don't want to, meet the instructor lecture. I'm Tim, Dr. T. Shamillard, and I grew up in a small town in southeastern Massachusetts named Norton. And after high school, I went off to Georgia Tech to pursue a bachelor's in electrical engineering degree, but I was only at Georgia Tech for a year. So if you'd like, pause the video and guess for why I only stayed for a year, and then continue. As one of my past students said, I left for the love of a good woman. So my girlfriend was in Massachusetts, Georgia Tech is in Atlanta, Georgia, and that was too far for me. So I spent about a year and a half putting stuff into boxes and handing it to the UPS guy. And then I enlisted in the U.S. Air Force, went off to basic training, went to technical training school, and after about 4 months in the Air Force, I got married. So pause the lecture again if you'd like, to decide whether that was the same girl I left Georgia Tech for or somebody else. The answer is, it is in fact the same woman, and we are still married. So here we are in the Air Force. We went off to Omaha, Nebraska for our first tour, and then after 16 months, the Air Force decided to send me to school full-time to pursue a bachelor's degree in electrical engineering at Georgia Tech. So I did get to finish that degree at Georgia Tech in electrical engineering, and then I went off to officer training school and got my commission as an Air Force officer. Our first assignment in the Air Force was at Los Angeles Air Force Base, where I spent 4 years managing contractors writing software to help us fly satellites. Particularly orbital software was my general area of expertise. We had our first 2 children, both boys, while we were in Los Angeles. And I also pursued my master's degree in computer engineering at the University of Southern California, going to school night. Finished that tour after 4 years and went off to the U.S. Air Force Academy, where I taught undergraduate computer science courses for 2 years. Now, the Air Force Academy is usually a 4-year tour, but I only spent 2 years there. So if you'd like to pause the lecture video again and try to guess why I only spent 2 years, go ahead and do so. The answer is the Air Force decided to send me off to UMass Amherst to pursue a doctorate. So I am in fact a doctor of computer science, so I don't actually help people. And my entire family loved the part in Treasure Planet, the movie, where there's a non-medical doctor and he is trying to help somebody who's injured, and he says, "I just sit here and I'm useless." And I saw that movie with my entire family at the movie theater, and at that line, every single person leaned over and looked at me. So everyone knows I'm a doctor, just not a real doctor. Okay, so I finished off that degree and went back to the Air Force Academy for that full 4-year tour that I should have had in the first place. And then my final assignment was to Washington, D.C., where I spent a couple of years managing contractors, developing web applications, and the databases that support those web applications. And then I retired from the Air Force. So I've been at the University of Colorado at Colorado Springs since 2003, and I've taught a variety of courses, including graduate-level software engineering courses, undergraduate computer science courses, and undergraduate game design and development courses, all of which I created from scratch. And in fact, we now have a Bachelor of Innovation in Game Design and Development, and I teach many of the beginning and the final course in that particular program, and I'm the program director for that program. So at this point, I exclusively teach game development courses. I also spent a year and a half as an indie game developer in a company that I formed with my 2 sons, and that's Peak Game Studios. And we did a number of games both on speculation and on contract. So here are the games we built on speculation. The 2 images on the left are a game called Ket that's based on an actual board game. So we got the license from the board game manufacturer. And you can think of this as chess with lasers. And you can actually download a free version of this game at this point from the Burning Teddy website. I'll talk about Burning Teddy soon. The other screenshot from the upper right is for a game that we didn't quite finish as we shut down the company once my sons sort of grew up and moved on to do other things. And that game is called Battle Paddles. And you should think of this as Pong with weapons, because that's sort of the big idea behind that game. We didn't quite finish it, but we'll get back to that game as well. So on this slide are the games that we built under contract. So as a company, we went and we got a contract to build some games, and we actually got paid to build them, and that was awesome. So the 2 on the left are for educational games for 8th graders. The one all the way to the left was a set of 4 mini games to teach about physics. And the title of that group of mini games was Physics with Neat Details. And if you think of the acronym for that, it's PWND. And so, of course, a little tongue-in-cheek game development, of course. And the lower one was to teach 8th graders about robotics. So they would configure a robot with various attachments to go complete a number of missions. Again, there were a few mini games to do. The upper right one is something called Colorado History Arcade. We got a contract to teach 4th graders about Colorado history. And that game was deployed on the Pikes Peak Library District website. So all of the games we built as a company, except for the Colorado History Arcade game, were using C#. We happened to use XNA Game Studio to do that. But now, of course, we've moved on to Unity. The company hasn't, but I have. And so that brings us to this next slide, where I tell you I now have a small company, and by small I mean just me, called Burning Teddy. And I use that company to publish textbooks and online courses, and of course also to do game development. So that Battle Paddles game that I showed you the screenshot from, I am in the process of porting that over from XNA Game Studio to Unity. That is about 60,000 lines of code, so it's going to take a little while to port, but at some point that will be on the Burning Teddy website, burningteddy.com. And I'm also working on another smaller casual game that is called Balloons Extreme, and I'll actually post my progress on burningteddy.com as I build that game in Unity. So Burning Teddy, all the game development I'm doing is actually in Unity. So when I'm not teaching and I'm not doing game development, what am I doing? Well, a number of different things. But one of those things is cycling. So riding a bike is one of my joys in life, I guess. So these are my 3 bikes. The blue one is the oldest one, and that's really an old bike at this point. But I used it to really get into cycling, not racing so much, but doing long rides like a number of centuries, which are 100-mile bike rides, including at the time one of the 10 toughest centuries in the United States. And so that century had over 10,000 feet of climbing. That's what makes 100-mile bike ride harder than another is, elevation gain. And so I did a number of bike rides. The mountain bike, the one on the bottom, is a result of going mountain biking with some friends one day. And I loved it so much that I went out and bought the mountain bike the next day. The bike all the way on the right is my triathlon bike. So, being a cyclist, I did a lot of long rides. I also did a bunch of running, including a number of marathons and a running race that goes from the bottom to the top of Pikes Peak here in Colorado Springs. I did that running race multiple times. And once you've biked a long time and run a long time, you say, well, you might as well do some triathlons as well. Just add a swim and you'll be fine. And so I've done a variety of triathlons, all the way from sprint distance, which are really short, all the way up to an Ironman distance race. I also play guitar. I started doing that way back in high school and then gave it up for decades while I was raising my family and doing other things. And now I've started up again to try to learn how to do it even better than I used to. So moving from left to right, the acoustic is a Yamaha acoustic that I bought way back when while I was just out of high school. The next guitar is a Joe Strummer replica. Fender came out with a Joe Strummer tribute guitar some years ago, and that was my starting point. But I replaced the 3-saddle bridge with a 6-saddle bridge because that's what Joe Strummer used. I got that relict pick guard from a place called Extreme Creations, and I even took the stickers that were on Joe Strummer's guitar and cut them into the shapes that they were worn into by the time Joe stopped playing the guitar, and affixed them to the guitar in the appropriate places. The next guitar is a Gibson Les Paul Gold Top from a couple of years ago. And the one all the way on the right is my most recent guitar. That is a Fender Stratocaster American Professional 2, and I didn't have a Strat, so I wanted a Strat, but I also couldn't resist getting it in the gorgeous Miami blue color. Really, the other thing, other than, interesting, like, reading books and stuff like that, the other leisure thing I do is I play video games. That should come as no surprise to you. And so the question is, what kind of video games do I play? And you should pause the video, guess in your mind what those might be, and then you can move on to see a screenshot of what I use to play my video games. You can see racing games are my passion, so really racing simulations, so, realistic racing games rather than arcadey racing games. And if you're interested in all the details of that racing rig, you can go to the PDF that I've provided as a resource for this lecture. So there you have it. None of this has anything to do with course content, but it gives you a little more insight into who's teaching you in the course. What will you learn about in this lesson? You'll learn about the bool data type and Boolean expressions. You'll learn about the selection control structure, which lets us make decisions in our code. You'll learn about if statements. You'll learn about switch statements. You'll learn how to implement a manual timer in Unreal. You'll learn how to build a spawner using the built-in Unreal timer system. And you'll learn how to use gameplay tags. This lecture is about Booleans, but what are Booleans? Booleans are things that can only evaluate to true or false. And Booleans are really helpful to us as we implement the selection control structure because they let us decide which code to execute. We do get a data type in C++, and it's called bool. And not surprisingly, this data type can only evaluate to true or false. So having a data type lets us declare variables of type bool, or say a function that we've written returns a bool. So it's really useful to have a Boolean data type. We also get this thing called Boolean expressions. And Boolean expressions can also only evaluate to true or false. And we build up Boolean expressions using two kinds of operators. The first kind of operator is called a logical operator. And we'll talk about three of them. The first one we'll talk about is AND. And the way AND works is if we have two Booleans and we AND them together, the only way that that Boolean expression evaluates to true is if both of those operands are also true. So true and true is true, and the other combinations, true and false, false and true, and false, are all false. The second logical operator we'll talk about is OR, and the way OR works is with two Boolean operands, the OR operator evaluates to true if one or both of the operands is true. So true or true is true, true or false is true, false or true is true. And the only way OR evaluates to false is if both operands are false. False or false is false. The third logical operator we'll talk about is actually something called a unary operator. It's called NOT. And NOT simply negates the single operand we provide to it. So not true is false, and not false is true. The other kind of operator we use to build up Boolean expressions is called the relational operator, like equal, not equal, less than or equal, greater than or equal. So these are operators that we apply to determine the relationship between two operands, and these should be more familiar to you, right? 3 less than 2 is false, 3 greater than 2 is true, and so on. So they determine the relationship between the two operands. To recap, in this lecture you learned about Booleans and how they're useful in helping us implement the selection control structure, and you also learned that C++ gives us both the bool data type and Boolean expressions. In this lecture, you'll learn how to implement the selection control structure to make decisions about which code we're going to execute using if statements. So what kind of decisions might we want to make? We might want to decide if an enemy will drop loot or not. We might want to decide if the player has leveled up. We might want to decide what menu to go to, and lots of other things. So there's lots of decisions that we make in our code, and if statements help us make those decisions. In its most basic form, the if statement has a Boolean expression. That's why we talked about Boolean expressions. It has a Boolean expression that evaluates to true or false. If the Boolean expression evaluates to true, we follow the true branch and do something as shown in this diagram. And if we follow the false branch because the Boolean expression evaluated to false, then we just don't do anything and we move forward in our code. Let's go see what this looks like in C++. Here's the code we'll start with. All I've done so far is I've provided an answer variable and I'm prompting for and getting user input. So here's my prompt: pick up the shiny thing, 1 for yes, 2 for no, and then I read in the user's answer. Down here, where we're going to print an appropriate message, is the interesting part. So we'll start by adding a basic if statement. So we say if, and then we put open and close parentheses. And in between these parentheses, we're going to put a Boolean expression, an expression that evaluates to true or false. And then we'll put curly braces for our if clause, and we'll put whatever code we want to execute if that Boolean expression is true inside the if clause. So let's handle picking up the shiny thing first. If answer is equal to 1, that's 2 equals as the relational operator, not 1 equal like that. It's 2 equals. So if the answer is 1, we'll print out a message. You have the shiny thing. Like that. So the way this will work is, I'll run it and show you. If we enter a 1, it will print out you have the shiny thing. And if we enter anything other than a 1, even 2, it doesn't say anything. So the execution checks this Boolean expression, and if it's true, it does this. And if it's false, it just goes past the if statement to the end of our main function. Now we can do something on the false branch as well. So if the Boolean expression evaluates to true, we go and we do something and then we move on in our code. And if the Boolean expression evaluates to false, we do something else and then move on in our code. Let's go see what that looks like in C++. Now we'll add an else, which will be executed for every input other than 1. So if this Boolean expression evaluates to true, we'll do this and go past the entire if statement. But if the Boolean expression is false, we'll go to this else and we'll do whatever we say to do in the body of the else statement. And they decided not to pick up the shiny thing. So now if we run our code, if we enter 1, we get you have the shiny thing. If we enter 2, we get you don't have the shiny thing. Unfortunately, the way else works is, even if they enter 3, we say you don't have the shiny thing. And while that's true, they didn't pick up the shiny thing, it's also true that they didn't give us one of the valid answers. So we should in fact tell them that they gave us an invalid answer. We also might want to have multiple alternatives, specifically more than 2 alternatives, that we evaluate in our if statement. And even though this structure I'm showing you doesn't go along with the example we're doing, you can see that we have a cascade, if you will, of if alternatives that we want to handle within our if statement. And we do those alternatives between the if and the else. We do those alternatives using something called else if. Let's go see what that looks like in our code. We need to take this piece of code and put it into an else if clause. So we only do this if they've entered 2. So we'll see how that works. As always, we make sure 1 still works. We make sure 2 works. You don't have the shiny thing. And now if I enter 3, I don't get any message at all. Now I would like to actually tell them that they've messed up. So I'll add an else here. And here I'll print out a supportive message to the user telling them in a gentle way that they didn't provide valid input. So I'll say invalid input dork. So now the way it will work is we start at the top and we work our way down. We get here, and if this Boolean expression is true, we execute this code and we go all the way to the end. If this Boolean expression is false, we drop down here and we check this Boolean expression. And if this Boolean expression is true, we do this and leave the if statement. And then finally, if this one is false also, so this one was false and this one was false, we do whatever is in the else. So let's watch that in action. 1 gives us the shiny message. 2 gives us the not shiny message. And 3, or any input other than 1 or 2, gives us the invalid input dork message. And I'll put that new line there as well. So as you can see, we've used an if all by itself. We used an if with an else. We used an if with an else if. And we used all 3. And of course, we could have more else ifs in there too. So the rule for an if statement is you need an if, no matter what. You can have 0 or more else ifs, as many as you want, including none. And you can have 0 or 1 else clause. You can omit the else clause like we did at the very beginning, or you can include it. You can't have multiple else clauses. That doesn't make any sense, but you can have 0 or 1. To recap, in this lecture you saw how we can use multiple variants of the if statement to implement the selection control structure to decide what code executes in our program. In the previous lecture, we explored how we can use multiple variants of the if statement to make decisions in our code. In this lecture, we'll use another statement, the switch statement, to make decisions in our code. Let's go take a look. We're starting with the code we ended up with last time from our if statements lecture. So we have that variable and we prompt for and get user input, except here we're not going to use an if statement to print an appropriate message. We're going to use a switch statement instead. For our switch statement, we put the switch keyword followed by parentheses, and in the parentheses we're going to put the variable that we're going to switch on. So we're going to use our selection logic on the answer variable just as we did down here in our if statement. However, within a switch statement, we put a set of cases. So starting like we did before, where we were only responding to 1 as an input, when answer is 1, we'll say you have the shiny thing. The other thing that we'll put at the end of each case is we'll put a break. And that says break out of the switch statement, go to the line after the closed curly brace for the switch statement. So if I run this code and I enter 1, it says I have the shiny thing. And if I enter anything else, it doesn't print anything. Remember, the next thing that we did when we did the if statement lecture is we added an else clause to our if. And remember, the else clause gets executed if none of the other alternatives in our selection have been executed. If none of those above the else clause have been executed, then the else clause gets executed. We have a similar thing within our switch statement, and it's called default. So default will be executed if none of the cases above default were executed. Following the same pattern we did before, we started off in the previous lecture by using the else to print out you don't have the shiny thing, and we put a break at the end of a default clause as well. And then we saw that we could do 1, and we could do 2, and then we were disappointed to see that we could also do 3, and it said you didn't have the shiny thing. So of course what we want to do is make this specific to answer having a value of 2, and then we'll add that default clause back in, but we'll print the invalid input message here, remembering our break. And now 1 works the way we expected, 2 works the way we expected, and 3 works the way we expected. And just so you don't think I'm trying to do anything crazy, 42 also works as an invalid input. So the default is the else, right? It's if none of the cases above applied in the switch statement, then the default clause gets executed if we include one. We don't have to include one, but it's generally a good idea to include a default clause in your switch statements. And that's it. We've converted our if statement structure to get the same behavior out of a switch statement, because a switch statement also gives us a way to implement the selection control structure. To recap, in this lecture, you learned how to use the switch statement to make decisions in our code, implementing the selection control structure. In this lecture, we'll look at how to implement a timer actor component. And I'm calling this a manual timer because Unreal actually has a built-in timer system that we'll learn to use very soon. But I wanted to do this example to show you both how actor components work and also to show you a compelling example of where the selection control structure is really useful in a game. Timers are also really useful in our games. So when are timers useful in our games? They're useful in timed levels, so we can decide when to end the level. They're useful when we're deciding whether or not to spawn something. They're useful for weapon cooldowns. They're useful for deciding when to increase the difficulty in the game, and lots more. So let's go look at how we can implement that timer actor component. As I've mentioned before, when we create a new class or a new script in Unreal, we actually get 2 files. We get a header file that ends with the extension .h, and we get an implementation file that ends with the file extension .cpp for C++. We'll look at the header file first for our timer, and you'll notice here that the class name is actually uTimer, not timer. When I created the script, I said I wanted it to be a timer script, and the Unreal Engine prepends a U to the class name. So the actual class name for my timer is uTimer, and you'll notice here that when I created it, I said it wanted to have actor component as its parent class. Not actor, as we've done previously, but actor component. And the reason I selected that as the parent class is because we won't add a timer as a standalone entity into our map. Instead, we'll attach timers to actors that should have a timer associated with them. Remembering that this is just an exercise in seeing how we could do a manual timer with if statements, we'll really use the built-in Unreal timer system when we need timers in our games, but this is a great example of using actor components, and it also lets us solidify our understanding of how if statements work. In our header file, so I'm in timer.h here, in our header file, I've declared an area that's private. In other words, consumers of this class can't access these variables. And I'm calling them fields here because they are variables. We declare them like variables, but they're visible throughout all the code in our class. So instead of having a variable that we have just inside a particular function, these will be available throughout our class. I have a bool variable called b running, and this variable will tell us whether the timer is currently running, and I set that to false because when I create a timer, it's not running yet. I have a bool variable called b started that I set to false, and I'll talk about why I need this additional variable soon. I have a floating point variable for the elapsed seconds that the timer has been running since it was started, and I set that to 0. And finally, I have a floating point variable for the total seconds, and that's also set to 0. So the way we use elapsed seconds and total seconds is total seconds say how long is the timer supposed to run, and for this lecture that's 3 seconds, and then elapsed seconds says how long has the timer been running since we started it. And so when elapsed seconds reaches or exceeds 3 seconds, the timer should stop. So elapsed seconds keeps track of like the running time that's accumulated since we started it, and total seconds tells us when to end. This debugging variable is not needed in this lecture, but I did use it as I was talking through in the book the full development of this class. The rest of the stuff that we put in our header file includes a constructor that we're not going to use. It includes begin play, which we will use. It includes tick component. So in the past, we've always said, should we let the actor tick? Should we call the tick function on every frame of the game? And we've always said no. But this time we're going to say yes, we actually do want to tick this timer every frame so we can update elapsed seconds. We have a getter that tells us if the timer is finished, and we need that because if we start a timer, we probably want to know when it's done. We have a getter that tells whether the timer is currently running because we may be curious about that. We have a setter, a set duration function that lets us say how many seconds we want the timer to run. And finally, we have a start function that actually starts the timer. So the structure, even though you're not yet designing your own classes, the structure of a class is in our header, we put our fields and our functions, and the fields will always be private. We'll talk about good design processes as we keep moving forward, but the Functions will be either private for internal helper functions that the class needs but doesn't want to expose to consumers of the class, and public functions like these that we've exposed to anyone who has a reference to a timer object. In our implementation file, in our constructor, here's where we say we do want to tick. I lied about begin play. We're not actually going to use it in our implementation here. In tick component, here's our first if statement. If we're currently running, and you might think we should do this if b running equal true, and that would work, but b running is a Boolean already, so if b running is true, we update our elapsed seconds, and the way we do that is we add delta time to elapsed seconds. So this is actually the same as this. Those two lines of code do exactly the same thing, but you'll see most experienced programmers just using this syntactic shortcut to add delta time to elapsed seconds. So what is delta time? Delta time is the amount of time it's been since the last time tick component was called. So this gets called every frame, but as your frames per second change in your game, delta time would change. Sometimes it would be larger, sometimes it would be smaller. So this gives us a good way to update no matter what our frame rate is or how it's fluctuating. So if we're currently running, we add delta time, and then we check to see if we're greater than or equal to total seconds, and if we are, we just stop running. Now you might think you could check equal here, but that's a really bad idea, because if elapsed seconds was 2.99 on one frame, and then it was 3.01 on the next frame, elapsed seconds would never equal total seconds, and our timer would never finish. So we always want to check greater than or equal to when we're trying to reach a certain point, but if we exceed that point, that also means we've reached it. Our isFinished getter tells us whether the timer is finished. And here's why we need that be started field. Because if we just said return not be running, as soon as we created the timer, we would say it was finished because it's not running right now. So we want to only say the timer is finished if it's not running anymore, but we did start it at some point. Is running is really easy. We just return be running. Setting the duration, we do some error checking in here. So this is why it's really good not to just let a consumer of the class directly access total seconds, which is why we made it private. We'll say here we won't add time if it's running already, and we won't set a negative duration because that doesn't make any sense for a timer. And starting the timer is really straightforward. We make sure we have a valid duration, and if we do, we start it, we say it's running, and we set elapsed seconds to 0. Which, by the way, that debugging code you see sprinkled throughout, when I first implemented the timer, I did not have that line of code, and it wasn't working. And if you want to, you can go check out the selection chapter of the book to see how I discovered that and how I fixed it. Well, how I fixed it was I put this line of code right where you see it. In this lecture, we learned how we could implement a timer actor component using the selection control structure. In the previous lecture, we learned how we could implement a timer actor component. In this lecture, we'll see how we can test that timer actor component. Okay, so that's the timer class, but remember it's an actor component. And so we're going to want to attach it to an actor. And that's one of the reasons I wanted to do this manual timers lecture, even if we're going to use the Unreal timer system later, because this shows us how we can work with actor components. And we're going to do that with our timer test actor. So here in the header file for our timer test actor, which you can see is a child of the actor class, and it's called a timer test. I have some private fields here. I have uTimer for my timer, but that asterisk right there is something new for us. So that asterisk says this timer field is actually a pointer to a uTimer object. It's not an actual uTimer object, it's a pointer to one. And we'll see why we need that later, and we'll also discuss pointers later. But you can just think of this variable as holding the address of the object, not the object. And we'll have a couple of syntactic things to do as we deal with pointers, but we'll explore them in more depth before we're done with the entire specialization. fDateTime is a built-in Unreal type for date and time. So we've left the rest of this, the public constructor, the protected begin play, and the public tick, we've left all those the way they were when we created the script. In the implementation file for the timer test script, we're going to let the timer test script tick on begin play. You can ignore those red squigglies on check. Sometimes Visual Studio gets confused, right? Usually in a console app, for example, red squigglies would mean this thing will not compile. But when Visual Studio is attached to Unreal, sometimes it will mark things as errors and they're not. So this is not an error, that particular red squiggly. Okay, so this part here is about using an actor component, one of the reasons we're doing this video. So the comment says add, check, and register the timer component. So first, we take our field and we want to put a new pointer to an uTimer object into that field. We don't use our typical form for constructing an object in Unreal. Instead, we say new object. We want a new object, and we want it to be of type uTimer. And this says who's going to own this new object that's getting created. And for us, it's going to be timer test. And this whole thing returns a pointer to a uTimer object. And that's why we need timer to be a pointer to a uTimer, not just a uTimer. So we have to work within the constraints of how Unreal works, and Unreal wants to give us pointers, so we'll just use pointers. This next line of code that is confusing Visual Studio is called an assert. When we put check, we're making an assertion, and if our assertion is false, our game will crash and it'll stop right here. And so we want to check to make sure timer, that pointer that just got returned to us, is, sorry about that, is not equal to a null pointer. In other words, this did not fail, it succeeded and gave us a pointer to a uTimer object. So this is just making sure that happened fine before we actually start trying to use the timer field. This next line has a couple of things. First of all, we're calling a register component function, and we'll talk about why we do that in a moment. But what you've learned for classes and objects so far is you would have expected this to be timer dot register component using the dot notation. We use the dot notation when we have an actual object, not a pointer to an object. So to actually call a function on a pointer to an object, it's most convenient to use this arrow notation. And so we're doing essentially the same thing, but there's one more step along the way. We're actually doing what's called dereferencing the pointer to get access to the actual object, and then using dot notation to call the function, but using this arrow notation is just cleaner. But why do we have to call this register component function at all? The reason is, this is the chapter of the book, the reason is that the Unreal Engine components documentation tells us in order for actor components to update each frame, which we need our timer to do, and affect the scene, the engine must register them. So whenever you add an actor component that you want to tick every frame and have some effect, you need to register it. Now, we set the duration for that timer to 3 seconds, and we tell the timer to start. The rest of this stuff is just keeping track of how long the timer ran, including down here when we check whether it's finished in our tick function in the timer test. So I'll let you just go read the chapter in the book that does this. It's just calculating the elapsed time each time we run the timer. So I'll compile just to convince you that those red squigglies don't actually prohibit us from compiling, and I succeeded here. So we'll come over to the Unreal Editor and select the output log so we can watch as the timer goes along running approximately every 3 seconds. Now this 2.934 at the very beginning is a side effect of when I get the current time and when I tell the timer to start. And as you can see, it's running every 3 seconds as expected. To recap, in this lecture we saw how we could test the timer actor component that we implemented in the previous lecture. In the next 2 lectures, we'll see how to use the selection control structure in the Unreal Engine timer system to build a spawner. In this lecture, we'll build the blueprints that we're going to spawn, and we'll also learn how the uProperty macro works. I've already implemented all the code for the required functionality for this lecture, but I'm going to show you how I've done that, and we'll start with the teddy bears dying after 10 seconds. I'm just going to run the game to show that happening. And as you can see, I placed some teddy bears into the map, and we just watch them bounce until their 10 seconds timer ends and they disappear. So this was one line of code to actually make this happen. So over here in the teddy bear implementation file, I changed can ever tick to false because we don't need it to tick. But in the begin play function, I set the lifespan to 10 seconds. So we can set a lifespan for any actor we've got, and I set this to 10 seconds. So after 10 seconds expires, Unreal destroys the teddy bear. That was the easy part. The harder part is adding the teddy bear spawner. Let's take a look at the header file first for the teddy bear spawner. And I have a pound include for the teddybear.h here, and I'll show you why in a moment. So we scroll down and I have some constants that I want to use for the spawning process. I have a min spawn delay seconds of 1 second and a max spawn delay seconds of 2 seconds. So we'll do a spawn somewhere between every second and every 2 seconds. We'll change the spawn delay each time we complete a spawn so that we don't just spawn at a regular interval. We have some randomness to that. I've also added a min spawn Y and a max spawn Y so that we're going to just be spawning our teddy bears inside the screen when we spawn them. And I have a min spawn Z and a max spawn Z for exactly the same reason. I'm not spawning down at the bottom of the screen. That's why my min spawn Z is a 0. But I'm going to spawn up as high as 100 in our map. So this should look somewhat familiar to you. We've seen constants and we've seen floats and we've seen variable names and initializing those variables with the braced initializers. I also have a start spawn timer function, but you'll notice up here I've said that that function and all these constants are private, so they're only accessible inside the teddy bear spawner. We'll talk about class design later, and we'll talk about why this information hiding is a great idea. I know we've addressed information hiding when we talked about classes and objects, but this is a good idea to keep all these things private because they're only needed inside the teddy bear spawner. A very new thing is this uProperty stuff. So we're marking this field and this field and this field as unreal properties using the uProperty macro. So what we've put in here are the uProperty macro. This edit anywhere is called a property specifier. And I will tell you as I talk about these items or elements that we put inside the uProperty macro, the best thing to do is to go explore the documentation for uProperty if you decide to want to use it in a different way from the way we're using it here. But here, I'm setting this uProperty as edit anywhere, and then I'm providing a metadata specifier, which basically says for this property, you can only populate a list. We'll see that we'll have a populated list of classes that we can use to populate this particular property. So this says only those classes that are either a teddy bear or a child class of a teddy bear. Remember, we pick parent classes, or when we create blueprints, we say create a blueprint class from this C++ class, and that's what I did here. But I did all of them off of a teddy bear, all the blueprints we have for our teddy bears. And so when we populate a list, which I promise I'll show you soon, we will only include those classes in the list. And we can also say, give us a particular category that we can look at for these properties. So you might, in a larger game, you might have a bunch of uProperties and a bunch of different classes, and they would be different categories of classes you want to include. And so this is a way to set it up so that in our blueprint editor, we can actually have things categorized. Finally, I have a field, because this will be visible throughout the teddy bear spawner class. I have a field that I've called uGreenTeddyBear. Green teddy bear because it's a green teddy bear. I put U in front of it because I wanted to do that. It's actually a U class, which is what blueprints are. And the data type, I said, is it's a subclass of a teddy bear. So this is sort of the C# part of saying I only want teddy bears. Here I'm saying the uGreenTeddyBear is going to be a subclass of the A teddy bear class. So I have these three properties for green, purple, and yellow teddy bears so that I can randomly pick which one to spawn when it's time to spawn it. Let's see how this property stuff works in the editor. So here in the editor, if I navigate to my teddy bear spawner blueprint and double click it to open the blueprint editor, you'll see here under teddy bear blueprints, I have my uGreenTeddyBear field, my uPurple teddy bear field, and my uYellow teddy bear field. And these are appearing here because I marked them as uProperties. And they're appearing here under the teddy bear blueprints heading because I said that's what category they belong to. I can select over here on the right for my uGreenTeddyBear, I can select the green teddy bear blueprint I created from my A teddy bear C++ script, or my purple teddy bear blueprint, or my yellow teddy bear blueprint, or my base class. And I'm not going to pick my base class, I'm going to just pick the green teddy bear. And as you can see, I populated each of these things. So using the uProperty macro makes it so we can populate these fields in the blueprint editor rather than trying to do it within our code. There is a way to do it within our code, but we're going to do it within the blueprint editor instead. So I did change this, so I'll compile and save it. In this lecture, we learned how we can build an actor with a set lifespan, and we also learned how the uProperty macro works. In the previous lecture, we built the blueprints we're going to spawn, and we also learned how the uProperty macro works. In this lecture, we'll use the selection control structure and the Unreal Engine timer system to actually do the spawning. And we'll go back to the teddy bear spawner code, and the other stuff in our header file are the default things we typically get. So in our implementation file, in our begin play function, we call our start spawn timer function, which we'll look at soon. And in our spawn teddy bear function, we declare a variable for the teddy bear we're going to spawn. It's also a T subclass of a teddy bear. We generate a random number, 0, 1, or 2 inclusive. And if that number is 1, we set spawn teddy bear to the green one. If it's 1, we set it to the purple one. Otherwise, we know that teddy bear number is 2, so we set it to the yellow one. So here's an instance of using an if else to do something interesting in our game, to randomly select which teddy bear blueprint we're going to spawn into the map. Next, we generate a random spawn location. So f vector is a floating point vector, a three-dimensional vector, and we'll declare a spawn location variable that is an f vector, and I read the f vector documentation to determine that I wanted to use 0 here in the constructor to set x, y, and z to 0. You know I want x to be 0 because we're making 2D games, but setting y and z to 0 initially also makes a lot of sense. I also learned in the f vector documentation that the f vector class exposes a set component for axis function. And here is that function in the f vector documentation, and if I click on it, I see that I provide 2 arguments when I call this function. I provide which axis I want to set, x, y, or z, and I provide the value as a floating point number that I want to set that component to. So this e-axis thing looks a little strange to us. If I click on it, we can see that e-axis is something called an enumeration, which we haven't explored yet. So an enumeration is a data type that can only have specific values. So if I have something that is of the e-axis data type, it can only have the value none, x, y, or z. So when I come back to my code, I'm saying here that the axis that I want to set is the y-axis, and I put the name of the enumeration, and then colon, colon, and then the value I want to use. So if I tried to use something like e-axis Bob here, this won't compile. The IntelliSense tells us, right, that it's none x, y, or z. And so the enumeration makes it so I can't provide an invalid value. I can mistakenly try to change the x-axis here instead, but I can only use those possible values in the e-axis enumeration. So I'm saying I want to change y, and now I call rand range, and I say min spawn y and max spawn y. So I will be spawning at a random location in Y between min spawn Y and max spawn Y. I do the same thing to set my Z axis between min spawn Z and max spawn Z. So at this point in my code, spawn location has a random Y and Z in the ranges I set with those constants in the header file, and X is 0. To spawn the teddy bear, I first call getWorld. So the getWorld function is a getter for the cached world pointer, which basically is a pointer to the world in which this actor exists. And by world, we mean map. So first, we get a pointer to the map that this teddy bear spawner is placed in. Then we call spawn actor, and spawn actor is a templated version of spawn actor that lets us tell the location and rotation as well as the class type that we want to spawn via the template type. In other words, we put the class we're trying to spawn here, and because all of our blueprints were generated from the A Teddy Bear C++ script, this will work great for all our blueprints. We say what we want to spawn, and this is the teddy bear that we generated up here. We say where we want to spawn it, which is this random location that we set up here. And I read the documentation to figure out how to actually do it with no rotation. Once we've spawned a teddy bear, we start the spawn timer again. Before we go look at how the start spawn timer function is implemented, I feel like I might have misled you a little because I was so excited to show you how enumerations work. So this is certainly one way that we can set the Y and Z components of our spawn location variable. However, there is in fact an easier way. I'll comment out those, and I'll show you that I can also directly say spawn location dot Y is equal to this and spawn location dot Z is equal to this. And that's definitely the more common way to change the Y and Z components of our F vector, but I was excited to show you about enumerations, so there you go. You learned about enumerations, but this is the more common way to do it. Okay, let's finally look at how the set spawn timer function is implemented. So here's how we set our spawn timer. First, I'm going to generate a floating point number that is a random float between min spawn delay seconds and max spawn delay seconds. So at this point, timer duration is holding how long we want the spawn timer to run, somewhere between 1 second and 2 seconds. Next, I'm declaring a variable called timer of data type fTimerHandle. And the way I learned I needed an fTimerHandle variable was because I read the documentation for how to actually set a timer. I start by calling the getWorldTimerManager function, which gives me the timer instance from the actor's world. So we're using the built-in Unreal Timer Cistern, and this gives us the timer manager that we need for this particular map, the map in which the actor lives. So this returns an fTimerManager, and if we click on fTimerManager, we discover that the fTimerManager object that we get back has a number of set timer functions. In fact, it has 6 different functions for set timer, we're actually going to use the last overload, and it turns out that the last two parameters here are optional, so we don't need them. But this first parameter that we need to provide, an argument in our code, needs to be an ftimer handle. So the first argument I provide here is that variable that I declared on the previous line. Next, we say that we want to use the timer here in this particular object, and then we provide the address of a function that we want to get called when the timer expires. Not just the function name, but the address of the function. And finally, we say how long do we want the timer to run, and that's the timer duration that we generated right here. So what will happen is this starts the timer. When the timer finishes, after timer duration, it will call our spawn teddy bear function, which we already looked at is right here. And that function will pick a teddy bear to spawn, generate the random spawn location, spawn the teddy bear, and start the timer again. Back in our game, I will need to actually add the spawner to the map to make it work. And once I've done that, I can just Alt-P, and we can see that we're spawning new teddy bears every 1 to 2 seconds. I know we got a few yellows in a row. That's just how it works. And as you can see, the spawner is also working properly, spawning new teddy bears into the map. To recap, in this lecture we saw how to use the selection control structure in the Unreal Engine timer system to spawn our blueprints. In this lecture, we'll look at how we can use the selection control structure in conjunction with something called gameplay tags. So this game is identical to the spawning teddies game, except that we're going to destroy teddy bears periodically as well. And the mechanism that we're going to use to destroy teddy bears is something called gameplay tags. So it's really useful to be able to tag particular blueprints or actors in our map with a label or a tag so that we can go find them later is one of the most common uses of tags. So we can actually apply multiple tags to each blueprint if we want, but we're only going to use one tag per blueprint here. The first thing we need to do is actually add a gameplay tag to apply to those blueprints. So we go to Edit, Project Settings, and we select Gameplay Tags, and I've actually already added a tag called Destructible to my game. The way you add a tag is you click here and you type in the tag, and then you add the new tag, and then the new tag is included in your game. So I already did that. I added a tag, but this is our first step. We add a tag, one or more tags, to our gameplay tag list here in Project Settings. That makes that destructible tag available for application to any blueprint. So if I open up the blueprint editor for the green teddy bear blueprint, and over here in details, I scroll down, you can see under the actor section, I have tags, and right now I have applied one tag to this blueprint. I could add multiple tags, as I said, but I only need one. And when I go to add an element, I click here and I type in the name of the tag that I want to add. Typically we won't add none as a tag. I would type in the tag that I wanted to add. But I don't actually want two tags on this blueprint, so I've just gotten rid of that. But you have to remember the exact string you used for the tag to actually type it in again here. But now that I've done this, the green teddy bear blueprint now has the destructible tag attached to that blueprint. And of course I did that to the purple teddy bear and the yellow teddy bear as well. So where do we actually do this destruction stuff? Well, we're going to use something new. We're going to use something called a game mode. So let's look at the Unreal documentation. So a game mode is a mechanism that we can use to set some of the rules of our game. We actually could have set up the spawning of our teddy bears in a game mode as well, but I actually wanted to have that as an actor so that I could sort of add multiple spawn points if I wanted to, and not generate a random spawn location, then actually just spawn things out of those spawn points. So I wanted an actor for my spawner, but we'll use a game mode for our destroyer. And we'll continue to use game modes as we move forward in the specialization when it's appropriate for us to do so. So in this lecture, I'm going to use a game mode to implement the destruction functionality. Let's go take a look at that game mode. So I called this a destroyer game mode, and it will destroy a destructible tagged actor every second. I have a private function called start destroy timer that should look familiar to you, because remember I had a private function called start spawn timer in my teddy bear spawner class. And I have a function that we can call to destroy a destructible. And we'll see how that works once we get into the implementation file of our destroyer game mode. And this is just the default begin play. In my implementation file, on begin play, I start my destroy timer, much like I started the spawn timer before. We'll come back to destroying the destructible. I just wanted to show you this function looks a lot like the start spawn timer, except this time we're just doing it. The comment said every second. I'll go fix that. It's every 3 seconds. But this is the same thing. We're not doing it randomly this time. We're just doing it every 3 seconds consistently. So let me fix this comment. Because we always want our comments to actually match what the code does, otherwise they're misleading. So the interesting stuff for this particular lecture is using tags. So we say here, we're going to destroy destructible. And just like in our spawn timer, we provided an address of spawn a teddy bear here, the spawn teddy bear function. Here, when our timer goes off, we're going to call our destroy destructible function. Now this uses some new stuff that we haven't seen before, but we are going to have tagged actors. And really what we're going to have is we're going to have an array. We're going to talk about arrays soon, but I really wanted to use tagging here. But our tagged actors variable will be a T array of pointers, remember that asterisk notation, of pointers to actors. So an array is just a way to hold multiple things. So we're going to go find, on the next line of code, we're going to go find all the actors that are in the map with our destructible tag, and we need to store them somewhere. And there could be more than one of them. There may not be, but there could be more than one of them. So we need a way to store multiple pointers to actors in a single variable. And so the way we're doing it is with the T array. I know I'm waving my hands a lot, so just sort of squint at that. That's not really the important piece here. The important piece here is the next line of code. So, uGameplay statics, the class, has a get all actors with tag function right here. And when we call this, we need to provide a world context object, which we can get with a call to the getWorld function like we have before. We provide the tag that we're looking for. So that's destructible. Again, you need to spell this correctly and have it exactly match your tag. And we also provide it with the T array of AA actor pointers that it can populate with all the actors it finds. And that's why tagged actors is declared to be of this data type. There is a remark here that's important, and that remark is this is a slow operation. Finding all the actors in a map with a particular tag is slow, so we don't want to do it on every frame. We aren't doing it on every frame. We're actually only calling destroy destructible every 3 seconds. So we're willing to eat the inefficiency of doing this because we're not doing it regularly. Then we check to see if we got at least one, and if we got at least one, then the very first one, and we'll see why we use 0 when we talk about arrays, the very first tagged actor, we call the destroy function on it, and it destroys that actor. And then we start our destroy timer again, so that we can do this again 3 seconds from now. So this part right here is the piece that tags make really useful for us, because by tagging our actors, our blueprints, we can go find them in the map when we want to do something, and this time we just want to destroy one of them. So finally, if we actually run the game, we'll see teddy bears spawning into the map, and then every 3 seconds we're going to try to find all the tagged actors, and then we'll destroy one of them. So I started the game and we spawned a purple one and it disappeared immediately, and now we got rid of a green one and we're going to get rid of that green one. So if you watch, you'll see that we are destroying teddy bears periodically as we run the game. There's finally a purple teddy bear as well. The last thing I'm going to mention is I set a different game mode, destroyer game mode, that I wanted to use here. And I actually need to go to Edit Project Settings, and under Maps and Modes, which we've used before to set these maps, I need to set the default game mode to the Destroyer game mode that I wrote. Otherwise, that game mode just doesn't get used when I run the game. And that's how we use gameplay tags in a useful way in our games. To recap, in this lecture we learned that we can add tags to blueprints so that we can find them and process them based on their tags. What will you learn about in this lesson? You'll learn about action mappings and axis mappings in Unreal. You'll learn how to process mouse input. You'll learn how to process keyboard input. And you'll learn how to process gamepad input. In this lecture, you'll learn how to use the mouse location in your Unreal games. So let's go take a look. In this lecture, we'll create 2 new scripts, and we'll use the mouse input game mode base script that Unreal automatically provided to us when we created this project, because we're going to write a custom game mode like we've done before. The other 2 scripts I've created here are a character pawn and a character player controller. So as I mentioned, the big idea is the pawn is the avatar for the player in the game, and the player controller will possess the pawn to make it bend to its will, if you will. So we've got the pawn to represent the player in the game, and then the player controller will control how the pawn behaves. Before we look at those 3 scripts, I'm going to navigate to the blueprints that I have in the game. So I have turned the character pawn script into a blueprint, and I gave it a static mesh representation so we can see it in the game. And I turned the character player controller into a blueprint as well. So I've converted those two scripts to blueprints. We'll look at our custom game mode base for this project first. So I've added a constructor here. This doesn't come for free when we have the game mode base as the default that gets created by Unreal. So we need to add a constructor for it. And here's where I do some serious work. So what we need to do here in our custom game mode is we need to set up what the default pawn is in the game and what the player controller is that controls that pawn. Because I have these as blueprints, I'm going to use this FObjectFinder class. That's a templated class, so we say what kind of object are we looking for, and blueprint classes are of the data type U class, and then I tell it what I want to name this variable, and then I have this really interesting stuff here that says where can I find that blueprint class definition. Back in the editor, the way we get a location of a blueprint is we right click on the blueprint and we say copy reference. Now I'm going to copy that reference into the code even though it's not quite correct for what we need, and I'll show you how we can change it. So I'll just find a blank space here to put it. So if I Control V now, I actually have a reference to the blueprint itself, not the blueprint class. And I want a reference to the blueprint class. So I take what I got here and I put it between the double quotes here, and the two changes I make are I changed blueprint to class and I put _C at the end because that's what Unreal does to name the blueprint class that goes along with this blueprint. So I want to load the class here, so that's what I'm doing. Next, the FObjectFinder class has an object property that will tell us the object for the asset that was loaded. And I'm checking here to make sure that's not a null pointer. If trying to load this pawn class fails, then pawnClass.object will be null, and I better not do anything with it. So this is my safety check to make sure that worked properly. And if it's not null, finally, I can set the default pawn class, the class of the default pawn in my game, to pawnClass.object. I do a very similar thing for the player controller. I turned it into a blueprint, so I use this line of code to go find the class associated with that blueprint. I make sure that I didn't get a null pointer, and as long as I didn't get a null pointer, I set the player controller class to be controllerClass.object. So by doing this in my custom game mode, what will happen is when the game starts, Unreal will automatically possess the default pawn class with the player controller class. It will also place that default pawn at player start, which is right here. I've set it to 0, 0, 0, so it will put it right in the middle of the screen for me. Remember, if we change the game mode, we need to go to Edit, Project Settings, Maps and Modes, and here we need to set our default game mode. And we're using the custom game mode that I was just working on. And that's an important step. If you forget to do that, and you did all that work I just did, if you forget to do that, then when you run your game, you'll just end up with a sphere in the center and you'll wonder why your character isn't showing up there. And the reason is, the most common reason is, that you didn't remember to change the game mode. Okay, let's see how the pawn class works next. So here we are in the character pawn header file, and these are default things we get. We get a constructor, we get a begin play function, we get a tick function, we get a setup player input component function, because sometimes you can set it up so the pawn handles all its own input processing. It's not possessed by a player controller. I'm going to consistently throughout the specialization just use a player controller to possess the pawn. Or a different kind of controller. If I set it up so that it has artificial intelligence, it won't be a player controller, it'll be an AI controller, but something will possess all my pawns. So we get this function by default, but I'm not going to use it. I did, however, add a function that will let a consumer of this class call the setLocation function so that I can move the pawn to a different location. The way I move a pawn to a different location is I call this function setActorLocation, and I do it with location. And because a pawn is a special kind of actor, it just moves the pawn to the provided location. The most interesting stuff is in our character player controller script. Here in the header file, I've added a player tick function, and I need that because I'm going to make the pawn follow the mouse location on every frame. And so I need to tick every frame to do that. It's called player tick here in a player controller rather than tick like we've seen in pawns and actors, but it does the same thing. So in player tick, I do a number of different things. The tricky part is the mouse is in screen coordinates. It's just this flat plane, right, that we move the mouse along, but it's not in the game world, it's just on our screen. To get a world location so we can actually make our character follow the mouse, we need to convert the screen location that the mouse is on into the world location where we want the character. The way we do that is we use the dproject mouse position to world function that appears in the player controller class. And here's the documentation for that. It says it converts the current mouse 2D position to a world space 3D position and direction. We don't really care about the direction here in our 2D games, but in a 3D game, you would care about the direction as well. So we provide an F vector for the world location and an F vector for the world direction when we call this dproject mouse position to world function, and that's why I declared these two variables before I call the function. So now, after I call the function, when I get to line 23 here, world location is the location in the 3D world that corresponds to the location of the mouse in the 2D space of the screen. Now we want to move our character to that location, but before we do, I want to set world location.x to 0. Remember, we're keeping everything on the YZ plane, so I'm going to move the pawn to stay in the YZ plane. How do I actually get the pawn? Well, I call the getPawn function, and that gets the pawn that is possessed by this player controller. I will say that that actually returns an A pawn pointer, and because I need to call a function on an A character pawn, I need to typecast the results of that function call to be an A character pawn pointer, and that works because an A character pawn is a special kind of A pawn because I picked pawn as the parent when I created this script, and I put that into a variable called character pawn. Again, for safety, I make sure that that getPawn function worked fine, by making sure character pawn is not a null pointer. And if it's not, I can now say on that character pawn pointer, call the function. Remember, this arrow notation is what we use if we need to call a function on a pointer to an object rather than the object itself. And then I call that set location function that I showed you earlier, and I provide the world location that I extracted from the mouse and set to the YZ plane. So back in the editor, I can now run my game, and I have this character. So Peak Game Studios actually built a number of games for the Pikes Peak Library District to use to teach fourth graders about Colorado history. And that was a 2D Flash game, but my 3D character modeler turned those characters into 3D models that we can use here. So this is one of the characters from that game. And as you can see, she follows the mouse around as I move the mouse around. Unfortunately, if I drag the mouse outside the screen, she leaves the screen as well, including top and bottom as well, of course. And there may be some games where we want to actually keep the player in the screen, and we'll address that particular issue in the next lecture. So this is all the code and all the setup to make our character follow the mouse around the screen. To recap, in this lecture you learned how to retrieve and use the mouse location in your Unreal games. The title of this lecture comes from a song by one of my favorite groups of all time, The Clash. So if you've never heard of The Clash or you've never checked them out, pause this video, go check out The Clash, and then come back. In this lecture, we'll learn how to clamp the character's location so the character stays fully within the bounds of the screen. More generally, we use the term clamp when we want to keep a particular value within a range of values or a set of values. To support clamping our character into the screen, I've added some constants for the screen. So we put them in a namespace called screen constants. The way I generated this particular script is over in Unreal, I created a new script with none as its parent, and then I added the code I wanted here and deleted some of the code that was in the default script that was provided. So in our header file, I've got a new namespace here. We've used namespaces before, but this time we're creating our own. And I'm declaring 4 constants for the left, right, top, and bottom edges of the screen. I will say that there's certainly a way to calculate those boundaries using characteristics of the camera and so on, but we're just going to set the constants because I know what the numbers are, and this will be fine for us. So we've seen const and float and variable names or constant names before, but we've never seen this extern keyword before. Here's how it works. Constants in C++ have internal linkage by default. And what that means is those constants are only visible within this translation unit, not other translation units. So other translation units are loosely, although not precisely, the other implementation files in our project. And we want these constants to be visible from other implementation files. Specifically, we want them visible from the character pawns implementation file. So we need to mark them as extern for external so that other translation units can access those constants. The implementation file for the screen constants just gives values to each of those constants. So this will be useful to the character pawn to know where the left, right, top, and bottom edges of the screen are. Over in the character pawn header file, I've declared some constants. for the half width and half height of the character that we're using, and a vertical offset that I'll talk about when we get there. So the way I actually figured out the half width and half height for this character is I went to the actual static mesh and I opened up the static mesh editor, and over here on the left it tells us the approximate size is 6. I know that's the depth by 25. I know that's the width by 32, which is the height. So this is sort of a rough way to get the size of the mesh. We could certainly, if we replaced the simple collision that was automatically added when we imported the mesh, if we removed that and added a capsule collider, we could access information about the height and width of that capsule collider, but that's overkill for what we're trying to do here, so we'll just use this information instead. So let's move to the implementation file for the character pawn, and all our work will be in the set location function. Recall last time all this function had was this one line of code, and I want to add some more lines of code to actually keep the character in the screen. I will say, because I'm using these constants from the screen constants namespace, I had to add a pound include for the header file for those screen constants. So if you forget to do this and you try to compile, you get a number of compilation errors. The first one is the trigger for the rest of them, and it says screen constants is not a class or namespace name. So whenever you see that error message, your first thought should be, I forgot a pound include. Okay, so I've pound included screen constants, and Visual Studio takes a while to catch up to me, realizing that I've done that. But I'm going to use the clamp function in the fmath class to clamp location y so that it falls between a minimum of left plus half width. So you should think about this. If I'm on the left hand side of the screen, I have my location on the origin or the center of my model, and mine is approximately in the center of my model. So the left side of where I should be able to move my character is left plus half the character width. And that will make it so the left side can't go past the left edge of the screen. Similarly, I make the maximum the right hand side minus half width, and I hand in the location I'm trying to move in. It makes sure it stays between these bounds, and I put that into location Y. I do something similar with Z, except that you'll see I'm using bottom plus half height plus vertical offset, and top minus half height minus vertical offset. And once we've clamped Y and Z to be within the screen, we set the actor location. But why do I need this vertical offset thing? So let me change it to 0, and I'll show you what happens after I compile, of course. When I run my game, my character follows the mouse around. The character clamps properly on the left and right, but if you look carefully, I can actually move part of her hat above the top, and I can move, she has black shoes on, I can move her shoes down out of the bottom. I will be honest, I don't really know why this is happening. I checked the simple collision that was imported, and it seems reasonably tight around the static mesh and everything, so it's not clear to me what's going on here, but I'm just going to force this to work properly by figuring out how to keep it in the screen on the top and bottom. That's a little unsatisfying to me, I will freely confess. I'd like to make this to be perfect, but since at this point anyway, I only have a single character, I can just figure out what this offset is and make it work in my game just fine. And although I strongly encourage game developers to try to figure out the cause of every problem that occurs and fix it in the most robust and elegant way possible, you've got to understand that there are certainly places in games where you decide that the time or the cost, or time is money, so the time and cost of chasing down a problem isn't worth it. And you just say, well, I'm going to fudge it and make it so it works fine. Obviously, horizontally still works fine, but vertically she hits the very top of the screen and the very bottom of the screen as well. So while I don't encourage people to just put those fudge factors or kludges into their games, sometimes. To recap, in this lecture you learned how to clamp the pawn's location so it stays in the screen. In this lecture, you'll learn how to use action mappings to process mouse button input in your Unreal games. We'll start with our project from the previous lecture, and the first thing we'll do is we'll add the input mapping that we need to process input. We go to Edit Project Settings and select Input on the left, and we have two kinds of input mappings that we use here. We have action mappings and we have axis mappings. So action mappings are for discrete events, a button press or a button release, something that happens once instantaneously. Axis mappings are used for continuous input, like using the WASD keys to control a character or something like that. So we don't need axis mappings in this lecture, though we will need them when we start doing keyboard input, but we do need one action mapping. We want to destroy our character when the left mouse button is pressed. So an action mapping is the correct choice here. So I will add an action mapping. And sometimes you'll have it show up like this and you'll need to expand with that little left arrow. And I'll say destroy character. Now it's important that you remember exactly what you type here for the name of this action mapping, because you're going to need to use it inside the C++ code. It is also sometimes the case that it shows up like this when you add it, and so you need to expand it. And right now there's no key binding to this particular action mapping. The way we add a key binding is we click this drop down and we can pick which device we're using. In this particular game we're using the mouse, and we want the left mouse button. So now we've mapped the left mouse button to the destroy character action. We've added that action mapping to our game. The next thing we do is we add some code to our character player controller script. We need to add two functions to this script. The first one is the setup input component function, which, as this comment says, is what we use to bind functionality to input to make it so our code can respond to that action mapping. The other thing we need to add is a function that destroys the character pawn, the function that will actually get executed when that action mapping occurs. In our implementation file, first we check that our input component field is not a null pointer, and we are supposed to automatically get a pointer to a uInput component object when we start up our player controller, that should be initialized. So this is just a safety check to make sure that we did in fact get that pointer. If we did get that pointer, we want to use our pointer to that uInput component object to call. Remember this notation, the arrow notation, when we're calling a function from a pointed to object or from a pointer. And we want to use the bind action function. The first thing we do is we provide the name of the action mapping we're trying to bind behavior to. And this is why you need to remember how you actually named that action mapping. The next thing we provide is what event on that mapping do we want to respond to. So if we look at the eInput event enumeration, we can see that we can respond to a pressed input event. For us, on the left mouse button, we can respond to it to being pressed. We can respond to it being released. We can respond to double clicks on it. There are a variety of different input events we can respond to on this particular mapping. And I know I got really excited when we were responding teddies to show you how we could use an enumeration when we were setting the spawn location. And then I admitted we didn't really need the enumeration there, but all that stuff that I talked about for enumerations back then applies here for using the enumeration. The third argument says this player controller is the one that's going to respond to the action occurring. And finally, we have to say which function should we call to respond. And we don't provide just the function name, we actually provide a pointer to the function. So we've spent time talking about how variables are stored in memory, and we haven't really talked about the fact that functions, the executable binary instructions, are also stored in memory. And so we can provide a pointer to the function, and the Unreal Engine will know to go to that memory address to start executing the function. So that's how address of works for functions. And so we're telling it, if this occurs, if the left mouse button is pressed on the action mapping called destroy character, the engine should call the destroy character pawn function. The destroy character pawn function is pretty straightforward. We get a reference to the pawn that is currently possessed by this player controller, and we've already seen this code above when we make the pawn follow the mouse on player tick. And then once we get access to the character pawn, we just tell it to destroy itself. And that destroys the pawn that's possessed by the player controller. So back in the editor, when we run our game, we move the character around like we used to, but if I press the left mouse button, then the character disappears. So that's how we can use an action mapping to respond to a discrete input event in our game. To recap, in this lecture you learned how to use action mappings to process mouse button input in your Unreal games. Last time, we finished up with mouse input processing in our Unreal games. In this lecture, we'll learn how to use action and axis mappings to process keyboard input in our Unreal games. We'll start by setting up our input mappings. So edit project settings. And I've already done it. So I've set up one action mapping for a discrete input event. Pressing the spacebar will destroy the miner. We have a miner as a character in this particular game. And remember, axis mappings are for continuous input, like for movement. And that's how I've set these up, so we can move horizontally using the right and left or D and A keys or some combination of those, and we can move vertically using up, down, or WS. I want to point out in the horizontal axis mapping that I've set the right key and the D key to have a scale of +1, and I've set the left key and the A key to have a scale of -1. And that's how we'll end up moving to the right on right or D, positive along the y-axis, and how we'll end up moving left when we use left or A, going negative on the y-axis. So this is the setup of the action mapping to destroy the miner like we were destroying our character last time with the left mouse button, and axis mapping so we can provide keyboard input. As you can see, we have our typical game mode that I've customized in the usual way with the pawn and the controller. We have a miner pawn and we have a miner player controller for our C++ scripts. So let's go take a look at the miner pawn first. In the header file for the miner pawn, I have some private constants for half collision width and half collision height like we've seen before. I did need another kludge factor in height and I just added it into the number there, but we need this constant as well. We need to know the speed of the pawn. How far can it move per frame? So this is the speed if we have movement input. We didn't need that when we were following the mouse around. There was sort of no speed at which we moved. We just moved to the mouse location on every frame. But here you can think more of we're pushing the miner around with our keyboard input, so we have to know how far the miner moves when it has keyboard input, and that's what this gives us. Scrolling past the default stuff, we have a move horizontally function that will move the miner horizontally, no surprise, and move vertically to move the pawn vertically. In the implementation file for the pawn, we are going to tick every frame, and I'm going to move past the tick function and then we'll come back to it. So when the move horizontally function gets called, what we do is we add a movement input for this pawn. We could actually just move the pawn right here, but it's a better approach to actually use the movement input system that is in place in Unreal. So we're going to add a specific movement input. We get the actor right vector, which is the positive y-axis. So we say we want to move along the positive y-axis, and we want to move by move scale times move amount per frame. Now I will say that by getting the positive y vector, if move scale is negative, we press the left key for example, then this will be negative, so we'll be applying a negative movement input along the positive y-axis, which moves us to the left. And we do a similar thing down here with move vertically. So if one or both of these functions are called, we'll have some movement input that we've added because the functions were called. Back in the tick function, I have an F vector called pending movement input, and I call this function called consume movement input vector. So what happens is, adding movement input in these functions down here build up a movement input vector that I can consume here to find out if there are any movement inputs waiting to be processed. If y isn't 0 or z isn't 0, that means I have movement input on at least the y-axis or the z-axis. I might have it on both, but I have it on at least one. And I want this if statement because I don't want to do all this work in here unless I'm actually processing movement input. So first thing, I get the actor location and I put it in an F vector called new location. For Y, I add, so now I'm changing the location in Y. I add the Y component of the pending movement input, and I clamp on the screen for Y. For Z, I add anything that might be pending in Z, and I clamp in Z, and then I set the actor location to the new location. So this is the pawn having functions called on it saying you should handle movement input, and on tick actually processing any pending movement input. I should have mentioned, when we create a pawn with pawn as the parent class for our C++ script, we actually get a default function for setting up the input component. And I just deleted that. I'm not handling any input in the pawn. I'm doing all that work in the player controller instead. So speaking of the player controller, here we are. We've seen this function before when we added this function in our mouse button processing so that we could bind to the destroy character action. We also have here, we want to be able to move horizontally. We want to be able to move vertically. And we want to be able to destroy the miner. So I've added those functions for movement processing and for that action mapping for destroying my miner. Finally, in the miner player controller implementation file, I've added my setup input component function. And this stuff is new. Well, the assert isn't new, right? This is just making sure we did get the pointer to the U input component when the player controller was created. But this time, instead of binding to an action, we're binding to an axis. The rest of this looks very similar. Here's the axis mapping name. I'm saying this player controller is the one that's going to do it. And again, we have the address of the function we should call when an input event occurs on that axis mapping. In other words, if there's some non-zero input on that axis mapping, this is the function we call. Obviously, binding to the vertical axis is very similar. And this is exactly what we saw before when we were destroying our character by pressing the left mouse button. This time I set the input to be the spacebar, but we're still going to do it on pressed. You'll notice this particular argument isn't required when we're binding to an axis because we're just checking for non-zero input. We're not trying to determine whether something was pressed or released or double-clicked or whatever. To move the teddy bear horizontally, if the input isn't 0, because we only want to do this work if input is not 0, we get a reference to our miner pawn, and we call that move horizontally function that we already looked at for the miner pawn. Similarly, for move vertically, and finally, the destroy miner function. The body of the function looks much like the destroy character pawn function from our mouse button processing lecture. So let's go back to the editor and run the game. So I'm going to Alt-P, and now I'm going to try to move my character around. And I'm pressing the keys that should move it, and it doesn't move. And I will confess to you that I spent a stupid amount of time trying to debug my code to figure out why it wouldn't respond to keyboard input. And the answer is you have to click in the viewport before your input will work properly. So that's something that I'm warning you about. You need to click in the viewport. So heads up, if it doesn't seem to be working, click in the viewport and check only call your problem. There is another problem we actually have here though. If I Alt-P again and actually click here, I can move my miner around, but watch what happens if I press A and D at the same time. I can move twice as fast as I move if I only provide input on one of those positive scale inputs for the axis mapping. Before we fix that problem, I realized that I never actually included the move amount per frame in my movement. So here and here, I'm only adding some number between -1 and 1. And I intended to also include the movement amount per frame. So I'll multiply that number that's between the range -1 to 1 by move amount per frame in both those places, so that changing the move amount per frame will actually change the speed at which I move. Okay, so we've fixed that problem, so we can actually tune the speed of movement, but we haven't fixed the making sure that we're getting a number between -1 and 1. And there are actually multiple places that we could do that. We can do it here. We could clamp our pending movement input in Y and pending movement input in Z to be between -1 and 1. And that's a reasonable approach to take. We could also go down to our move horizontally and move vertically functions and make sure that the move scale parameter is clamped between -1 and 1 before we add that movement input. Or we could go to the minor player controller and make sure that when we move horizontally and move vertically, that we clamp the input to be between -1 and 1 before we call the function in the minor pawn. So I'm going to say that I don't like the idea of putting it in the player controller, because the minor pawn, in a good object-oriented design, the minor pawn, if there needs to be some sort of validation of the input or the range of parameters or something, the minor pawn should take care of that to make sure that consumers of the class can't screw up the behavior of the minor pawn. The minor pawn is responsible for its own behavior. So now we're down to the choices of putting it here in these functions or putting it up above in tick when we consume the pending movement input. And that's not an arbitrary decision. I guess it's a personal choice, but I'm going to do it here. So before I add the movement input, I will say move scale equal fmath clamp, and I'll clamp move scale to be between -1.0 float and 1.0 float. And that way I'm ensuring that when I add movement input, the move scale is between -1 and 1 inclusive. And I'll put that here as well. And we'll build again to make sure it builds. And it does. And back in the editor, when I run and get focus in the viewport, I can go left and I can go right, and I'll press right and D, and as you can see, it doesn't speed up. Now I will say that there is still a bug in here. Watch what happens when I move diagonally. I can move faster diagonally than I move left and right. So that may be hard for you to see, but it's true. So this is something called the Doom Strafe 40 bug. You can move diagonally faster. In fact, your speed is whatever the inputs are times square root of 2, and that's just from the Pythagorean theorem, right? So I can move vertically and horizontally, but diagonally I'm actually moving further on each frame. So I'm not going to solve that problem for you, but it can be solved by figuring out your actual complete input vector and normalizing it turning it into a vector of length 1, and you can do that to get rid of the doomstrafe4 debug. The other thing I should show you is if I am moving around in the screen, I can press the spacebar and destroy my miner as expected in response to that action. And that's how we can use keyboard input in our Unreal games. To recap, in this lecture you learned how to use action and axis mappings to process keyboard input in your Unreal games. I will confess to you that the way I implemented movement with a move amount per frame isn't really a good idea. So way back in the old days, if you bought a computer video game and your computer happened to have a faster frame rate than the developers used to develop and tune the game, then the game ran faster on your computer than the game devs intended. If you want to know how to see how to make our movement frame rate independent, you should go to the chapter 8 of the book that I give you as a reading, and you should read about the minor pawn tick function, because I walk through how we can actually make our movement frame rate independent in that chapter. In this lecture, you'll learn how to process gamepad input in your Unreal games. And lots of people call gamepads controllers. That's just fine. While you don't need a rubberized controller with hyper-responsive buttons and thumbsticks for which you can adjust the resistance, I have a friend who may have one of those. Any gamepad will do. The ideas that we'll learn in this lecture will apply to all gamepads. The good news is, all we have to do is change our input mappings to use a gamepad rather than our keyboard, and our game will work the same way, except with gamepad input. So we can go to Edit, Project Settings, Input, and I've already set up the mappings. So I have an action mapping called Destroy Hunter, because this time it's a hunter in our game, and I picked gamepad, face button bottom, which is the A button on my Xbox controller. I also changed the mappings for the horizontal and vertical axis mappings, so I selected gamepad left thumbstick X axis to move horizontally and gamepad left thumbstick Y axis to move vertically. And we set the scale to 1 for both of those, and it will be negative automatically if we push negatively on the X axis or the Y axis. So now when I run my game, I still have to click in the viewport to give it focus before it will respond to my gamepad input. But once I do that, I can use my gamepad to move left and right and up and down, and we get finer grained control with the gamepad with this thumbstick. So with keys, we were either getting 1, 0, or -1, but with our thumbstick, I can push it a little and I move more slowly than if I push it all the way. And that's one of the benefits of using a gamepad rather than a keyboard. We can actually get a range of numbers between -1 and +1 rather than just -1, 0, and +1. And of course, I've set it up so pressing the A button will destroy my miner. All of the code looks exactly the same as it did before, so this is also a benefit of using the action mappings and the axis mappings, because we can just change bindings in the editor and we don't have to change any code at all. It still works the way it did before. And that's how we use a gamepad for input in our Unreal game. To recap, in this lecture you learned how to process gamepad input in your Unreal games. And we didn't have to make any code changes at all from our keyboard processing game to gamepad processing. All we did was did some work in the Unreal editor. Just as a reminder, to make your movement independent of frame rate, you should use delta time in the tick function of your pawn to make sure no matter what your frame rate is and how it fluctuates, your movement works smoothly. What will you learn about in this lesson? You'll learn about the iteration control structure, which is also commonly called looping. So you'll learn how to execute a block of code a set number of times, and you'll also learn how to execute a block of code until some condition evaluates to false. In this lecture, you'll learn about the for loop. And we use the for loop when we know how many times we need to iterate when we get to the loop as we run our code. Let's go take a look. The for loop will print the squares from 1 to 10. So we type for, and we put open and close parentheses, and we have 2 semicolons here. And then we'll put the body of the for loop. And just as with if statements, if we only have one statement as the body of the for loop, we can omit those curly braces, but I always suggest that you include them. We have 2 semicolons up here because we have 3 parts to our for loop. We initialize something that I'll call a loop control variable, because this variable I will control the execution of the loop. The next piece that we have is some condition that will test. Every time we get to the top of the for loop, we'll test this condition to see if it's true. And if it's true, we'll go into the body of the for loop again, and if it's false, we'll go past this closed curly brace and move on in our code. So my condition here will be I less than or equal to 10. And you should recognize this as a Boolean expression, right? This will evaluate to true or false. And then finally, I need to say how I'm going to modify the variable that controls the loop control variable, as I will call it. And I will modify this by incrementing it. So plus plus is the increment operator, and so if I is 0, I plus plus is 1, if I is 1, I plus plus is 2, and so on. In here, all I need to do is print out the square of I, 1 per line. So I'll use standard cout, and I will print I times I. And I know I'm going to want a new line as well. So now I can run my code. And it prints out the squares from 0 to 10 because I set I to 0 here, not 1. So let's try that again. I want to start I at 1. So I'll run it again, and I get the squares of the numbers from 1 to 10. Now, the way this works is the first time through the loop, we set I to 1, and we check if 1 is less than or equal to 10. And of course it is, so I go into the body of the loop, and I print out 1 times 1. Now I come back to the top again because I finished with the body of the for loop, and the first thing I do is I increment I, so now I is 2. 2 is less than or equal to 10, so I go into the body of the loop and I print out 2 times 2. I come back and make I 3, and we keep doing this until we increment I and I becomes 11. When I becomes 11, 11 is not less than or equal to 10, so we break out of the for loop, we don't execute the body anymore, we just move past it to this line of code, which happens to be the end of our main function. Now you might see people using different formats for the for loop. For example, you could take this part and put it here instead, and everything will run fine as you can see. The reason you might do that is because if we do it this way, which is the most common format for a for loop, this I is declared here, so it's only visible here. So that is the scope. It's called the scope of I. It's where that variable I is visible. And that works fine for most for loops, but if you need access to I out here on line 17, I is no longer visible, so you couldn't use it. So that would be one reason that you might put your loop control variable declaration and initialization before the for loop. You might also see people doing this and just incrementing I here instead. That's probably less common, but that also works. And finally, you're likely to see people doing this instead of I++. And that also works fine, as you can see. There are some subtle differences between this and this, but they don't matter in this particular case. But there are other cases in C++ where the place you put the plus actually matters. We're not going to deal with any of those cases in any of the courses in the specialization, but you should understand that ++I also increments I. Okay, so this is interesting, right? But let's actually make it so that the user can provide how many squares they want. So remember in the intro, I said that a for loop is useful when we know how many times we're going to loop when we get to the code. That's not the same as saying we know how many times we're going to loop at compile time. So we can prompt for and get how many squares to print So we'll start with the prompt. And I'll just say enter how many squares to print. And I'll give the user a hint about what they should use as the range, but they can ignore us, as we'll see soon. And now we're going to read in how many squares to print. And by now, I mean after I declare the variable that actually will hold that number. So we'll read into n, and we'll say here we're going to print the squares from 1 to n, and we'll change our upper bound to n instead of 10. So now when we run, we can say how many squares to print, and we can say 10, and it prints the squares of the numbers from 1 to 10. We could say 3, and it prints those squares as well. If we do something like this, if we say print 0, it doesn't print any. So here's how that works. If we read into n, and we get to line 18 here, and we set I equal to 1, but then we check to see if 1 is less than or equal to 0, and 1 is not less than or equal to 0, so we don't ever execute the body of the loop, and we just move on to this blank line after the for loop. So that's how you can use for loops in C++. To recap, in this lecture we learned how to use a for loop to execute a set of statements, the loop body, a certain number of times. Last time, we learned how to use for loops to execute a chunk of code a set number of times. This time, we'll learn how to use nested for loops. So to build nested for loops, we just put one for loop inside another. What are they good for? In general, they're good for traversing two-dimensional or higher dimensions of data. To demonstrate nested for loops, I'm going to print out the multiplication table for the numbers from 1 to 10. So the first thing we'll do is we'll print the header for that table. It will become clear to you momentarily why I'm starting by printing 5 spaces. Now I'm going to use a for loop to print the numbers from 1 to 10. And this isn't the nested for loop stuff, this is just a regular for loop. And I'm going to do things just a little differently here because in a table, I want each output to be in a field, if you will, of a particular width. And I know how to do that in C++. We can just use setWidth and say how many characters that field is going to be. And then I can print out I in a field of width 5. I'll point out that setWidth is in the IO manipulation library, so you need to include that library if you want to use setWidth. But now we can run the code to show that our header appears properly with that space at the beginning. The reason I want that space in the beginning is because when I print the table, I'll show you where I needed that space. So here's the nested for loop stuff. My outer loop, I will set my loop control variable, and I could call this anything. It doesn't have to be I, it could be Ro or Bob or Joe or whatever. It's fairly common to use I as a loop control variable here, so I'm going to do that. And I also want to point out that this I is not the same as this I. Remember, we talked about the scope of this I up here, and it's from here to here. So the scope of this I is from here to here, and it's a totally separate variable, even though it has the same name. The reason I wanted to print out those first 5 spaces at the beginning of the table header is because I know that here I want to print out I, and I will also say that I need to put standard there, and I will also say that here right before I loop back in this outer loop, we don't have the inner loop yet, but before I loop back, I know I'm also going to want to print a new line. And if I run my code now, I realize that the one that I wanted on the left is at the end of the header. So I will print a new line here as well. Try that one more time. So there you go. I have the header along the top, and each row will be the, we do row times column to do our multiplication table. So now all I'm missing is that inner loop. I'll do another for loop, and I can pick any variable name I want except I. If I pick I here, it's going to screw everything up because this I here is visible from here to here. So it's really common to say J equal 1, J less than or equal to 10, J plus plus, and in the body of this inner loop, I will print out in a width of 5, the product of I times j. And of course, I need 2 colons there. Push that back where it belongs. And now when we run our code, we get the entire multiplication table. And you can convince yourself that this is correct, but each cell is the product of its row and its column. So how does this work? When we get to the outer loop, the very first time we've just printed the header, we set I to 1, and we know 1 is less than or equal to 10, so we go inside the body of that loop. We print out I, and now we get to this loop. So we set j to 1. 1 is less than 10. So we print out I, which is 1 right now, times j, which is also 1 right now. And then we get to the end of this inner loop and we come back to the top. And we set j equal to 2. 2 is less than or equal to 10. So we print out 1 times 2, which is 2, and so on. So this inner for loop works just like a for loop like we learned last time. Now, when this for loop ends, we've just finished printing a row of the table, so we move to the next line. And now we get to the end of the outer for loop. We increment I from 1 to 2, and then we come into the body again and we print out 2. And here's where people sometimes get confused. So when we get to this inner loop again, it has no memory that it has ever executed before. So we initialize j to 1 and do that inner for loop. So it's sort of like wheels spinning within wheels, right? We get to the outer for loop, and then we spin the inner for loop till it's done, and then we rotate the outer for loop 1 tick, and then we spin the inner for loop again, and then we rotate and spin, and so on. So the important idea is the inner for loop always starts fresh whenever we get to it, and it works just like a for loop. And the outer for loop also works just like the for loops we've learned before. And that's how you use nested for loops in C++. To recap, in this lecture you learned how to use nested for loops to do something useful. Last time we finished our discussion of for loops. In this lecture we'll look at while loops, which help us solve problems where we don't know how many times we're going to need to iterate when we get to the loop. One of the places that people regularly use while loops is for something called input validation. We're going to have the user input some data for us, and we need to validate or make sure that it's within a particular range or a specific format or something like that. We're going to do input within a particular range in this lecture. So what we're going to do is we're going to have the user enter a test score. So we'll prompt for and get score. And of course, before I do that, I'll actually need a variable to hold the score. First we'll prompt. And if we have an expectation that the user input will be within a particular range, we should tell the user what that range is. And then we'll read it in. Here's the while loop part. We put the while keyword, and we put parentheses, and we put curly braces. And of course, as always, if the body of the while loop is only 1 line of code, you can omit the curly braces, but I suggest you always include them. And in between these parentheses, we put a Boolean expression. And the way while loops work is, if the Boolean expression evaluates to true, we're going to go into the body of the while loop. So the Boolean expression we need to specify here needs to be an invalid test score. That's the only reason we're going to want to loop to ask for a new input from the user. So this may seem counterintuitive to you, but we need to write a Boolean expression for an invalid score. An invalid score is either less than 0 or it's greater than 100. Any score that's between 0 and 100 inclusive is valid. So for those scores, this Boolean expression will evaluate to false. But for invalid scores, this will evaluate to true. So we should print an error message and get a new score. So first we'll print an error message. Score needs to be between 0 and 100. And then we prompt for and get the score just like we did above. So let's see how this works. If I enter a valid score, we're all done. So that tells us that the body of a while loop executes 0 or more times. We entered 100 up here and this Boolean expression evaluated to false, so we immediately went to the line after the while loop body. Of course, the 0 or more times, I can make it execute more than 0 times. So here's an invalid score and it looks like I need some line breaks, but now I'll enter a valid score and everything's okay. So let me put some line breaks in here. One to offset the error message from the user input they just provided. And of course, one here as well. We'll just test to make sure I did that properly. So -5, 5, and we're good. The reason we're using a while loop here is because we don't know how many times the user is actually going to provide invalid input. So we can't use a for loop, right? We don't know what the limit is for how many times the user will either be confused or malicious. So we'll just keep looping with invalid inputs as long as the user keeps entering invalid inputs. And then finally, when they finally enter a valid one, we'll break out of that loop because the Boolean expression evaluates to false. I'm going to add one more comment here. And I also want to mention that people will sometimes talk about getting stuck in an infinite loop. The for loop is not as prone to infinite loops. You can build an infinite loop if you choose to with a for loop, but people usually end up with infinite loops by mistake. I will point out that there will be times as you look at code that you'll see somebody do something like this. They'll say while true, which is by definition an infinite loop, until they put some code inside here to break out of the loop when you should break out of the loop. There are certainly places where that structure is appropriate, but certainly not in input validation. We should just do it a more reasonable way, like this. But people can get into infinite loops, and there are 3 things we need to think about when we are trying to avoid infinite loops for our while loops. And the initials for those things are ITM. And ITM stands for initialize, test, and modify. So let's talk about them one at a time. First of all, before we get to our while loop, we need to make sure that we have initialized our loop control variable to a reasonable value. Now it turns out that we could have multiple loop control variables for a while loop, and that's fine. We should make sure they're all properly initialized before we get to the loop. In this particular example, we've initialized score before we get here, so we don't need to worry about that particular issue. The next one is test. So we need to make sure that this Boolean expression that we write is correct. But let's say we got confused as we were writing this Boolean expression and we said while score is greater than 0 or score is less than 100. We got our relational operators incorrect. When we run the code, I can enter any number I want and it gives me an error message. And that's true of invalid numbers and more invalid numbers, and you say, oh, I'll take a 50. You're just stuck in this infinite loop forever. The problem is that you can't think of a score that is neither greater than 0 nor less than 100. And some scores are both, right? Any score that's 1 to 99 will meet both of these criteria for the OR, but all numbers meet at least 1. So that's an example of getting the test incorrect and ending up in an infinite loop. And that last initial M for modify tells us that we need to be sure to modify at least one of the loop control variables that we have controlling our loop, which we're doing with this line of code. But if we forgot that line of code and we were in our code, I'll have to enter an invalid score to push us into the body of the while loop the first time, but then I go forever. So let's talk about how this works. If this Boolean expression evaluates to true, I go into the body of the while loop and I do this stuff and I never change score. So when I loop back around to the top to check the Boolean expression again, it's still true because I never change score. So I go to the body and loop back around and it's still true and so on. So I'm going to fix this. So those are ways that we can end up with an infinite loop. Now, it's not really infinite, right? At some point, you'll rage throw your computer against the wall or the sun will explode or something. They're not actually infinite, but the while loop doesn't actually behave properly in terms of how many times it iterates. To recap, in this lecture, you learned how to use while loops to solve problems where we don't know how many times we'll need to iterate when we get to the loop. You learned that the body of the while loop executes 0 or more times. And you learned that thinking about initialize, test, and modify helps you avoid writing infinite loops. Last time, we learned how to use while loops to solve problems where we don't know how many times we're going to iterate when we get to the loop. This time, we'll look at do-while loops, another way to solve those problems. We'll start with our while loop code from before, though I did change the comment up here. So we'll just reformat this to use a do-while loop instead. The big idea is we put the keyword do, and then we have curly braces, and then we say while some Boolean expression. And the Boolean expression we'll use, I'm going to beat Visual Studio into submission. The Boolean expression we use is identical to the Boolean expression we used before. So we format it like this, and we'll prompt for and get a score inside the do while loop. So because we start at the top and work our way down, the body of a do while loop executes 1 or more times. There's no way to skip the body of a do while loop because we don't get to the condition until the end. And so far this feels like a win because we can do this. We can run our code. And we can't actually run our code because I left all this stuff here hanging around. So let me just comment out all this code right here. But we can run our code now. And as you can see, if I enter 100, I'm all done. If I enter an invalid number, I get another prompt. I'm looping through the body of the loop again. And I can enter another invalid number, and I'm still looping, and then finally I stop looping. So we're missing a piece though here. We're missing the error message that tells the user they did something wrong. And we really need to include that So we need this print error message part that we had before, but we only want to print it if what we just read from the user is invalid. So we need to add an if statement here that uses the same Boolean expression as the while condition for the do while loop. And then we can print that error message. And I won't say and get new score, I'll say as appropriate. And in fact, I'll put that comment here instead. And now if I run the code, from the user's perspective, we'll see that this looks just like a while loop implementation. The user has no way of knowing how we actually implemented this loop. And I'm going to get rid of all this dead code that I don't need anymore. So when should you use a do while loop? Well, you'll certainly hear people argue that if you need to execute the body of the loop at least once, the do while loop is the correct loop to use. And in particular for input validation, but for lots of other scenarios as well. Here's where the do while loop wins. We know we have to do this once, and we only need to include this code one time here at the top of the do while loop. In case you've forgotten, in the while loop, we had this code before the while loop, and we included this code in the body of the while loop when we were getting a new input after we printed the error message. So our while loop duplicated these lines of code twice, and here we only need it once. The downside is we also need to include an if statement if we're going to print out an error message. So we've saved some duplicated lines of code, but we've added some complexity overall to our code because now we don't just have the iteration control structure, we have the iteration control structure and the selection control structure in our code to get the same functional behavior. This is really a matter of personal preference. I will say that I personally never use do while loops. I always use while loops because they are less complex, even though I end up with a little duplicated code. But you can decide whether or not you want to use do while loops in those situations where you know the body of the loop has to execute at least once. To recap, in this lecture you learned how to use do while loops to solve problems where we don't know how many times to iterate when we get to the loop. We learned that the body of a do while loop executes one or more times, and we also learned that sometimes using a do while loop leads to more complex code than using a while loop. Last time, we finished talking about the three different kinds of loops that we commonly use in C++. That's a little lie because we'll learn about another variant of the for loop in the next lesson, but it's good enough for now. In this lecture, we'll learn how to use lots of what we've learned in this lesson to solve a particular problem. Here's the problem we're going to solve. We need to build a box with asterisks all around the edges of the box using a user-specified width and height. The constraints on this problem are that both the width and height need to be between 3 and 20 inclusive. Let's go solve that problem. This is a really interesting problem because it lets us use while loops and regular for loops and nested for loops. So it's a great problem. The idea for this problem comes from Beginning C, a book by Ivor Horton. And I know I'm teaching you C++ here, but this is a great book to use if you want to learn how to program in C. And I took the idea for this problem from that book. Okay, so my starting code, I have variables for the width and height of the box, and then I have while loops to do input validation to make sure I get a box width that's between 3 and 20 inclusive, and a box height that's between 3 and 20 inclusive. I will freely admit to you that I wrote my input validation for the width and tested it, and then I copied this code and I pasted it down here and I changed width to height. And as a programmer, that made me feel really sad. That's a horrible thing to do. Copying and pasting is never the right idea if you need the same code. What I really wanted was to write a function that would get me a value that was between a lower bound and an upper bound. Unfortunately, we haven't really talked about writing our own functions yet, so we're not ready to do that yet. So I did it the same way that you would probably have done it, but I found it very unsatisfying to do it that way. And once we know about functions, you'd absolutely write your own function. Okay, so how do we print out this box? Well, the first thing we're going to need to do is we're going to need to print out the top row of the box, which is really just a solid line of asterisks. That's the user specified width. We know how to do something a particular number of times. That's definitely a for loop. And we can start I at 1, and we'll go for the full width. So I less than or equal to width, and we'll increment. And the only thing we need to do in here is print out a single asterisk. And once the loop is done, we'll want to print out a new line so that we can move off that top row. So let's test this. It doesn't matter what I enter for height, but if I enter a reasonable width, you'll see I print 5 asterisks as the top row. Again, feeling like a bad programmer, I'm going to print the bottom row by copying and pasting that top row stuff. And I can test that. And if I enter some valid width and some valid height, you'll see I have the top and bottom rows of the box. The most interesting part of this problem is print the middle of the box. So we need to think about how many times we're going to do this. First of all, how many rows are there in the middle, because that's a good for loop for us. So I'm going to actually start I at the second row. And how many total rows do we print in the middle? We print height minus 2. So height minus the top row minus the bottom row. We can specify our condition here in a variety of different ways, but I'm thinking of I in this loop as keeping track of which row we're printing. So we start by printing row 2, and then we're going to print all the way up to row height minus 1. So I'm going to say I less than or equal to height minus 1. Now I know that implies we always need to use a less than or equal to here. I could just as easily have said I less than height, but I find this more readable thinking of I as the actual row number I'm printing here. I am going to increment I. And now we need to think of what does a particular row look like. And a particular row looks like an asterisk, and then a bunch of spaces, and then an asterisk, and then a new line. So let's do the asterisks at the end first. And of course, I'll do the new line as well. And let's go ahead and do this. I know it's not going to be correct, but let's watch all those rows print without the spaces in the middle. So I'll run the code, and I'll say the width is 5, and I'll say 7 rows, and there you go. I have the top row, and I have the 5 middle rows, even though we're just doing the asterisks, and then I have the bottom row. So now we need to add the spaces in between. I'll need another for loop for this because I don't know at compile time how many spaces I need, but I will say that I'll think of this the same way as I did the outer loop. I'll think of J as being the column I'm printing in. So I know that I'll start J at 2, and I'll print while J is less than or equal to width minus 1, and I'll increment J. And here, what I'm outputting is a space. So now I'll test my code again, and I'll say 6 by 6, and there's my nice 6 by 6 box. I will point out, of course, I was printing out strings up here, but as I'm printing out characters, I can print out character literals as well. So it doesn't have to be strings when I'm printing out a single character, but I'll show you we get exactly the same output if we print out asterisk characters and space characters. Let's do a big box, 20 by 20. And you can pause the video and check to make sure, but I promise you that's 20 by 20. And I'll show you a 3 by 3 box, our smallest possible box. So as I said, this is a really interesting problem to solve. We have regular for loops, we have nested for loops, and we have while loops. To recap, in this lecture you learned how to use while loops and for loops and a nested for loop to solve an interesting problem. And I know I mentioned Ivor Horton's C book, but Horton also has an awesome beginning C++ 17 book if you'd like to dig deeper into C++. In this lecture, we'll use what we've learned about for loops to spawn multiple teddy bears each time our spawn timer goes off. We'll start by adding a constant to the header file for our teddy bear spawner, and our constant will be for how many teddy bears to spawn each time. So obviously this will be an int. I'll call it teddy bears per spawn. And why don't we set it to something like 10 to start with. So every time the spawn timer goes off, we'll spawn 10 teddy bears instead of 1. Over in our implementation file, all we need to do is we've got this block of code in our spawn teddy bear function that randomly picks a teddy bear to spawn, generates that random spawn location, and then spawns the teddy bear. So we can just do this repeatedly. We can say for int I equals 0, I less than teddy bears per spawn, I plus plus, and we'll put all this work except starting the timer again into the body of that for loop. I'm going to compile, and I've compiled successfully, so back in the editor, I run my game, and then we get a bunch of teddy bears spawned in there and so on, and we're doing 10 at a time. This is awesome. And of course we're getting a big pile of teddy bears, and they're dying off a little bit at a time. And that's how we can use a for loop to spawn multiple teddy bears each time the spawn timer goes off. Let's actually spawn even more each time the spawn timer goes off. And I can do that by simply changing how many teddy bears I do per spawn to 100. And when I run the game now, and isn't that awesome? Now, it turns out that some of these teddy bears, I better stop this, It turns out that some of these teddy bears are actually spawning into collisions, and we may want to control that. We may not want to spawn a teddy bear into a collision with another teddy bear, especially because these are physical objects that collide with each other. And the way we can do this is we can select each blueprint and just search on collision, and you can see that this spawn collision handling method controls how we're going to handle this if we're spawning this actor into a collision. So by default, this is set to always spawn, ignore collisions. We can let the engine try to adjust the location, so it tries to find a nearby non-colliding location, but it will always spawn, even if it can't find such a location. We can try to adjust the location and not spawn unless it finds a non-colliding location. Or we can say never spawn. We don't want that one. But let's try to do this one. We'll try to adjust the location and don't spawn if it can't find a non-colliding location. That will mean that we don't spawn as many objects as we thought we would, but this is potentially better than spawning into a physical collision with another object that has physics behavior. And we compile and save, and we're going to do that for all of our blueprints that we're spawning into the game. So now when we run our game, we got lots of teddy bears, but we didn't get 100 because it was unable to find spawn locations that were not colliding. So if you want to be safe and spawn multiple things, or even when you're spawning just one thing into your map, to make sure it doesn't spawn into a collision, you can adjust the behavior of the spawning for that particular actor as it's getting spawning to meet your particular collision-free needs. And that's how we can use a for loop to spawn multiple teddy bears into our map each time the spawn timer goes off. To recap, in this lecture we used a for loop to spawn multiple teddy bears each time our spawn timer went off. What will you learn about in this lesson? You'll learn how to store multiple values in a single array variable. You'll learn how to process arrays using for loops. You'll learn about the C++ array and vector containers. You'll learn about the Unreal T-array container, and we'll look at a Ted the Collector game together. The big idea behind arrays is that arrays let us efficiently store multiple values in a single variable. So what can we store in arrays? We can store anything, but each array can only store one data type. So we can have an array of ints, and we can have another array of actors, but we can't mix ints and actors in a single array. This is a conceptual representation of what an array looks like. So typically we will declare an array as a variable, and I have declared this array as a variable named GPAs. Now each of those boxes that contain 0.0 is actually a location in memory, and the separate things that are stored in those locations in memory have a specific name, and that name is elements. So we talk about the elements of the array as the contents of the array. Now in this particular array, we have elements that are numbered 0 through 9, and we'll talk in a couple of lectures about why we start at 0, but those numbers on the left-hand side give us a way of indicating which element we want to do something with. We might want to find out its value, we might want to put a value into it, but we need a way to say within this GPA's variable of 10 elements which element we want to do something with. The number that we use to access a particular element in the array is called an index. We'll start by declaring our array variable, and the first thing we put is the data type for each of the elements in the array. Then we put the name of the variable, and I'm going to store some test scores in this variable. And this all looks just like the variable declarations we've had so far. The way we tell the compiler that we're going to actually have an array here is we put square brackets, and we also put how many elements we're going to have in the array. And once we've declared an array, we can't change the size of the array. The way we actually access elements in the array is we put the array name, and then we use square brackets, and we provide the index of the element we want to manipulate, and then we can do something like set scores 0 to 100. We start our indexing at 0, remember? And we can do this as well, and so on. But this doesn't really actually harness the power of the array so much, because if we just do a line of code for each element and so on, this is going to be pretty awkward, especially for larger arrays. So one of the great things about arrays is we can actually walk the array or touch each element of the array using a for loop. So I'm going to comment this out, and instead of doing it that way, I'm going to use a for loop. We're going to start our loop control variable at 0. We're going to run our loop control variable up to, but not including 5, because remember our elements are numbered 0, 1, 2, 3, and 4 for this particular array, and we'll increment I each time through the loop. I'm going to use this for loop to read in the scores. And what I'll put in the body of the loop is our typical input validation code. So I'll go do that, and then we'll come back and talk some more. So here we are. We're going to prompt for and get a score. And I've done a couple of things differently from what we've done before. So I'm telling the user which score they're entering. And I'm using I+1 because the user is a human, not a C++ programmer. So humans start counting at 1. So we'll be asking for test scores 1 through 5, but we'll be putting them at elements 0 through 4. And the other difference is here, where I'm reading into a particular element of the scores array. So we saw up here that I can use literals to access particular elements of the array, but I can also use variables because variables hold a value, and that value will be the index we use for the element in our array. And the rest of this is what we've seen before, of course, checking for invalid particular elements that we've just read into rather than just a single variable like we've done previously. Okay, let's run this code, and I'll show you that the input validation loop works properly, and then I'll just enter some scores. Like so. So that's how we can use a for loop to actually populate the array. Let's print out those scores to make sure we actually populated the array properly. And you might think that you can do something like this. And this will certainly compile, but when we run it, you'll see that you actually do not get the elements of the array there. We're actually looking at the memory address of where the scores array is stored, so that's not really what we wanted to do. We can't just print out the array all at once. We actually need to use a for loop to print out each element of the array. I know I'm going to want a line break before I do this. And now we need a for loop again. And of course, we want to print out scores I. And there you go. Now I will point out that we've been hard coding the size of the array in these for loops, and we'll actually learn a better way to do that, but not in this lecture, because this lecture was to give you your first introduction to how arrays work in C++. To recap, arrays let us store multiple values in a single variable, but we know those values have to all be the same data type. We also learned that once we create an array, we can't change the size of the array, and I will comment that I inadvertently started some of my variable names with the lowercase letters in the videos, but I've fixed that in the code that I'm providing to you. In the previous lecture, we learned how to declare and use an array to store multiple pieces of data. This time, we'll look at various ways we can initialize the elements of the array. Our starting point is code that declares a scores variable, an array of 5 integer scores, and then a for loop that prints out the values of each of those scores. We have a warning here that says that we're using uninitialized memory. So we're going to get whatever we get in those memory locations. In fact, if I run the code, you can see I get a whole bunch of negative numbers here. That's just the garbage that's sitting in memory. When the runtime system goes and grabs 5 contiguous pieces of memory for holding 5 ints, it just gets whatever is there. We do know from the previous lecture that we can initialize an array by getting user input, and we'll actually learn later that we can also initialize an array by reading from a file and putting values from the file into the array. But in this lecture, we're going to explore initializing the array using a braced initializer. So I can say I want specific elements in the array like this, and I can get rid of the 5 when I do that, and of course I'll need a semicolon. And now when I run the code, you can see that all the elements of the array have been initialized to 0. I can also set each of those scores to a different number, like so they don't all have to be the same. And as you can see, those scores have been populated into the array properly. Now you might be wondering, why don't I need to provide a number here? And the answer is easy. It's because the compiler can figure out if you've provided 5 values for elements in the array, then you want an array that has 5 elements in it. Back to initializing things to 0. If I want all the elements to have the same value, I can just provide that value. If I do, I need to come back here and say, how big do I want the array to be? Because the compiler can't figure out from one value how many you want it to be. As you can see, this works perfectly fine when I run it. If you forget to do this, here's what happens. the compiler decides to give you an array of one element, and it initializes that element to 0. But what are these other scores? We're actually just walking along through memory. These last 4 values aren't part of the array. They're just whatever happens to be sitting in memory at those locations past the end of the array. This is really dangerous. In C++, we can just walk past the end of the array and we are walking through memory and we think we're still in the array, but we're not. We'll learn a safer way to do this before we're done with this lesson, but it's important to realize that that can happen. So we'll make sure, if we're going to initialize a bunch of elements in the array to a particular value, to specify the array size here when we do that. And just confirming that that works fine. So there are a whole variety of ways we can use a braced initializer to initialize the elements in our array. To recap, in this lecture we saw various ways we can initialize the elements in an array. Last time, we learned a number of different ways we can initialize the elements of our array. This time, we'll see why we start indexing our arrays at 0. I've done some preliminary work here to set us up for this discussion. I've declared a scores array that has these values in it, and then I'm using a for loop to print out information about the array. I'm going to print out scores I, a label that shows us which element we're looking at, and I'm just going to use I, not I plus 1, because we're programmers here, so we want it to start at 0. I'm going to print out the address of that element in the array, and I use standard hex to say I want to print out what comes next in what's called hexadecimal or base 16, and we'll see that as soon as we look at the output. And I'm going to print out the address of the element in the array. Not the element in the array, not the contents. I'm printing out an address here. This is the address of operator, which we've seen before. Then I'll print out the actual contents, telling it I want it back in decimal or integer form, and this will be the contents of that element. So I'll label the scores, I'll print out the address of that location in memory, and then I'll print out what's contained in that location in memory. Okay, let's go ahead and run the code. Okay, so here we see scores 0 is at this address, and this is hexadecimal, this is base 16, so each place in our address is 0 through F. So 0 through 9 and then A, B, C, D, E, F are the possibilities for each place in this address. So the array starts at this location that ends in 4. And here's the contents. And then we walk down, and this one's at 8, and this one's at C, and this one's at 0 and 4. So why are these offset by 4 each time? 8 plus 4 is C in hexadecimal. The reason is that we said that we want this to be an array of integers, and integers take up 4 bytes. So if we start the array at location bunch of stuff 4, then we need the first element of the array to have the spaces in bytes 4, 5, 6, and 7. And then we can put the next element of the array at 8, and the 4 bytes we need here are 8, 9, A, and B. And so the next element at scores 2 goes at C. So that sort of explains why the memory is laid out the way it is for this array. Arrays are always in contiguous or next to each other pieces of memory, but that doesn't explain why we start at 0. The reason we start at 0 is for efficiency. So we have this base address of the array ending at 4 for scores 0. And the way we calculate the memory address for an element of the array is we take the base address and we add the index multiplied by the size of each element in the array. So if we want to access score 0, we take the base address and we add 0, the index, times 4, the size of each element in the array. So we add 0. So we end up with the base address, which is exactly correct. If we're trying to access the element at index 1, we take the base address and we add the index 1 times the size of the elements, 4. So we take 4, this address that ends in 4, and we add 4 to it, and we get 8. And just doing one more, if we're trying to access element 2, we take the base address and we add 2 times 4, so we add 8, and 4 plus 8 in hex is C, so we've accessed the element at index 2. So that's why we start at 0. It's a base address plus the index times the size of each element in the array, and the computer can calculate that very quickly. If we started at 1, there'd have to be a subtraction every single time to say the index you're trying to access minus 1 times the element size. And so there's no reason to do an extra subtraction every time we access an element of an array. So if we start at 0, we can avoid that subtraction and it's more efficient. To recap, in this lecture, you learned that we start indexing our arrays at 0 because the index is used to calculate an offset from the base address of the array. In the previous lecture, you learned why we start indexing our arrays at 0. In this lecture, you'll learn several ways to determine the size of an array at runtime. I've already generated all the code we're going to use in this lecture, so we're just going to talk about it. One way we can find out the size of an array that we've declared is by using standard size. So you could look at this and say, well, I know the size of the array, I can see it right here. But sometimes the places that we're using the size of the array are actually far away from the declaration of the array itself. So this is a good way to determine at runtime when you're about to use the size of an array, what the size of the array is. We have this function called size, and we can hand it an array, and it will tell us how many elements the array has. So we'll look at the first line of output when we run this code. And as you can see in that first line of output, it says we have 3 array elements, which is of course correct because we've declared an array of size 3. If your compiler doesn't support using size, which was added in C++ 17, there's another way to do this. And the way you can do this is, first of all, you can use size of for the entire array. Notice this isn't standard size, this is size of, and this will tell you how many bytes the entire array takes up in memory. You can then get the number of bytes for one element in that array, and I often just do the 0th element, assuming I have an array of at least one element. So this tells us how many bytes a single element of the array takes. And if we know how much space the entire array takes and how much space a single element takes, then we can calculate the number of array elements by taking the entire array size, let's say 12 in this case because it's 3 integers, and dividing by the size of a single element, which is 4 in this case, and that will give us the number of array elements that we have. I'll run the code again, and as you can see, 12 bytes for a 3-element array of ints. Each element takes 4 bytes because it's an int, and then we divide 12 by 4 and we get 3. So those are 2 different ways to get the size of an array at runtime. Remember, we can't change the size of the array after we've declared it, So this scores array will always be 3. And it's also the case, even though you might want to do it, it's also the case that the C++ standard does not let us dynamically figure out how large the array will be. In other words, we can't ask the user, how many scores do you want to enter, and then declare an array of that variable size. The compiler has to be able to figure out at compile time how big the array will be. Now, there are numerous compilers that will let you actually do it, even though it's not in compliance with the standard, but I'm not going to teach you those ways because I want to only talk about C++ standard code. So we can figure out the size of the array in multiple ways, and then we can read in the scores. This is acting like there's an error here, but if I compile, this is up to date, so let me clean the solution and compile again. So if I compile, you'll see that it compiles fine. So you can ignore those red squigglies. There are a couple of warnings that we will come back and take a look at, but first I want to talk about how we can read in the scores. So our typical for loop, but instead of our hard-coded size here, and I will also say that we could have declared a constant for the size of the array and then just use this constant here. I know I hard-coded 5 in examples in previous lectures, and that was probably the worst of all worlds, but I wanted you to sort of see how we can walk an array to manipulate particular elements of the array. But this is a good best practice to access the size of scores before running the for loop over the scores array. This is all code you've seen before here in the inside, so this is the difference from what we did before. We can also print out the test scores using this as our upper bound. So I'll run the code yet again, and I'll enter 3 scores, and it prints out what those scores are. I said we could talk about those warnings, and I'll need to clean and build again to see them. And those warnings say on line 28 and line 50 that we have a signed and unsigned mismatch using the less than relational operator. What that means is we've declared our loop control variable to be an int, which is a signed integer. Can be negative, 0, or positive. The size function, however, returns an unsigned integer. So the warning is you're comparing a signed value, I, right here, to an unsigned value, the return value from this function. We can actually use size t, which is defined as some form of unsigned integer. We don't know whether it's unsigned int or unsigned long or unsigned long. We can just use size t, and size t is an unsigned integer data type. And size t is used a lot in the standard library for sizes of things, like we see here, and counts of things. So we will find ourselves, at least sometimes, using size t as the data type for our loop control variable in our for loops when we're dealing with sizes of things. I'm going to change both of these. And I will also say that we haven't spent much time talking about warnings. They're warnings, right? They're not errors, so your code will run. But many programmers want what are called clean compiles. No warnings, no errors, everything is as high quality as possible. So I felt compelled to get rid of those 2 warnings. If I build again, you'll see those warnings have gone away. And I'll also demonstrate that the code still works the way it worked before. So even though this lecture was focused on figuring out how big an array is at runtime, we got to learn some other stuff about size t as well. To recap, in this lecture you learned a number of different ways to determine the size of an array at runtime. The standard size function became available in C++17, so if you're in a C++17 environment, you should just use standard size. But if that's not available to you, I also showed you how you can use the size of function to determine the size of the array. If you're working in Xcode, you need to configure your Xcode project to use C++17, and I've provided a reading showing you how to do that in the lecture resources for this lecture. In this lecture, we'll process the data in an array to calculate the average of the elements in the array. As usual, we have an array of scores, although I keep changing the number of scores we're going to use. So this time we'll have 4 scores that we're processing. We'll first read in those scores, and we're using that size function that we've talked about. And I've declared I to be of type size t because I hate warnings. Here's our standard input validation stuff. And now we're going to walk the array and calculate the average. So I initialize a sum to 0. I do another for loop here, again using size and using size t. And each time through the loop, I add scores I to the sum. And this plus equal is identical to this, but it's a convenient shorthand, so many programmers just use plus equal if we're adding something to sum here. And of course we got minus equal and divide equal and times equal and so on. So this for loop adds up all the values in our scores array. And then I declare an average variable that is of type float, and I typecast the sum to float so that I do floating point division here, not integer division, and I divide by how many elements there are in the array. And of course, if we add up all those elements and divide by how many there are, that is by definition the average. Finally, I do one more for loop, and I walk through the elements in the array and print out the value of each element, and then I print out the average as well. As you did in programming assignment 2, we're going to set our precision for our average output to be 2 decimal places. If our average doesn't have any decimal places, or if it only has 1, then it will print none or 1. But if it has more than 2 decimal places, then this will be rounded to be 2 decimal places. So I'll run the code, and I'll show you an average with no decimal places. And as you can see, it prints an average with just the whole number because that's all the average has. I can show with 1 decimal place. You can see it's 2.5. So these are standard ways that we've seen that we process an array, whether we're populating the array with values provided by the user, or we're printing out the contents of an array, or we're walking the array to do some processing. I said back in the iteration lectures that I told you a small lie, that there was another variant of the for loop that we can use that I hadn't shown you yet. And I want to show that to you now because we very commonly use it when we're processing arrays. This variant of the for loop is called a range-based for loop. So instead of doing this, we can do this. We can say int score and provide a range of values to walk across. So let me fix line 36 and then we'll come back to that. So here's the idea. We have a range that we want to iterate over. Remember, the looping is the iteration control structure. And instead of having to index into the array each time on line 36, we provide a variable that will get populated each time we go through the loop with a different element of scores. So the first time through the loop, score will be set to scores 0. And so down here, we will add scores 0 to our sum. When we come back to the top of the for loop again, score gets set to scores 1. And we go through and do some stuff until we've walked the entire scores array. Notice we don't have to calculate the size of that scores array or anything. The system knows that scores has 4 elements, and so this for loop will execute 4 times. And as that happens, the first time through, score will be scores 0, then scores 1, then scores 2, then scores 3, and then the loop will stop. I'm going to run the code to show you that this works the same way. And as you can see, it works exactly the same way. So the range-based for loop is a very powerful variant of the for loop that we regularly use when we need to iterate over a range of values, like an array of values. You'll notice though, I could try to do that here as well, but we'll actually have a problem because I'm using I inside the body of the for loop. In a range-based for loop, we don't get I. We don't know which iteration we're on in the body of the for loop. If we don't care, like we didn't when we were adding up the values of all the elements, then we should use a range-based for loop. But if we do care, like we do when we want to label our output to tell the user which score we're displaying, then we need to use a for loop that uses the loop control variable as shown here. Similarly, when we're reading in the scores, we're actually telling the user which score they're entering, so a range-based for loop isn't appropriate in this scenario. Now, if you want to provide less helpful output to the user, you could use a range-based for loop, but it's really best to give the most helpful output to the user and use range-based for loops when they're appropriate, and they are appropriate many times. To recap, in this lecture you learned how to process the data in an array, and you also learned about the range-based for loop. In this lecture, we'll look at the C++ array container, which is a good alternative to using the arrays we've been discussing so far in this lesson. Our starting code for this lecture is the code from the previous lecture where we were using arrays. In this lecture, we're going to convert this code to use the array container instead. The array container is something called a class template. So we've learned about classes before, but a class template means that we're going to provide some template parameters and we'll end up with a concrete type based on those template parameters we've provided. So we'll convert this scores array to an array container instead. So I'm going to say here, standard array, and I put my template parameters between less than and greater than, and the 2 template parameters that I provide are the data type of the elements in the container, so that's int, and I still need to provide a size that the compiler knows about at compile time. So even though I'm using this array container, I still have the constraint that I had with arrays that I can't dynamically size them. I have to say what size it will be at compile time. So I'll make it 4. And I get rid of that notation at the end, and we'll see if I compile that scores uses an undefined class, because if I'm going to use the array container, I need to pound include array. And once I do that, I can compile again, and the build succeeded. I'll run the code to show that it works the same way it did before. And you might be saying, well, that's not really a win yet. And that's true. We haven't actually seen the win yet, but we'll see it soon. One of the things we can do with the array container is actually access the size function of the array container rather than using standard size here. So I can treat scores like an object like we've done before. So I can actually call scores.size to access the size of the scores container. And I'll just change that every other place this appears, which is here and here. Now you'll notice, by the way, that I still used a range-based for loop here to walk the contents of the container. So containers also have an iterator. We can iterate across them using the range-based for loop, so I can keep doing that as well. Here's one of the huge wins for using an array container rather than using an array. So here we are printing out the scores, and if we make a mistake here, if I say less than or equal to rather than less than, now remember from our previous examples, when we used an array here, we actually just walked past the end of the array and continued looking at memory locations that weren't actually part of the array. If we try to do the same thing here with the array container, we actually crash with a debug assertion failed because our array subscript was out of range. So our code crashes here rather than just running past the end of the array and continuing to process memory. Now it turns out that with the scores container, we obviously can use the square bracket notation to access an element of the array, but we can also actually use an at function to access the element of the array. And if I do that, we get a separate debug error, but it actually still aborts. It still stops us from going past the end of the array. This at function is a safer way to access elements of the array. This crashing, when we use square brackets, is not in the C++ standard. In the C++ standard, walking past the end of an array's container still works the same way as with arrays. So that was a Visual Studio thing, that this crashes when I walk past the end of the array container with square bracket notation. But in the C++ standard, using at will always crash no matter which compiler you're using, as long as it implements the C++ standard. So the safety of using at across any C++ compiler is really one of the big wins of using an array container rather than just using an array. To recap, in this lecture we explored using the array container as an alternative to using arrays, and we also learned about the at function, which keeps us from indexing outside the array bounds, which is a great thing, so we don't just start walking through memory that's not part of the array, even though we think it is. Arrays are available in almost every modern programming language, but almost always, as in C++, we need to know exactly how many elements we need in the array when we create it. The same is true for the array container in C++. The vector container doesn't have that limitation. So what can we store in a vector? Anything, but every element of the vector needs to be the same data type. And the big win for us is vectors can grow and shrink as necessary as we run our code. Our starting code is the code from the previous lecture, and this time we're going to convert from using the array container to using the vector container. And the big win here is that our vector container can change in size at runtime. So we're no longer constrained to having an array of a specific size or an array container of a specific size. We can just have a vector container that grows and shrinks as needed. That also lets us have the user provide at runtime how many scores they want to enter, and then we'll have them enter that number of scores. So let's get started. We'll change this array to vector. We no longer have to provide a size because, as I said, the vector will grow and shrink as necessary. However, we have to come up here and instead of pound including array, we need to pound include vector. And now our scores variable will be a vector container of ints. We have some work to do. Get how many scores. So we'll prompt for and we'll tell the user what the valid range is. And I'll need a variable to store their answer in, so I'll just store num scores. So now I'm reading in how many scores they want to enter. And of course, in practice, we'd do a while loop here to make sure that they entered a valid number. That's not the point of this lecture, so we'll blast past that part. So now we're going to read in the scores. And I know I'm going to want a line break before I do that. But we can't do scores.size at this point. We could do scores.size, but scores.size will tell us 0 right now because we haven't added anything to our vector yet. So we're going to use numScores here just for this one as we populate the vector. The other thing we're going to need to do is we're going to declare a variable to hold the current score that the user enters. So we're not reading into scores I anymore. We can access elements of our vector using the square bracket notation just as we see here. But because we haven't filled up the vector yet, we'd be trying to access elements that aren't actually in the vector yet. So I'll change all these scores I in this for loop and while loop to that variable that we have right here. And now, at this point, right before we go back to the top of the for loop again, at this point, score is a valid score, but we haven't added it to our scores vector yet. The way we do that is we say scores, and we call the push back function, which will put the score that we just got at the back of our vector. So this is how we fill up the vector and add things to the vector. That's our sort of first new thing for the vector, in addition to being able to dynamically say how many scores there are going to be. So now we calculate the average. Again, the vector container is a range, so it has an iterator, so we can use the range-based for loop here. And it has a size function, so we can find out how many things are in the vector right now. And then we can print out everything in the vector and the average just like we've been doing. So if I run the code here, so I'm going to say I'm going to enter 3 scores. And now I entered the 3 scores. And as you can see, it calculates the average properly and iterates over the scores properly, just as we'd expect. One more thing I want to show you, the vector container has lots of different functions we can call. As you can see, we've got pushback, we've got size. There's another function that you might find convenient to use periodically. So I'll say clear the scores. I can do this. I can take my scores vector and I can call the clear function on that vector. And now if I run the code, I'll enter 3 scores again, 1, 2, 3, and it calculates the average just fine, but the vector is now empty. So when I get to this for loop, scores.size is 0, and 0 is not less than 0, so we don't even print out any scores. So the clear function empties the vector. And you'll find this to be really useful if you have a vector field in a class and you want to reuse that vector multiple times as your program runs. I'm going to comment this out before I give it to you, and we can see one more time that we're back to working the way we used to work. To recap, in this lecture, we learned how to use a vector instead of an array or an array container when the number of elements we need to store is likely to change. Over the last few lectures, we've explored the C++ array and vector containers. In this lecture, you'll learn about the Unreal T-array container, which is the container you should use in your Unreal games. What can we store in a T-array? Anything, but a particular T-array can only store a single data type, and T-arrays can grow and shrink as necessary as our code runs. We're not going to look at any code in this lecture because we're going to use the Unreal T-array container in the next lecture. However, this can be a little confusing because, first of all, you should not try to use the standard containers in Unreal. We should just use the containers that are provided in Unreal. Why did I teach you those C++ containers? Because I'm teaching you both C++ and Unreal Engine. But despite what we learned about the array container and the vector container in the previous lectures, when we're in Unreal, we'll use the T-array container. Now, the reason this can be a little confusing is because the T-array container in Unreal basically corresponds to the vector container in pure C++. So it's too bad this is not called T-vector. There is a T-vector in Unreal, but T-array is what we want to use for dynamically sized containers of things. So the big idea is T-array is our container, and I'm going to scroll down and talk about a few of the things in the documentation, but really we'll put this into practice in the next lecture. So it's a container. It can dynamically grow. We do have to store only one type in it. So it's a homogeneous container. It can only store a single data type for each of the elements, just like we had for both array and vector containers in pure C++. So we create an array like we created a vector in standard C++. So we put T-array. It's a class template just like the containers we've looked at. So we put the data type of the elements and then we put the variable name. This gives us an empty array. There's no memory allocated yet. It's just like an empty vector. And we can populate them in a variety of different ways. You'll typically see me use add as the function to add elements to my T-array variables. There is an in place function as well, but I'll typically use add. We can also append, so we can add a number of different things to our T-array all at once. So this is actually helpful. We can insert an element at a particular location in our T-array rather than just pushing it on the back of a vector, for example. We can iterate over our T-array variables either using the range-based for loop, because the T-array is a container that has an iterator. It is a range. And we can also use a standard for loop if we choose to do so. And as you can see here, we have a num function that corresponds to the size function for the C++ array and vector containers. And that's a whirlwind tour of the T-array container in Unreal. We'll learn about how to use all the capabilities we need as we need them as we use the T-array container in our Unreal games. To recap, in this lecture you learned about the Unreal T-array container, and you learned that that's the container you should use in your Unreal games. And we also learned that the Unreal T-array container is similar to, but not identical to, the C++ vector container. In this lecture, you'll see how a teddy bear can collect things using T-arrays, of course. Let's go take a look. We'll start by talking about how the game actually works, and then we'll look at how it's implemented. So when I run the game, I have Ted the collector here, and I can right-click in the game world to place a pickup for Ted to collect. And I can place multiple pickups along the way, as many as I want, but when I left-click, Ted will collect the pickups in the order in which they were placed. So Ted will always pick the oldest pickup first. You can see Ted just passes right over other pickups. I can start him collecting and then add more and he'll keep going. But once he's collected all the pickups in the game, he stops and waits for another left click to start collecting again. We have a number of C++ classes here. We have a class for the pickup, and I did that not because a pickup has behavior, but because I wanted to create a blueprint from that pickup. I have a pawn and a player controller for Ted, and I have a custom game mode that I've used to set up the pawn and the player controller in the ways you've seen me do that before. In our content, you can see I have the blueprint for the pickup, the blueprint for the pawn, and the blueprint for the player controller. Now there is some configuration stuff that I had to do for collisions to make sure that collisions worked properly. In other words, I didn't want a physical collision between Ted and the pickups. I wanted Ted to be able to pass over them and sort of trigger when Ted overlaps with one of those pickups, so that I could either ignore that overlap or I could say, oh, this is the target pickup that I was trying to pick up. To do that, in the pickup, the static mesh for the pickup, I needed to set up a custom collision preset, enable collisions, and I marked this object as world static. And I have it so it blocks physics bodies, and Ted is a physics body, and very importantly, I checked this box that says generate overlap events. So when an event occurs, I want the engine to tell me that that happened, and we have to click that box to make that happen. So the other thing I had to do is in the pawn, in the static mesh for the pawn, I also had to click that generate overlap events, custom again, I am a physics body, and I said I want to overlap with world static objects. So those are configuration things that I had to do to make it so that the engine would tell me when the TED pawn overlaps with a pickup. Let's go take a look at all the C++ code that I wrote to make this game work. In the player controller header file, I declared a property so that I could populate in the editor the pickup, so that when I right click, I will place a pickup. So this is the actor that I'm going to place when I right click. I'm setting up my input component as you've seen me do before with player controllers. I have a place pickup function so that I place a pickup on particular input, specifically a right click. I collect pickups on a left click, and I destroy a given pickup when the pawn tells me I've run into the target pickup. The pawn will call this function so that I can destroy it and take it out of the T array. So I wanted to do this particular game in this lecture so that we could use a T array to maintain our set of pickups that we've placed. And because we will add our pickups to the end of the T array, the ordering in the T array, the front of the T array, the element at index 0 is the oldest pickup, so that will be the target. I want to point out that I didn't mention this when we were talking about T arrays in the previous lecture, but it's very important if you have a T array field that you mark it with the U property macro. That's so that the engine does appropriate garbage collection. It's not because, like we did up here, so we could edit it in the editor or anything like that. It's to make sure that garbage collection works properly on this T array. So if you're ever declaring a T array field, you need to mark it as U property. I also have this Boolean that tells whether or not we're collecting, and when the game starts, we're not. And I have one more function that tells TED to go to the next pickup. And we'll see how that all works in a moment. In the implementation file, I've set up two action mappings. I set up one for place pickup with the right mouse button, and will respond when that is released, and will place a pickup. And I defined another one called collect pickups that responds to the left mouse button being released and will call the collect pickups function. How do we place a pickup? Well, we figure out where the mouse is because we want to place the pickup where the mouse is right now. And remember, we used this when we were doing mouse input to make our character follow the mouse. This is how we figured out the world location of the mouse position. Setting X to 0 so we stay in the YZ plane. And so I'm using spawn actor here just like our spawners have used to spawn a pickup, specifically the one we populated in the editor at this world location, not rotated. Now previously when we used spawn actor, we sort of just had this, but this function actually returns a pointer to the pickup that got spawned. And we need that because we want to include it in our, I said list of pickups here, but it's really our T array, right? This is the T array, and we've added this new pickup that we just spawned into the world. And the add function adds this pointer to a pickup at the end of our T array. And that's what keeps our T array in chronological order, where the front is the oldest and the back is the newest. When we left click, so this function gets called, if we're already collecting, we just ignore it. We say, okay, well, I'm already collecting, so I don't care that you left clicked. But if I wasn't collecting on a left click, I go to the next pickup. And here's how I go to the next pickup. If there's at least one pickup in our pickups T array, so the num function tells us how many elements are in the T array right now, I get the target pickup, we know it's at index 0, and I put it into a local variable. And remember, this is a pointer to a pickup actor, not the actual actor. And then I remove this pickup from the T array. And the remove at function lets us provide an index, and it will remove the element that's at that index. So first we have to grab it and save it, and then we take it out of the T array because we don't want it in that set of pickups that we still need to go pick up. Once we've done that, we get our pawn that we're controlling, and as long as it's not a null pointer, we tell our pawn to go to that target pickup. And we'll take a look at that when we start looking at the pawn. So here's where we called go to next pickup. The other thing is when the pawn reaches a target pickup, it calls this function to say destroy it. And we need it to happen that way because the player controller is maintaining our T array of pickups. So it has to know when the pawn has reached the target pickup. So the pickup gets passed in, and we remove it from our T array, and we destroy it out of the game world. And now we know there may be more pickups that have been placed in the world, so we want to go to the next one. And we already looked at that go to next pickup function. That's it for the player controller. For the pawn, we need a reference to the static mesh component for the pawn because we're going to push the pawn toward a pickup and to use the physics engine to add an impulse, we need the static mesh. So I'm saving it here in a field so that we don't have to go get it every time the pawn is sent to another pickup. So that's an efficiency thing. We have the typical constructor in begin play and tick. Here's the go-to pickup that the player controller calls in the pawn when it's supposed to go to a pickup, and it passes the target pickup into the pawn. This function right here is going to act as what's called a delegate for when we get an overlap between a pickup and the pawn. Unfortunately, there's lots of stuff we need to know sort of all at once before we can do interesting things, but just trust me and I'll talk through a little bit about how this works, but I promise you we'll actually be talking about delegates in much more detail in the last course in the specialization. I have a constant for the magnitude of the force I'm going to apply to the pawn when I get it moving. I have a target pickup that I'm going to save, and we'll see why, but I've saved it as a field so that it persists in the pawn as time passes, because we'll need that to detect when we get an overlap, whether we're overlapping with the target pickup or not. And then finally, a utility function to get the force vector between two locations, because when we need to go to a pickup, we need to figure out the direction and the magnitude of the force to apply to the pawn's static mesh to do that. And this function helps us with that job. In the implementation file for the TED pawn, in begin play, this is where I'm saving the static mesh component. So here's a T array, just because we need a T array as our argument here for get components. So basically what we're saying is we're going to have a T array of pointers to all the static mesh components that are attached to the pawn. And then we call the get components function with static mesh components to populate static mesh components. So when we get to line 30, static mesh components is a T array that has 0 or more static mesh component pointers in it. We check to make sure there's at least one, and if there is, we take it and we save it into our field. And remember, we're doing all of this work because the static mesh component is the thing that will add a force to actually get our pawn moving. This is the delegate thing. So our static mesh component, we're saying when the onComponentBegin overlap event occurs. So we've just entered an overlap on this frame with the static mesh component for the pawn and something else. We say call this onOverlapBegin function that we wrote. We've seen this sort of thing before, right? When we've bound functions to be called when input is provided. This is the same idea. It's just a little more complicated. And like I said, we'll discuss this in much more detail in a couple more courses. Here's that onOverlapBegin. So here's what I do. The parameter that I care about, if this function gets called, is the other actor, the thing that the pawn is overlapping with. So first of all, I just make sure there's no error in the way this function has been called, and then I check to see if the other actor is the target pickup. If it isn't, I'm all done. I don't have to do anything. I just keep moving along my velocity vector the way I was before. This is not the pickup you're looking for. But if it is the target pickup, I want to stop the pawn. So I do that by calling the setAllPhysicsLinearVelocity function to 0. So as you can imagine, right, I'm setting linear velocity to 0. So that means stopped. And I also do that on the static mesh component. So we're applying these physics things to the static mesh component. The other thing I do is I get the thing that's controlling me right now. We haven't seen this before, but it's similar to the get pawn from the controller side. This is from the pawn saying who is possessing me right now, making sure that we get the TED player controller. And if we do, we call the destroy pickup function with the target pickup, the one we were looking for. And then as we saw, the TED player controller removes that pickup from our T array and destroys it in the world and then moves on to the next pickup. The goTo pickup function, we save the pickup that gets passed in as a parameter into our target pickup field, and then we get the force vector from the pawn, get actor location, and the location of our target pickup, and that gives us the force vector, and then we add an impulse. This is an impulse force, so think of it as whacking the pawn with a baseball bat or something, and it will whack the pawn with a baseball bat. It will add an impulse force in the direction of the force vector with the magnitude of the force vector. Finally, that last function I was talking about, the get force vector, we simply subtract TED location from pickup location, so that gives us a direction, but the direction has a magnitude that is based on how far away the pickup is from the pawn, right? The Pythagorean theorem tells us that the magnitude of this direction vector will be dependent on the distance. So what we do is we normalize the direction vector so it is a pure direction vector. So when we normalize a vector, we give it a length of 1. So no matter what direction it's pointing in, its length is 1. But it's pointing from the pawn to the pickup. And then finally, we return that unit vector multiplied by force magnitude, and that's the force vector that we want to apply. So I know that's a lot of code and a lot of new stuff, but this is a really good way to implement the game as I showed you. Before I finish, I'm going to show you a flaw in the game. I probably shouldn't, but I will. So back in the editor, if I run the game and I place two pickups really close to each other, watch what happens when the teddy bear goes. He just leaves and never picks up the next pickup. So the issue is that the onBegin overlap event happens on the beginning of an overlap. But when we ended up hitting that first pickup, we were already overlapping with the second pickup, so the event was never fired, so we couldn't pick it up. There's certainly a way to solve this problem. We can take a particular actor, like the pawn, and we can find out all the actors we're currently overlapping with. So when we're told to go to a next pickup, we could actually check to see if we're already overlapping with the target pickup. And if we are, we could immediately tell the player controller, okay, destroy the next one, I'm already there. That was more complexity than I wanted to add because I think we have enough complexity as it is in this game, but that's also a solvable problem. To recap, in this lecture you saw how we can use T-arrays in a small game. Congratulations on making it through the second course in the C++ Programming for Unreal Game Development Specialization. I hope you enjoyed the course and I hope you learned a lot as well. And if you feel like you have enough to just go off and start building your games, then go ahead and do that. If you'd like to learn more about both C++ and the Unreal Game Engine, then you should just move on to the next course in the specialization. No matter what, I appreciate your joining me in this course. I really have a blast doing these courses, and I'm glad you came along for the ride. Cheers.